स्कॉलर्स टीआईएफआर में जो कटिंग एज रिसर्च हो रहे हैं उसके बारे में लेक्चर देंगे, और उसके बीच बीच में हम ये भी चेक करेंगे कि आप कितना साइंटिफिकली अवेयर है। तो हमने क्विज अरेंज किया है, ठीक है। और क्विज में काफ़ी सारे एक्साइटिंग गुडीज हम एज प्राइज देंगे। सो बी हियर फॉर द क्विज एज वेल इफ यू वांट टू। नाउ सिंस वी आर like short of time, I would like to introduce our first speaker, who's Professor Onkar Parikar. He is a expert in TIF. Hello. Yeah, he's an expert in quantum gravity, field theory, and whatnot. And he will be telling you about black holes and quantum gravity. And so brace yourself for the exciting talk about quantum gravity. I hand over the mic to Professor Unkar. Yeah.
Hi, good morning. Can you hear me clearly? Yeah? Okay, great. So welcome to TIFR. Happy National Science Day to you. So my name is Onkar, and I'm going to tell you about some of the work that we are doing on black holes and the search for quantum gravity. This talk will be sort of a broad outline of the history of this subject and where we are currently and where we are headed in the quest for quantum gravity. But along the way, I'll try to explain what some of these words mean. If you have any questions along the way, please feel free to just ask. All right? Okay. So, two of the most foundational theories, or you might call them foundational pillars of modern theoretical physics, are quantum mechanics and general relativity. Many of you have probably heard these words at least. So these are foundational theories of theoretical physics which were developed in the early 20th century, around 1910s, 1920s. And both of these theories have been tremendously successful, right? Namely that they have been subjected to experimental verifications for over 100 years now. This is 2026. It's been more than 100 years. And both of these theories have been tested experimentally over and over and over again, and we've not found any violations of these theories so far. So it's fair to say that quantum mechanics and general relativity, or Einstein's theory of gravity, are two of the most experimentally tested and most successful theories upon which the foundations of modern theoretical physics are built. Okay, so what is quantum mechanics? Basically, quantum mechanics is the study, or is the physics of tiny things, tiny particles, subatomic particles, right? In school, perhaps we study Newtonian mechanics. Many of you have studied Newton's laws, right? These things are applicable at the length scales that we work at, or the energy scales that we operate at. But when you go to the subatomic world, when you talk about the hydrogen atom or things like that, very fundamental constituents of matter, they don't really follow the laws of classical mechanics, or the laws of Newton's laws, as we call them. Okay, they follow a slightly complicated set of equations, which are called quantum mechanics collectively. Okay. And in essence, what quantum mechanics says is that particles are not really particles, okay, point-like particles, but they're more like clouds, okay? They're more like probability clouds. So the particle could be here or it could be here. It's not at a fixed place. And it doesn't have a fixed velocity, but there is some probability associated with it. It's like a cloud, okay? So for instance, in this picture over here, you see what an electron looks like in the hydrogen atom. And you see it sort of looks like a cloud, right? It doesn't look like a particle anymore, okay? It looks like a cloud. It's a probability cloud that could be here or it could be there. It's a little fuzzy, okay? It's not a very sharp object. And what quantum mechanics tells you is the dynamics of this probability cloud, okay? How does this probability distribution evolve as a function of time? And it says that these particles, which look like these little fuzzy things, they also have some wave-like properties, okay? They interfere like waves interfere, okay? And while this is very counterintuitive, we never see these things at the scales that we live at. these equations or this theory has been very experimentally successful. Okay, so we've been able to explain everything from the hydrogen atom to even more subatomic particles like quarks and gluons, the fundamental constituents of nuclei. Okay, all of those things are more or less completely described by the laws of quantum mechanics. There is a little bit of sophistication, but something called quantum field theory. But for our purposes, we don't need to worry about that. Quantum mechanics basically describes all of the basic physics of subatomic particles as we know it. Okay. On the other hand, there is Einstein's theory of gravity. Many of you have probably heard about it. Okay. Einstein's theory of gravity deals with physics at the very large scales, like planetary motion, okay, like the evolution of the cosmos, or galaxy formation, galaxy motion, things like that. Okay. And the basic premise of Einstein's theory of gravity is that you should think of space and time as one object. Okay, it's sort of what is called a space-time continuum. And then what gravity is that gravity is curvature of the space-time. Okay, space-time is not flat. It's not like a sheet. A flat sheet. It's a sort of a sheet that can bend around. Okay, and when you have matter, like let's say the sun or Earth, then that matter, some heavy object, it bends this sheet. It bends space-time. It introduces curvature, and that curvature is experienced by other objects as gravity. Okay, so matter curves space-time, and then that curvature of space-time is felt by other objects moving around that matter as gravity. Okay, and while this is the Einstein theory is very is beautiful, it's written in terms of geometry, as you can imagine, right? Like sheets and bending of sheets and stuff like that. It's a completely geometric theory. The really remarkable thing about this theory is that it has non-trivial experimental predictions. Things like the precession of Mercury's orbit, bending of light, gravitational redshift. These things were not explained by Newton's laws of gravity. Einstein's theory made these predictions, and then these predictions were experimentally verified. Okay. So again, Einstein's theory of gravity, which we call general relativity, is a very experimentally successful theory. By now we have tons of evidence that the predictions of general relativity are correct. Okay, general relativity is correct. Okay, and for the most part, quantum mechanics and general relativity work very well. Okay, quantum mechanics describes the physics of subatomic particles. General relativity describes the physics of very big things, planets, stars, galaxies, those kind of things. And they work at very different scales, as you can imagine. Quantum mechanics at subatomic scales, general relativity at cosmic scales, and they are very successful in the regimes where they're applicable. And life is good. What else do you need, right? But in some situations, you're basically forced to apply these two principles together. Okay, this happens most strikingly in the context of black holes, as I will explain. Okay, and then when you try and apply quantum mechanics and general relativity together, then you run into contradictions. Okay. Okay, so what are black holes? Black holes are certain solutions in Einstein's theory of general relativity. Okay, one way to think about them is to think about a star which collapses on itself under its own gravitational pull. Okay, and what happens is that when such a process happens, the gravitational field outside this object has become so dense that the gravitational field outside this object is very strong, and not even light can escape the gravitational pull of this object. Okay, that's essentially what a black hole is. So it's very a bizarre object, right? We don't see such things around us. I mean, of course, they're out there in the cosmos, but it's a bizarre object. It's so heavy but so small at the same time, right? Heavy and small. That's what makes it complicated. It's so heavy and so small that not even light can escape its horizon. The horizon is the surface around a black hole, from which even light cannot escape. Okay. So anything and everything that falls into a black hole is doomed forever, because if light cannot escape the horizon of a black hole, nothing else can, because the speed of light is the maximum speed that anything can move at. That is one of the principles of relativity, if you've encountered it before, okay? So everything is doomed inside a black hole, and everything that falls into a black hole eventually ends up in what is called the black hole singularity, okay? The black hole singularity is a very, very mysterious thing. It's there in Einstein's equations predict that there should be a black hole singularity in space-time, but it's a place so extreme that it's almost as if space-time itself gets crushed, okay? Space-time itself stops existing at that point, okay? And this black hole singularity is not understood in general relativity, okay? We don't understand how to, basically the equations of general relativity break down at that point, at the black hole singularity. We don't really understand what to make of that, okay? This is an open problem as of now. It's generally what people will tell you, or people will say, is that, okay, general relativity works at very, very long length scales, right? Since the black hole singularity has such extreme curvatures, or it is such a small place, or it has such a small size, maybe quantum mechanics is important there, right? Quantum mechanics will come in and save the day. It will cure this black hole singularity. Okay, so then one sort of hopes that one can put quantum mechanics and general relativity together and make sense of the black hole singularity. But even before you do that, the moment you try and apply quantum mechanics to black holes, you run into another puzzle, okay? This is called the black hole information puzzle, for which was discovered by Stephen Hawking, and he was famous for it, okay? The essential problem is that quantum mechanics is what we call a unitary theory. By unitary, that's just a fancy word. What it means is that the total probability in quantum mechanics should be conserved. Information should be conserved. You're not allowed to lose information, okay? That's just how quantum mechanics works. It's a theory where total amount of information is conserved, much like total energy in everyday life is conserved. You know, there is some abstract notion of information in quantum mechanics, and that notion of information, how much information one has about a system, cannot be destroyed, okay? That's roughly what that means. And quantum mechanics has that property, okay? But if you try and apply quantum mechanics in the presence of a black hole, you run into a problem, because some amount of information can fall into the black hole and get lost forever, right? Because anything that falls into a black hole never comes out, all right? So then you run into this contradiction where some information can fall into a black hole, get lost forever, and then quantum mechanics does not remain unitary anymore. Namely, information can get destroyed in the presence of a black hole, okay? This is what is called the information loss problem. And it was discovered in the 70s, as I said, by Stephen Hawking, and it's been around for the last 50 years or so. I would say it's still not completely resolved, but I'll tell you where we are in terms of understanding this problem. Okay, so that sort of motivates us to confront the question of quantum gravity. Okay, there must be some underlying theory of quantum gravity which merges quantum mechanics at the very subatomic scales and general relativity at the very big scales, and combines them into one consistent theory, which works not just at one scale or the other, but everywhere, right? Which we can apply consistently, let's say, to black holes, to understand singularities, to understand the information problem, and so on. And to just give you some intuition for why this is so hard, you see, Einstein's theory is a very smooth and geometric theory. Okay, it's based on geometry, sheets and bending of sheets and stuff like that. It's very, very smooth and geometric theory, but quantum mechanics is inherently discrete. The word quantum means one discrete unit, right? So quantum jump means discrete jumps, right? Quantum mechanics in its very nature is a very discrete kind of theory. And so it's hard to put them together, okay? On the one hand, quantum mechanics is very discrete. On the other hand, Einstein's theory is so smooth and continuous. How do you put them together? Okay, that is essentially like one of the difficulties in putting these two theories together. But we do expect that whatever this final theory of quantum gravity is, it should presumably replace our notions of a smooth space-time continuum with some new notion of quantum space-time. So this is not fully understood yet, and that's what some of us are working towards. Okay. All right. Now a big revolution happened in this field. So this was sort of around before, this was the state of the art before 1995 or so. A big revolution happened in 1997. Okay. This is now called the holographic correspondence. At the time, it was called ADS-CFT. So around 1997, Juan Maldacena proposed a theory of quantum gravity. Okay, he said that quantum gravity in a particular class of spacetimes called anti-de Sitter spacetimes, that is the word that is where the word ADS comes from. Okay, it doesn't really matter for our purposes what that is. It's just a certain class of solutions of general relativity. So Juan proposed that in these class of spacetimes, you can understand gravity completely, quantum gravity completely, and in fact, that quantum gravity theory is something that we had already understood before. Okay, he proposed in this very radical idea that this quantum theory of gravity is actually completely equivalent to a dual theory. Okay, a dual theory, which in this the dual theory is a perfectly quantum mechanical theory. It's what is called a conformal field theory. That's where the name CFT comes from. But never mind what that means. Okay. The basic point was that Juan suggested that quantum gravity in these ADS spacetimes is essentially completely equivalent. It doesn't look like it, but it's completely equivalent to a purely quantum mechanical theory without gravity. Okay. Now, why is that great? That's great because quantum mechanics without gravity is fully understood. Okay, we understand what that is. All right, there are no issues, there are no puzzles. We can make sense of it. It's perfectly unitary. There is no information loss. There are no singularities. We understand that theory completely. On the other hand, quantum gravity has all these issues that I was describing to you. There's black hole information loss. There is black hole singularities. We don't fully understand it. But Juan came along and said, well, look, they don't look like they're equivalent, but these two theories are in fact equivalent. Okay, so if they are equivalent, then you can construct a map between quantum gravity and this non-gravitational quantum theory and try to understand these puzzles on the quantum gravity side. Okay, so that's why ADS-CFT was so revolutionary. It gave us a direct map between quantum gravity on the one hand, which is so poorly understood, and an ordinary quantum mechanical theory, which is so well understood. Okay. Now, the amazing thing about this correspondence is that the dual theory, which is this quantum mechanical theory that I was telling you about, it lives not in ADS spacetime, but on its boundary. So it's one lower dimensional. Okay. So that's saying that a gravitational theory, let's say in 4 dimensions, like the 4 dimensions that we live in, is actually secretly equivalent to a 3-dimensional quantum mechanical system. Okay. That's where the name holography comes from. It's sort of holographic. It's like a holographic projection from 3 dimensions into 4 dimensions. Okay. And the amazing thing is that this 4-dimensional theory is gravitational. It has gravity in it. It has black holes. It has other gravitational effects. Whereas the 3-dimensional theory has no such thing. It's a purely quantum mechanical theory, no gravity, no nothing. We understand it completely. Okay. So that's where ADS-CFT was so powerful and so such a radical idea. And then shortly after Juan proposed ADS-CFT, people worked out a dictionary. Now, when you say that these two theories are equivalent, it's not totally obvious how. I mean, that statement is only meaningful if you tell me how to go from one to the other, right? If I wanted to do some calculations in quantum gravity, how would I go about doing them? Well, I would need a dictionary. I should be able to translate the observables of the quantum gravitational theory into the boundary into the quantum mechanical system, and then do some calculations and see that they agree. So shortly after ADS-CFT was proposed, people came up with this dictionary or some version of this dictionary. And then since then, many different calculations have been done, it's been confirmed, and it seems as of now that the duality works. Okay, many of these calculations look very different. Like on the gravity side, you're doing some calculations with geometry, as I was saying. You're calculating some geometric object with Einstein's equations and stuff like that. Whereas on this boundary side and this dual quantum mechanical side, you're using quantum mechanics. It's more like calculating things in quantum mechanics. So these calculations look completely different on the face of it, but magically the answers match. Okay, that's where the power and the magic of ADS-CFT comes. And in many ways, one might even say that space-time, the geometric notion of space-time in this picture, sort of emerges from quantum mechanics. So while we started by looking for a quantum theory of space-time, it looks like space-time is not a fundamental thing, but sort of emerges from within quantum mechanics. Okay, that's sort of where this is headed. So let me give you one example of how this works. You may have heard the word entanglement. If not, I'll sort of briefly tell you what it means. So entanglement is an essential property of quantum systems. Okay. Usually, we think that particles which are very, very far separated from each other have nothing to do with each other, and they're sort of independent particles. But that's not what happens in quantum mechanics. Okay. In quantum mechanics, entanglement is an essential property of quantum systems where particles which are very, very far separated or distantly separated can nevertheless be intertwined. Okay, so the properties of one particle are associated with the properties of the other particle, even if they are very, very far separated from each other. Okay, that phenomenon is called entanglement. It's present in quantum mechanics. It's just a property of quantum mechanics. It's everywhere in quantum mechanics. Okay, and in fact, that is what makes quantum systems very different from classical systems. And you probably have heard of words like quantum computation, quantum computers, quantum information theory. These things are now becoming so useful and powerful precisely because of what I just said, because of this property of quantum mechanics called entanglement. Okay, and in this ADS-CFT correspondence, you can describe entanglement in terms of what is called entanglement entropy. Never you mind what that means. It's some measure of how much entanglement there is on the boundary theory. In a revolutionary paper in about 2006, Ryu and Takayanagi showed that on the ADS side or on the gravity side, you can calculate this entanglement entropy by just calculating the area of some surface. Okay, so this is an example of what I mean when I say that there are very different calculations happening. On the quantum mechanics side, you're calculating some measure of how much entanglement there is. On the gravity side, you're calculating the area of some surface, some geometric object, and magically the answers match. Okay? And so since then, the Ryu-Takayanagi formula has sort of led to a very rich confluence between the theory of quantum information and computation and gravity, research in gravity. And in fact, the black hole information problem can also be addressed. The problem that I mentioned to you, the black hole information problem can be addressed using the Ryu-Takayanagi formula. And in a series of papers around 2019 or so, people actually did calculations in gravity and confirmed that information is not lost in ADS-CFT using the Ryu-Takayanagi formula. Okay. Interestingly, some non-local effects like gravitational wormholes play an important role in these calculations, but I'll just skip over that. So where is this headed? What is the road ahead? I suppose the idea, the punchline is that we don't really understand quantum gravity in any detail, but we still feel that we are on the right track. Okay, we have ADS-CFT. We have at least one consistent framework in which we understand how quantum gravity could work. There are many, many open questions. We don't understand the black hole singularity and its resolution. Even within ADS-CFT, that's not understood. Issues like cosmology, the Big Bang singularity, things like that, those are still not understood. How to make sense of them within quantum mechanics is not understood. And ultimately, of course, we hope to have a theory which will combine general relativity at the very big scales, quantum mechanics at the very small scales, and come up with a consistent theory of quantum space-time. That ultimate theory we haven't found, but we believe that we are on the right track with ADS-CFT. So these are my colleagues at TIFR in the string theory group who work on these ideas. Thank you. If you have any questions, feel free to ask.
Hello. Thank you, Professor Onkar. So, ये आई मुझे लगता है इतने अच्छे टॉक के बाद आपको बहुत सारे क्वेश्चंस होंगे, तो उससे पहले मैं प्रोफेसर ओंकार को रिक्वेस्ट summarize this in Hindi, like Hindi is not that. Okay. तो अगर आपके पास कोई क्वेश्चन है, प्लीज रेज योर हैंड्स एंड आस्क द क्वेश्चन टू प्रोफेसर ओंकार.
Hello. If a theory of relativity is correct, which is correct, so it is possible to create a wormhole in space-time to go from one point to point from greater than light of speed.
Well, so the wormholes that one, okay, indeed it's true that there are wormholes in general relativity, but the wormholes that one can consistently construct are of the type which cannot be traversed. So these are called non-traversable wormholes. What that means is that these wormholes can exist, but no observer can go through them.
No.
From this side to the other side in violation of what might seem like a violation of causality, right?
Is any other way to go faster than speed of light?
Not that we know of. That's one of the fundamental principles of general relativity, which is that you cannot violate you cannot violate causality. Namely, you cannot go faster than the speed of light.
Is if we find any other life form on the very far light of years, so if you want to go there, we need something which can go faster than speed
I have
of
to say, I won't be able to help you with that.
light. Okay, thank you.
Any more questions? Yes.
About the mapping between ADS system and quantum mechanical system. One is 4-dimensional, that we know 3-dimensional space and time. The second is 3-dimensional. What dimension is lost and how?
Yeah, so a good question. So the 3-dimensional system is 2 space and 1 time dimension. So roughly speaking, 1 space dimension gets lost in this mapping. So you can say that one of the spatial dimensions of the ADS gravitational system emerges from quantum mechanics in the 2 + 1 dimensional system.
Like ADS to
No.
quantum mechanics
So
and back?
no, these two theories are believed to be exactly equivalent, which means that there is no information loss. We don't fully understand the map in such detail as to show that what every single observable here maps to every single observable in the other description. That would of course be the dream, to come up with a map which is completely one-to-one and show that every single observable can be mapped. This dictionary is not understood in that detail. It's understood in a somewhat approximate way, but it's believed that the map is exact and that there should not be any loss in this mapping.
Any more questions? Yes.
There's a question.
Inside black hole, are there higher dimensions present?
Higher dimensions present? Well, unfortunately, the interior of a black hole is not that well understood. It's a very complicated place that we don't fully understand how to describe. Einstein's theory has solutions where you can sort of go inside a black hole and then open up into another different universe. So certainly there are solutions where you can imagine new dimensions, which are small outside, becoming large inside the interior of a black hole. Such solutions probably exist. But unfortunately, we don't completely understand the black hole interior so well to be able to say anything concrete. I mean, solutions exist in general relativity, where you can go into the black hole interior and open up into other universes. Those are very easy to find.
Hello, sir. So my question is regarding which of the physics fields fail at the pinpoint of the black hole, and which are those equations which fail at the entrance of the black hole, and what could be the possible solution so that we could have some equations or some unified equation or some branch of physics which could explain this phenomena of black hole.
You mean is your question which equations fail at the black
At
hole
the
singularity?
Pinpoint of the black hole, yes.
Singular, yeah.
Yeah.
So, okay, so essentially Einstein's equations, as I was telling you, so first of all, the black hole is a solution to Einstein's equations, okay? So there is an equation in general relativity called Einstein's equation, and that's basically that equation describes how matter curves spacetime, okay? If you solve that equation, you can get the black hole out as a solution, okay? And that solution has a singularity. What that means is that when you go close to that singularity, the curvature or how curved spacetime is, there's some measure of how curved the spacetime can be, that curvature blows up, okay? It diverges near the black hole singularity. So what that means is that another way to say this is that because the curvature of spacetime is becoming so large, the effective size of spacetime is becoming very small. Very, very tiny things curled at a very, very small scale have very large curvature, right? So the scale at which spacetime is curved is very, very small. It's curved into a very, very tiny region. And because of that, quantum mechanics is important. Okay, so you cannot ignore quantum mechanical effects at the close to the singularity. All right, so to address your question, the expectation, first of all, what goes bad at the singularity is Einstein's equation itself, because Einstein's equation is written in terms of curvature of spacetime, and that curvature is diverging near the singularity. Okay, and to address your second question, what do we expect to come and cure this divergence? Well, the natural expectation is that quantum mechanics will cure it, because the curvature is becoming so large and this thing is getting curled up into a very small thing. So maybe quantum mechanics saves the day. But we don't understand how this might work in any detail.
Any more questions?
Sir, is that possible that white holes exist as well?
Yes. So white holes are again solutions of Einstein's equations,
Yes.
which do exist.
And if they do, then what are the properties of them?
Well, in a black hole, stuff just falls in and never comes out. In a white hole, stuff comes out and never falls in some way.
So if that's the truth, then how does the stuff come out of it?
It's it existed in the past. It was just not causally accessible to the observer at infinity, and this stuff sort of comes out from the horizon of the black hole. You can see it at infinity. An observer at infinity can see it, but you can't fall into that white hole.
Okay.
Just from the fact that you can't violate causality. Yes.
If everything is made of atoms, means jumping of atom and atom, then what is thought? Means how we can imagine what is thought? Means according to quantum mechanics.
What is
Thought?
Thought. Well, thought is some very emergent thing which happens in your brain, right? So the brain is made up of whatever, I think the biologists can probably answer this question much better, but the brain is made up of neurons and so on and so forth. And these things are then further made up of atoms and so on. So what happens at the level of the brain is somehow an emergent phenomenon, which is, of course, ultimately described by quantum mechanics at the level of atoms. But then, the scale of the brain, quantum mechanics is not important because it's such a big system. Like in everyday experience, like when you throw a ball into the air, you don't really have to use quantum mechanics, because even though the ball is made out of atoms, you don't really care, right? That ball effectively follows Newton's equations of motion, right? Newton's laws are enough to describe its motion. It's something similar. The thought is an emergent phenomenon at the level of the brain. You don't really need quantum mechanics to describe it, as far as I know.
Okay.
Thank you.
Hi. Hello. Please try to stay quiet since the speaker is talking.
Sir, I've heard that near black holes, the time slows down. So what is exactly the relation between gravity and time?
Yeah. So in general relativity, time is sort of not an absolute thing. Okay. It depends on which observer is measuring it. Okay. And then different observers can have different notions of time, and then they can be related to each other in some specific way. Now, what happens near black holes is that the geometry of space-time is very curved, right? So remember that Einstein's theory of gravity describes not just space, but it describes space-time. Okay, so the geometry of space-time itself gets very curved, and near a black hole, or actually not just a black hole, near any gravitational object, even on the surface of the Earth, for instance, okay, the effect that gravity has is that it sort of dilates time. Okay, so that's sort of what you were referring to. It's sometimes called time dilation. So if you go very, very close to the surface of the Earth, the notion of time gets very dilated with respect to someone sitting far away, and that happens because of what I described. The gravitational effect of a heavy object is basically to change or to warp the notion of space-time itself. Yeah. I think there's one question there. Yeah. Yes. Go on. Go on. You can talk in any language you want. I'll come there. I can't hear you. Yeah, speak up. Hindi, you can talk in any language. Yeah. So one way to get that is that while light, it's not the light from within the black hole that you're seeing, it's the light of stuff around it. A black hole has a lot of stuff around it, and that emits light. So it's that light.
Yeah, everyone, there's a quiz. If you want to stick around, there's a quiz.
There's a quiz, by the way. So if you want to stick around, there are prizes as well.
You can fall into a black hole, yes. You don't have to do much. You just have to sit around it.
Hello, hello.
Mail you a question.
I can't hear you very well. Maybe
Hello,
you can.
hello.
Yeah.
Hello. Hello.
Yes.
Hello.
So we can enter in a spiral manner at the same speed of the black hole rotation. Can we enter without getting any damage to it?
Yeah, possibly. Yeah, that's right. If you rotate fast enough. Yeah.
Finding the black hole.
Hello.
Safety purpose or
Yeah. Everyone,
What is
please form a queue. If you are
exist
leaving the
as
foyer,
solutions to
please
Einstein.
form a queue.
Yeah.
Try to keep quiet. Form a
Ideology.
Hello. And if you want to participate in the quiz, you can stick around. Dear participants, please stay quiet. Form a queue if you are leaving the foyer area, or you can stick around for quiz. Hello. Yeah, people who are here, we can have quiz. Shall we start the quiz?
Yeah.
But the next time हमको ऐसे question answer round terminate करना पड़ेगा. You
Yeah,
see
yeah.
this situation?
Yeah, yeah.
No, this is not good. For all of you who are here, please come closer to this area so we can have a quiz session. So my friend Kiran will ask you a question from biology. From biology. तो आपको excitement है quiz के लिए? Do you think you are up for it? Okay, तो देखते हैं.
Hello.
First, note the question. But
Hello. Yeah. Slide number 2.
So the question is, what species of grass grows the longest? Please raise your hand.
Raise your hand if
You can Google it.
Okay.
Yeah.
So we'll give you the first chance. Do you know that?
Bamboo.
Bamboo. Bamboo is the right
He is
answer.
saying bamboo.
Yay.
So your name?
Manashvi Tripathi.
So Manashvi is going to get a pen from our side. So this looks like this was a very easy question. So let's do some hard stuff. Okay.
Yeah, because you are answering very easily and more than one person raised the hand. So we'll go to a harder one. Go to 24. 24.
Remember, the harder the question, better the
No,
prize.
No. Okay. So here's the question. Why does a strong chlorine smell at the pool actually mean the water is less clean?
Okay. Yeah, your name?
Anagha.
Anaka.
Yeah, so because like the water potential in the pool is lesser than the chlorine potential. The chlorine ions are more than the water ions.
Okay. So
The mic is.
the mic is can
Yeah. So basically, because the chlorine ions are lesser than the water ions, like the H plus ion. Chlorine is more, na? So what did I say? Oh, more. Okay. So the chlorine ions are more in number than the water ions. So like the H plus ions and the OH minus ions are lesser in number according to the chlorine ions. Cl minus.
But then how does the like smell of chlorine make the water less clean? That's the question you should answer. So uh, I yeah, you want to attempt this? Yeah.
So it's chlorination basically removes germs. So if you need more chlorine, that means the microbial load, the original microbial load was more. That's why I can guess that this is.
Hello. Check. Hello.
So this is closer to the answer, but Aishwarika.
Your call.
Your
Hello. Hello.
Oh, I said since chlorination is basically for removing germs, microbial load. So if you are using more chlorine, that means there was initial microbial load which was there in the water was more. So if you are adding more chlorine to nullify the germs and pollution, that means the water was less pollute. I mean less clean.
Now, odor. Right now, the pool is not clean. It's not like you have
Initially.
Yes. It's not like
So because as it is water, it has become impure because the presence of chlorine, extra chlorine.
That's
No.
that's not the answer we are looking for. So yeah.
So in the pool, what you actually smell, the chlorine smell is actually chlorate ions, which only form when chlorine interacts with bacteria and sweat and pee, and that's the indication that the pool is dirtier.
Exactly. Your name?
Arit.
Arit. So Arit has given the right answer and he wins a pen. T-shirt दो ना मतलब टफ क्वेश्चन के लिए टी-शर्ट निकालो ठीक है Okay, so are you liking the quiz? So you are excited for the next question? You want a challenging one or easier one? Easier one. Okay, let's get a easy question. Hello. So yeah. So all the junk food fans, there's a Diet Coke and normal Coke, which is inside a tin. So if you submerge both the tin, the can, inside water, the Coke will float, but the normal Coke won't float. Do you know the reason? Okay, let's, ma'am, your name and
Myself, Bhakti. I would like to try it again. Basically, something which floats or sinks is dependent on density. So, Diet Coke is not having sugars, which gives more density, like sugar syrup or something. So, could be because of that.
yeah, right answer. You this win this time. So yeah, there's a prize for you. Congratulations. So now what do you think? You want a easier question or a harder one? Come on, be up for the challenge. Okay. So let's go for another question. But you have to remember, if the question is hard, then you get better prize. You get a TFR t-shirt. Harder. Okay. So yeah, let's ask this one. So
Graphite are both made entirely of carbon atoms, but their structure gives them vastly different properties. What is the term used to describe different physical form which are made of the same element?
okay. Right.
And can you tell one more allotrope
Yeah. I have the mic.
Yeah.
for diamond and graphite, the third one?
I don't know for carbon. I know like
Your name
Uh,
and the answer.
Adva. So it's an allotrope.
Yes. And your name?
Adva.
The next part of the question? Okay. So
We need a prize over here.
Third allotrope is fullerene.
Yeah. That's the right
exactly.
answer.
So yeah, both of you get prizes. अरे अरे पेन ही दिए जा रहे हैं, पेन ही दिए जा रहे हैं, थोड़ा मिक्स कर देते, चॉकलेट देते हैं इजियर वन के लिए. So yeah, looks like you know your science. So we'll go for the next question and we'll try to make it challenging. Let's see if you know this answer. Please, volunteers, load the next question. क्या अच्छा, तुम लोग स्क्रीन इस पे शेयर कर रहे हो ना, जूम पे? हाँ. So आपने इतने अच्छे आंसर दिए कि टेक्निकल ग्लिच हो गया. So we'll have to wait for a minute or so and we'll resume the quiz.
What is the name of the science principle and what is the term that describes the upward force? We'll give him.
Buoyant force or buoyancy.
Yes, but then you have to name the principle as well. So anyone for the first part of the question, the name of the principle according to which the object submerged in any fluid remains floated, feels an upward force? Yes. Your name and then the answer.
My name is Omi, and is it the Archimedes principle?
So congratulations, both of you get prize. You for saying the name of the force. So yes, so the next question is, so the energy source of solar cell is from the photons of sunlight, right? So if you have a solar cell, the photon from the sunlight gets converted, the energy of the photons from sunlight gets converted into electricity. Now you have to say what is the energy source or what is the form of energy which is stored inside your lithium ion battery of your phones, laptops, and other devices. So yeah. Yeah, you want to take a guess? Yeah, the form of energy. So, next time you will be disqualified if you shout the answer. You first have to raise hands. So yeah,
Chemical.
so uh, chemical energy is not the form of energy which it is called. So you have to be a little more specific.
The chemical potential energy.
Yeah, chemical potential energy is the right answer. So your name?
Gunjan.
So congratulations, Gunjan. It was a good answer. So you get a prize. And I will request the volunteer to load the next question. Gunjan. So since you guys are really good at answering, next time I don't want you guys to shout the answer. Rather we want you whisper the answers to the volunteers. Okay. So that we can have multiple responses for a single question. So yeah, if you leave the refrigerator door open for several hours, it won't cool down your room. Okay. Rather, it may heat up your room than the original temperature. Which scientific principle explains or dictates this scenario? Which scientific, or if I rephrase the question, which scientific principle actually uh, stops the temperature from going down when you keep the refrigerator door open? Did you understood the question? You want to have a guess? Okay, so you have to whisper the answer. No, the question we are asking, which scientific principle it dictates the scenario that the room cannot be cooled down. Huh? So yeah. No. So any more guesses? Any more attempts?
Mahesh Yadav. The second law of thermodynamics.
Yes, that is the right answer, sir. You win a goodie from our side. One. So we can have more attempts if you want, since nobody heard the question answer. So let's. So the answer is the second law of thermodynamics, which states that you cannot have a lower temperature than the reservoir where you are drawing the temperature from. So you basically need a intermediate machine to run, and that machine operates and dumps the heat into the reservoir. So ultimately, if it cools down your room, its efficiency will be more than 100%, which is not possible according to the principle of second law of thermodynamics. Yeah. So yeah, you still want more questions? Okay, let's go for some more questions. कितने हो गए? हाँ, एक और कर सकते हैं. तो next one है. अभी कितना time बाकी है? 5 minutes. 5 minutes. Right?
Yeah, we have 5 minutes.
We have time for one more question. Okay, so
Yeah.
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 So you guys already have pivoted, so we'll give new participant chance first. If they don't answer correctly. Is that the right answer? But don't tell the answer. Okay, if हाँ? हाँ, हाँ. ये क्वेश्चन किसने बनाया था? Whisper the answer. Please don't shout the answer. क्या? हाँ. So okay, we'll take one more response, like one more answer, and we'll close the question.
Enamel.
Yes. So the answer is tooth enamel. So all of you who have whispered the answer will get a chocolate from our side. एक और उनको. अरे कहाँ है? हाँ.
इतना कम लोग
हाँ.
इतने कम है हवे लोग
हाँ.
इतने कम है अभी
हम्म. Escort volunteers around? Any escort volunteers around? Escort volunteers? Okay.
if any escort volunteer
If somebody can just inform them just to get the people around here. Yeah, so there will be rotation in the labs. So if somebody can just inform them just to get the people.
Okay. Okay, thank you for coming. We'll have the next talk here, next scientific talk by our friend Ashwarika. Acha, someone has left their bag purse here, so please come and collect. Someone has left their purse here. Please come and collect. यहाँ पे क्या नहीं? अच्छा, इसको साइड पे रख दे. हाँ हाँ. अच्छा, oh, I see. I didn't know that. Someone has left their bag here. Please come and collect. In a few minutes, we are going to have our next talk of the session. If you want to hear the talk, please stick around.
Hello, hello,
No, it's not working.
hello.
please be seated.
Yeah,
We
yes,
are
sir.
going to start the talk in 2 minutes.
Hello, hello, hello.
नए लोग आओ.
Sir?
किसको
Hello?
भगाया नहीं है किसी को? If you're here for the scientific talk, we are going to start the talk in a few minutes. Please stick around.
Hello, hello, hello.
Uh,
Hi guys. So for our next talk, we have Aishwarika Mohanty.
Oh,
She works in Department of Chemical Sciences, and she studies properties of molecules with the help of light, not the light we see around, but special type of light which comes from laser. So today she is going to talk about when light makes twins. So over to her.
Yeah, thank you, Kiran. So maybe whoever are here, if you can just come to the front or something so that it will be more interactive. If you can please come to this or this side. Thank you. So, so everybody is comfortable with Hindi, English, everything, or should I just continue with English? Hindi, English, everything, right? So, okay. So, my name is Aishwarika. I am a final year PhD student working with Professor Jyotishman Dasgupta. He's sitting behind you. And in the Department of Chemical Sciences. So, today, the title of my talk is When Light Makes Twins. So, I will just talk about some very interesting process as to how you can, you know, light creates magic in different processes. Okay, so that's how I have kept the title of my talk is When Light Makes Twins. So let's start with you know, when I talk about light, the first and foremost energy source that comes to our mind is sun, right? तो क्या होता है ना, for example, if you talk about the plants, right? So using the solar lights or something, they can basically make their own food and also generate oxygen, जो हम use करते हैं oxygen, right? But unlike the plants, so basically they use this, you know, chlorophyll molecules to use it in a process known as photosynthesis. But unlike the plants, it's a bit delayed. ओके, थैंक यू. सो अनलाइक द प्लांट्स, तो हम लोग क्या करते हैं ना, एक इंटरेस्टिंग थिंग होता है सोलर सेल्स. यू ऑल आर मस्ट बी अवेयर ऑफ दैट. तो सोलर सेल में हम क्या करते हैं कि लाइट एनर्जी लाए, सोलर एनर्जी, हम इसको इलेक्ट्रिसिटी में कन्वर्ट किए, राइट? अब क्या होता है, इफ आई टॉक अबाउट द सिंपलेस्ट मॉडल ऑफ द सोलर सेल इज द सिलिकॉन सोलर सेल, the simplest model. Okay, I don't want to go into the you know, higher models, but अगर मैं सिलिकॉन की बात करूं, just to simply describe you all, so सिलिकॉन में कुछ स्पेस होता है जो इलेक्ट्रॉन से फिल्ड होता है, ठीक? उसको हम बोलते हैं वैलेंस बैंड, and some are empty, which we call it as a conduction band. Okay, so as a few people are here, if you want to ask something, you can just directly ask. Okay. सो नाउ मैं अगर लाइट डालू उस पे, तो क्या होता है ना, जो इलेक्ट्रॉन होता है जो बैलेंस बैंड में है, इट कैन डायरेक्टली जंप इनटू द कंडक्शन बैंड, ठीक है? क्योंकि हायर एनर्जी स्टेट है, तो अब आप अगर एनर्जी दे रहे हो, देन इट कैन टेक द एनर्जी एंड जंप इनटू द हायर एनर्जी स्टेट. ओके, नाउ अगर इलेक्ट्रॉन ऊपर चला गया, इलेक्ट्रॉन इज बेसिकली अ नेगेटिवली चार्ज पार्टिकल, ठीक? अगर वो ऊपर चला गया तो नीचे क्या रह गया, अ होल. होल इज बेसिकली अ पॉजिटिवली चार्ज पार्टिकल. तो मैं अगर आपको बोल लूं मेरे पास एक नेगेटिवली चार्ज पार्टिकल है, एक पॉजिटिवली चार्ज पार्टिकल, और बात बहुत पास में है, सो देयर विल बी सम इंटरैक्शन, कूलम्बिंग इंटरैक्शन, अट्रैक्शन बेसिकली, राइट? तो वो क्या होगा, अगर पास है, सो दे विल बी बाउंड टू ईच अदर, ठीक? तो वो जो बनाएंगे एक पार्टिकल टाइप का बनाएंगे, जिसको हम बोलेंगे, साइंटिस्ट लोगों ने जो बोला है उसको एक्सीटॉन्स बोलते हैं. तो मैं अपने स्लाइड्स में बहुत बार ये टर्म यूज करूंगी, एक्सीटॉन, विच इज बेसिकली अ पॉजिटिव एंड अ नेगेटिवली चार्ज पार्टिकल बाउंड टू ईच अदर. ये थोड़ा आप याद रख लो कि एक्सीटॉन अगर मैं बोल रही हूँ, दैट मीन्स समथिंग इज पॉजिटिव, समथिंग इज नेगेटिव एंड दे आर बाउंड टू ईच अदर, ठीक? अब मैं क्या करूंगी, अगर मैं इसको एक्सट्रैक्ट कर सकती हूँ समहाउ, ओके, देन आई कैन क्रिएट द करंट और द इलेक्ट्रिसिटी. दैट एग्जैक्टली व्हाट वी डू इन द सोलर सेल. कि मेरे पास जब मान लीजिए ये सिलिकॉन लेयर है, इसमें मैं क्या जनरेट कर रही हूँ, इलेक्ट्रॉन और होल पेयर. अगर उससे मैं एक सर्किट बनाऊं तो क्या होगा कि अब इलेक्ट्रॉन्स वो मूव करेंगे, करेक्ट? and that will generate electricity. That's the basic principle of a solar cell. यहाँ तक सबको समझ में आया? ठीक है. अब क्या हुआ कि फॉर एग्जाम्पल द प्रॉब्लम इज, मैं अगर सोलर स्पेक्ट्रम देखूं मेरे पास जो है, जितना एनर्जी मेरे पास है उसका सिर्फ 33% ही है दैट इज अवेलेबल टू अस टू यूज इट इन द सोलर सेल. ठीक है, मतलब सोलर सेल में अगर 100% मानूं कि इतना मेरे पास एनर्जी है, उसमें से सिर्फ 33% ही है जो मैं सोलर सेल में यूज कर सकती हूँ, एंड अदर पार्ट्स आर गेट लॉस्ट टू डिफरेंट प्रोसेसेस. ठीक है, एंड दैट बेसिकली लीड्स टू this the efficiency has been limited to 29%. अगर मैं बहुत सारे बात करूं of different solar cells, the efficiency has been limited to 29% क्योंकि मेरे पास सिर्फ 33% ही available है. उसके साथ भी बहुत कुछ loss pathways हो सकते हैं, right? So I cannot go beyond 29%. But in my talk, I will talk about a breakthrough that scientists have, recently discovered, जिससे वो क्या करे ना, इस 29% का जो लिमिटेशन है दैट वो उन्होंने पुश किया अप टू 35% यूजिंग अ वेरी इंटरेस्टिंग प्रोसेस दैट आई विल जस्ट डिस्कस इन माय फर्दर स्लाइड्स. नाउ एज आई टोल्ड यू कि ये हमारे पास जो मैक्सिमम एफिशिएंसी वो 29% है क्योंकि हमारा अवेलेबिलिटी है 33% है. तो मैं अगर देखूं कि इफ आई हैव टू इंक्रीज द एफिशिएंसी बियॉन्ड 29% तो मेरे पास दो ऑप्शन है. पहला ऑप्शन, जो मेरा जो इनहिबिट जो लॉस पाथवे है जो 33% कर देता है लिमिटेशन उसका, क्या मैं उस लिमिट को क्रॉस कर सकती हूँ? मतलब मेरे पास जो लॉस पाथवे है, कैन आई इनहिबिट दैट टू एनहांस दिस अवेलेबिलिटी ऑफ दिस सोलर एनर्जी बियॉन्ड 33%. ठीक है, एंड नाउ द सेकंड ऑप्शन इज कि मेरे पास 33% ही है, बट विथ यूजिंग दैट मच ऑल्सो कैन आई जनरेट मोर नंबर ऑफ चार्जेस. मतलब मैंने अभी जैसे दिखाया कि कुछ अमाउंट ऑफ, मान लो लाइट डाल के आई एम जनरेटिंग अ इलेक्ट्रॉन होल पेयर, करेक्ट. बट अगर सेम अमाउंट ऑफ लाइट एनर्जी में यूज करके मान लो ट्वाइस और थ्राइस, अगर मैं 2 times और 3 times में अगर जनरेट करूं इलेक्ट्रॉन होल पेयर, दैट विल इवेंचुअली एनहांस द एफिशिएंसी ऑफ द सोलर सेल्स. इज इट करेक्ट? आर यू विथ मी? ओके. So today I will focus on this pathway where we can generate more number of charges using the same. Yeah. Yeah.
हेलो. हाँ, सो पहले केस में हम बहुत सारे एग्जिटॉन्स पे नहीं देख रहे, बस एक पर्टिकुलर पे कितना एनर्जी लॉस हो रहा है.
करेक्ट.
उसका
so फर्स्ट थिंग इज, फर्स्ट वाला जो पाथवे है उसमें क्या कर सकते हैं ना, मान लो 33% अवेलेबल है, बाकी सारा लॉस हो रहा है, तो आप उस लॉस को क्या बोलते हैं, इनहिबिट करो.
ओके.
ये करो कि ज्यादा लॉस ना हो. बट सेकंड में मेरे पास 33% है, आई एम नॉट थिंकिंग अबाउट द लॉस पाथवे, बट विद दैट 33% कैन आई जनरेट मोर नंबर ऑफ चार्जेस. दैट इज द बेसिक आइडिया. ठीक है, तो उसके साथ हम क्या करेंगे, तो मैंने क्या बोला कि फॉर एग्जांपल मेरे पास जो पहले था अमाउंट ऑफ एनर्जी सिलिकॉन लेयर में हम डाल के हम क्या कर रहे थे, वी आर जनरेटिंग सम एक्सीटॉन. ठीक है, but with the same amount of energy, if I can generate more number of excitons, basically electron hole pairs, then that can enhance the solar cell efficiency. ठीक है, so that's why the goal is to multiple exciton generation with single photon as in the packet of energy, and there is a process known as singlet fission with which we can actually achieve that. So fission is basically कुछ टूटना, right? मतलब कुछ टूट के कुछ multiple exciton generate हो सकते हैं. ठीक है, so that is the process which is known as singlet fission. I will discuss this process in my further slides. But now, before that, just let me tell you that these are some of the complicated molecules that basically show this singlet fission. These are made up of carbon, nitrogen, hydrogen, oxygen, all of these atoms. Okay. Now, before going to the singlet fission, for everyone's sake, let's first understand the basics as to what happens जब मैं लाइट डालती हूँ इस टाइप के मॉलिक्यूल पे. ठीक है, अब नाउ मैंने क्या बोला था, सिलिकॉन लेयर में कुछ स्पेस होता है जिसमें इलेक्ट्रॉन भरे हुए होते हैं, कुछ होता है खाली. ठीक है, सिमिलरली इन दीज टाइप ऑफ मॉलिक्यूल्स आल्सो देयर आर सम स्पेस व्हिच इज फिल्ड विथ इलेक्ट्रॉन एंड सम आर एम्प्टी. ठीक है, बट नाउ द थिंग इज इन द मॉलिक्यूल्स, नाउ द स्पेस इज कन्फाइंड टू अ स्टेयर लाइक थिंग, मतलब सीढ़ी जैसे होता है. ठीक है, अब जो लोएस्ट स्टेयर होता है दैट इज ऑफ लोअर एनर्जी, एंड एज यू गो अपवर्ड्स उसका एनर्जी बढ़ता जाता है. ठीक है, नाउ द इलेक्ट्रॉन्स दैट द मॉलिक्यूल्स हैव, इलेक्ट्रॉन को ना अच्छा लगता है लोअर एनर्जी स्टेट में रहने के लिए. as long as you are not putting any energy or any light energy, it will not go to the higher excited state. वो ग्राउंड स्टेट में ही, ग्राउंड स्टेयर में ही रहना चाहेगा, ठीक है। एंड अनदर रूल इज, दो जो इलेक्ट्रॉन होंगे, इलेक्ट्रॉन है पर स्टेयर आप दो ही डाल सकते हो इलेक्ट्रॉन्स, ठीक है। नाउ इलेक्ट्रॉन्स आर नेगेटिवली चार्ज पार्टिकल, राइट, ठीक। अब वो स्पिन भी कर रहा होता है। अब अगर मेरे पास कोई चार्ज पार्टिकल है जो स्पिन करता है, दैट कैन बेसिकली क्रिएट मैग्नेटिक फील्ड, ठीक है। बट दैट मीन्स नाउ I can consider the electrons as a tiny magnet, ठीक है। मैंने क्या बोला, पर स्टेयर मेरे पास दो इलेक्ट्रॉन्स है एंड each electron I can consider as a tiny magnet, okay। सब लोग बैठ जाए, फिर then I'll just what? So okay, as new people joined, I'll just tell you that what I'm saying is, for example, I am from a chemistry background. So what I'm saying here is, if I'm putting a light onto an organic molecule, for example, these type of molecules which are made up of carbon, hydrogen, nitrogen, and oxygen, how do they behave? And how can I increase the solar cell efficiency that has been reported up to 29%, okay। तो बेसिकली मैं बता देती हूँ, जो लोग नए आए हैं, तो मैं आपको दिखाऊंगी कि सोलर सेल, जो हम सिलिकॉन सोलर सेल जनरली यूज करते हैं, जिसका एफिशिएंसी 29% तक लिमिटेड था, उसको हम कैसे एनहांस कर सकते हैं बियॉन्ड दैट 29%, ठीक है। दैट इज द बेसिक गोल दैट आई एम जस्ट प्रेजेंटिंग ओवर हियर। नाउ जस्ट टू टेल यू दैट दीज आर सम ऑफ द मॉलिक्यूल्स which contains electrons, and electrons are basically charged particles जो घूमते रहते हैं, spin करते रहते हैं, and they can be considered as tiny magnets, ठीक है। Now if I have to put two magnets close to each other, उसका मतलब क्या होगा कि मेरे पास अगर मान लो दो magnets है, तो मैं अगर दोनों को एक साथ रखना चाहूँ तो मुझे क्या करना पड़ेगा, इसका नॉर्थ पोल इसका साउथ पोल के साथ रखना पड़ेगा, करेक्ट, नॉट नॉर्थ पोल टू नॉर्थ पोल, बिकॉज फिर रिपल्शन होगा। If I have to put together, then I have to bring now north pole towards the south pole, ठीक है। Similarly, if I have to put two electrons close to each other, तो दो स्पिन को अलग करना पड़ेगा। ये अगर अप है तो दूसरे को डाउन में रखना पड़ेगा, so that they will be stabilized together, ठीक है। Now just to give you all an information that this is just a terminology, that if both the electron spin are opposite, we call it as singlet. If they are parallel, okay, then we call it as a triplet. Just remember that. Now, for example, let's say I have this molecule which is in the singlet state. Why singlet? Because if you look at the electron spin, they are both anti-parallel, opposite. That is why we are calling it a singlet state. ठीक है। अब मैं अगर लाइट डालूं, ये जो इलेक्ट्रॉन है अभी लोअर वाले एनर्जी स्टेट पे है, मैं अगर लाइट डालूं तो वो क्या होगा, हायर एनर्जी स्टेट पे जा सकता है, correct, because I am putting some energy, right? So now what happens is the electron can just jump to the higher energy state, मतलब higher stair पे जा सकता है। Now ऊपर जो होगा, ऊपर स्टेयर पे वो या तो अप स्पिन रह सकता है या तो डाउन स्पिन रह सकता है, उसकी मर्जी, भाई हम थोड़ी कुछ बोल सकते हैं, ठीक। तो अगर वो डाउन स्पिन हुआ तो टोटल ये क्या हुआ स्पिन का, एंटी पैरेलल, तो इसलिए हम उसको सिंगलेट बोल रहे हैं। अगर दोनों पैरेलल हुए तो उसको हम ट्रिपलेट बोल रहे हैं। बट नाउ द इंटरेस्टिंग थिंग इज, अगर मान लो जैसे मैंने सिलिकॉन के केस में बोला था, अगर मेरे पास एक इलेक्ट्रॉन जो जंप कर गए ऊपर स्टेट में, इलेक्ट्रॉन क्या है, नेगेटिवली चार्ज पार्टिकल, राइट, अगर वो ऊपर के हायर एनर्जी स्टेट पे चला गया तो नीचे क्या रह जाएगा, पॉजिटिव, ठीक। अब मेरे पास एक पॉजिटिव चार्ज है, एक नेगेटिव चार्ज है, एंड दे आर बाउंड टू ईच अदर, तो वो क्या होगा, एक एक्सीटॉन टाइप का फॉर्म करेगा। सो हुएवर केम लेटर, अगर मेरे पास एक पॉजिटिव और नेगेटिव चार्ज पार्टिकल है जो बाउंड टुगेदर, बाउंड, इफ दे आर बाउंड टुगेदर, देन आई कैन कॉल इट एज एक्सीटॉन्स, ठीक है। सो दैट मीन्स इफ आई कैन सेपरेट दीज टू चार्ज पार्टिकल्स, आई कैन यूज इट इन सोलर सेल्स, बिकॉज फिर मुझे करंट मिल सकता है, इलेक्ट्रॉन मूव करेगा अगर सर्किट में तो फिर मुझे करंट मिल सकता है, एंड आई कैन यूज दिस टाइप ऑफ मटेरियल्स इन द सोलर सेल, ठीक है। नाउ द थिंग इज, लेट्स से हाउ can I enhance the solar cell efficiency? For example, let's say initially I have these molecules in the ground state, बहुत ही सबसे lowest energy state में है, and I am putting energy, light energy, ठीक है। तो वो क्या करेगा ना, एक फोटोन अगर एक पैकेट ऑफ मैं डाल दूं लाइट, इट कैन ओनली एक्साइट, मतलब एक ही मॉलिक्यूल को वो हायर एनर्जी स्टेट में ले सकता है। सिर्फ एक फोटोन में अगर डालूं तो एक ही वन ऑफ द मॉलिक्यूल्स विल गेट एक्साइटेड टू द हायर एनर्जी स्टेट, ओके, एंड द अदर वन विल स्टिल बी इन द ग्राउंड स्टेट बिकॉज यू हैव पुट ओनली वन फोटोन, ठीक है। बट नाउ द थिंग इज, इफ देयर इज अ स्ट्रॉन्ग, आई मीन देयर इन क्लोज प्रॉक्सिमिटी, अगर बहुत आसपास है, तो मेरे पास जो एनर्जी है जितना S1 में जो है, अगर वो शेयर कर सकता है विद S0, ठीक है, क्योंकि उतना क्लोज प्रॉक्सिमिटी में, राइट। आप लोगों के दोस्त होंगे ना, अगर मान लो इफ यू हैव सम चॉकलेट्स और समथिंग, you can just share with your best friends, right? If they are in close proximity in the molecules, they can also share their energy. तो अगर वो शेयर किए तो एक बनाते हैं TT pair intermediate. You don't have to go into the details. It's just that it is sort of a single product. But आप अगर individual देखोगे, spins are parallel, right? Individual. This one individual, this one individual. Individually they are triplets, क्योंकि parallel है. But अगर overall देखोगे तो टोटल स्पिन इज 0, और वो इतने क्लोजली पैक्ड है ना, इतने स्ट्रांगली कनेक्टेड है, मतलब यू विल कंसिडर दैट एज अ सिंगल सिस्टम, ठीक है। बट विथ टाइम, जैसे मान लो आपके कोई बेस्ट फ्रेंड्स हैं, आप बहुत क्लोजली कनेक्टेड हो, बट एज यू, मतलब स्कूल जब खत्म होता है या यू गो टू कॉलेज और हायर स्टडीज, ऑब्वियसली आप सेपरेट हो ही जाते हो ना, कोई और कहीं गया कहीं गया। सिमिलरली विथ टाइम these things all will also get separated and form individual triplets, okay. And as I told you, each triplet you can consider as an exciton. Exciton means positive and negative which are particle close to each other, bound to each other, okay. That means in this process, very interestingly, we can generate 2 excitons by putting 1 photon, which is not the regular thing. Regularly what happens, you put 1 photon and you generate 1 exciton, but here you can generate 2 excitons per photon, ठीक है। Now, and just to give you a glimpse of this intermediate, so initially क्या होता है, बहुत closely packed होता है, these are like these twins who are very so in love and very closely packed, okay, and then with time it decays, or the interaction becomes weaker and weaker. These are like these twins, although they are twins, and so, but they are not so in love, okay. And the last part is, with time, if we give them much time, then you can just completely dissociate to form 2 independent triplets, okay. And like these twins, believe me, they are twins, but it is like that they don't look alike, ठीक है। So that means बहुत ही अलग अलग twins है, similarly आपको बहुत अलग अलग ऐसे ट्रिपलेट अलग से मिलेंगे, ठीक है। नाउ अभी मैं क्या कर सकती हूँ, क्या करती हूँ लैब में, मैं बस बता देती हूँ। सो दिस इज अ ग्रुप इन TFR। तो हम जनरली क्या करते हैं, हम ऐसे बहुत इंटरेस्टिंग लेजर लाइट्स यूज करते हैं, और वी लुक एट दिस मॉलिक्यूल्स, कि हम जब लाइट डालते हैं क्या होता है, क्या इंटरेस्टिंग प्रॉपर्टीज दिख सकते हैं, और उसको हम कैसे यूज कर सकते हैं आगे। वी बेसिकली डू दैट, ठीक है। नाउ द सिंगलेट फिशन प्रोसेस दैट आई जस्ट टॉक्ड अबाउट, वो ना इतने फास्ट टाइम स्केल में होता है, 10⁻15 to 10⁻12 ऑफ अ सेकेंड, मतलब बहुत फास्ट। तो ऐसे आप जैसे बैठे हो, मैं ऐसे मॉलिक्यूल्स को देख नहीं सकती बिकॉज द टाइम स्केल इज वेरी फास्ट। तो मेरे पास, मुझे क्या चाहिए, मेरे को आप ऐसे कैमरा दो जिसका शटर और फ्लैश इतना फास्ट हो, आई कैन टेक पिक्चर्स ऑफ दिस मॉलिक्यूल्स इन दीज टाइम स्केल्स। समझ आया कि अगर मेरे पास कोई बहुत फास्ट प्रोसेस चल रहा है, तो मैं क्या करूंगी, मेरे को ऐसे कैमरा चाहिए जो उतने फास्ट टाइम स्केल में आपको पिक्चर्स बना के दे, और आप देख सकते हो कि भाई मॉलिक्यूल क्या डांस कर रहा है, क्या कर रहा है, सब आप देख सकते हो, ठीक है। तो इसीलिए हम क्या करते हैं, इस ऐसे क्यूवेट टाइप का हम कंटेनर लेते हैं, उसमें मॉलिक्यूल डालते हैं, फिर हम लाइट डालते हैं और उसके पिक्चर्स लेते हैं, और जब TT पेयर इंटरमीडिएट जो मैंने आपको बताया, तो फिर हम देख सकते हैं कि कैसे बना, क्या हम उसको डिसोशिएट कर सकते हैं, क्या कितने टाइम स्केल में बना। क्योंकि अगर आपको इसको लेके सोलर सेल में डालना है लेयर को, तो आपको क्या पता होना चाहिए कि कितने टाइम स्केल में ये सब बन रहा है, बिकॉज यू हैव टू एनहांस द एफिशिएंसी, राइट। अगर कुछ चीज को प्रैक्टिकल एप्लीकेशन में डालना है, यू हैव टू डू द फंडामेंटल स्टडीज फर्स्ट, एंड दैट्स व्हाट आई डू इन माय प्रोजेक्ट, PhD प्रोजेक्ट बेसिकली। नाउ आप बोल सकते कि भाई इतना कुछ तो बोल दिया, कुछ हुआ भी है नहीं, कि प्रैक्टिकल बस बोले जा रहे हो तब से, ठीक है। So the thing is, recently people have actually tried to incorporate these type of molecules in सिलिकॉन सोलर सेल। तो उन्होंने क्या किया, जनरल जो सिलिकॉन लेयर होता है, सिलिकॉन सोलर सेल, ऐसे एक जंक्शन होता है जिसमें पॉजिटिव और नेगेटिव चार्ज जनरेट हुआ, देन यू मेक अ सर्किट, फिर इलेक्ट्रॉन मूव किया और आपको करंट मिला। ठीक है, अब जस्ट 2 मिनट्स। तो अभी इसमें क्या करेंगे ना, हम एक टेट्रासिन का लेयर ले लें। टेट्रासिन इज बेसिकली अनदर सिंगलेट फिशन मटेरियल जो हमें 2 एक्सीटॉन्स पर फोटोन दे सकता है। तो उसमें क्या करेंगे ना, जब लाइट डाला उन लोगों ने देखा सिलिकॉन लेयर में तो जैसे बनना चाहिए इलेक्ट्रॉन होल वो बन रहा है, बट इन द टेट्रासिन लेयर ट्वाइस द अमाउंट में जनरेट कर रहा है इलेक्ट्रॉन होल पेयर। जैसे मैंने बताया कि एक फोटोन डाला और ट्वाइस द amount of electron hole pair generate हो रहा है। ठीक है, with that they could actually enhance the efficiency from 29 to around 35%, which was not before. ठीक है, now just to tell you all that there are still, this is an emerging field, so there are so many challenges also. तो पहला चैलेंज होगा कि मेरे को एफिशिएंटली वो जो टीटी पेयर मैंने आपको दिखाया बहुत स्ट्रांगली कपल्ड है, उसको आपको तोड़ना है, अच्छे से तोड़ना है कि 2 आपको बने एक्सीटॉन्स। ठीक है, और दूसरा चैलेंज ये होगा कि अगर मैंने बना लिया तो वो सिलिकॉन लेयर में इंजेक्ट करूंगी तभी मुझे ज्यादा अमाउंट ऑफ इलेक्ट्रॉन होल पेयर जनरेट होंगे। ठीक है, दैट इज द बेसिक प्रिंसिपल। So yeah, so with that, just to conclude that I had shown you this very interesting process which is known as singlet fission, where you can generate twice the amount, 2 times excitons, and you can basically use that in the solar cells. So with that, let me just thank some few people, just Ullas and NSC organizing committee for giving me this opportunity. My guide, Professor Jyotishman Dasgupta, who is here for all his inputs, and Tia from Mumbai, and everyone for listening. Thank you.
Very interesting talk, Swarika. We can take a couple of questions. We don't have time for much, so raise your hands quickly.
So you mentioned that a triplet pair is formed when it's excited, but isn't it a random process? It can also be a singlet pair that is formed.
Absolutely. So that's why the molecules that can show singlet fission are very, not every molecule can show singlet fission. There are certain criteria which the molecule should fulfill so that you will not generate the singlet, but rather than but the triplet,
Okay.
TT pair intermediate. Yeah.
And one more question, like you're using organic molecules and you're exciting the electrons, but all the electron pairs are bonded, so doesn't that
So
also
the
mean
electron-
that the bond will break some?
Oh, so the thing is, I am not exciting the electron, I am exciting the molecule. Okay. I'm not pulling out the electron out of the molecule. It is still there. So within, you can think of it like when you're putting the light, you're basically rearranging the electron distribution within the molecule. We are not pulling it out, the electron.
Generally, for a solar cell, like you consider the sunlight to have 1000 watt per square meter of total energy, and we say that we are using, say, in commercial cells we are using 20%, so we get 200 watts. Now, giving that energy input, you are saying you are increasing the efficiency to 35%, that is 350 watts. That is the, what to say, how do you account for creation of new energy? So that there should be some chemical change in your.
Yeah, so if you think about the conventional way, you cannot go beyond 100%, for example, in any process. That is why this is an interesting process where you can go beyond 100%, because within the same amount of energy, you're basically generating 2 species, but of lower energy.
The output, especially output should be totally lower.
No. So the thing is, the exciton, for example, I'm generating an exciton. I have to inject that into the silicon layer. The energy is fixed. So I have to generate this lower energy state from a higher energy.
Once it excites the silicon layer, is that molecule again available for excitation?
Yeah, of course. So once everything is done, so it can go back, it can come back to the ground state, and then you can just do that.
The conservation of energy.
Okay, so there is a confusion maybe. So the thing is, I am putting this only a definite amount of energy. I am generating two species maybe, but if you sum the energy is same.
Taking 33% of the energy of light.
Okay.
They're generating 35% energy. So that extra 2%, either should come from chemical energy, or we are miscalculating how much energy.
Okay. The 33% is the availability. I'm not saying I'm putting 33, I'm getting 35.
We are using only the available. They're not
Yes.
using more.
Yes. Yes.
Yet we are getting
Yes, but for example, different solar cell material, the availability will also be different, right? The band gap is different.
Ashwarika.
Yeah.
I think
Yeah, sorry.
Yeah,
sorry.
so. Yeah, we'll start the next talk. Let's thank Ashwarika.
Okay. So now the next speaker is Mr. Rudra Dhara. He is a PhD student in the Department of Condensed Matter Physics. So now he will take you all to the fascinating world of this quantum materials. So these are some of the very interesting materials which can show very exotic behavior, for example, superconductivity, or you can use that in quantum computing, right? So with that, let's welcome Rudra.
Hello everyone, my name is Rudra and I work on quantum materials. So today I'll give a small description about what it is. So
Rudra,
yes.
Everyone please try to maintain silence as much as possible, because everyone is trying to listen and understand. I request everyone to maintain silence as much as possible so that everyone can listen what they're interested in. Please continue.
Okay. Yeah.
मैं स्टॉप करके फिर से शेयर कर रहा हूँ, ठीक है?
Okay.
आपने वो कुछ दबा दिया था.
Okay. Okay. ठीक है. So again, I'll talk about quantum materials, and my name is Rudra Dhara. So this is our group. So this is a group in TIFR and we work on quantum materials. So start about material. तो material क्या है? Material drives civilization. तो हम कोई भी civilization आप देखेंगे, material plays a very important role. For example, Stone Age. तो उधर हमने stone tools को use करना सीख लिया. Similarly, if you look at Bronze Age in modern, हम progress कर रहे हैं और हमने metals कैसे use करना है, उसका क्या property है, उसको हमने सीख लिया. But now we live in a modern age. तो उधर क्या है? We know all of the different kind of materials. We know how to mix them. We know every property of each material. So this is very important. So we can understand that material is very important. अगर हम हमारे आसपास कोई भी ऑब्जेक्ट देखे, those are made of materials. और हम उसको फंक्शनल कैसे बनाते हैं? हम उसको कोई भी मटेरियल को फंक्शनल बनाते हैं बिकॉज वी नो कि एक मटेरियल का प्रॉपर्टी क्या है. तो वो जानने के वजह से ही हम जो मॉडर्न प्रोग्रेस है, मॉडर्न सिविलाइजेशन है, उसको वो पॉसिबल. तो सिमिलरली इफ वी लुक एट आवर फ्यूचर, कि फ्यूचर में मे बी वी वांट टू कॉलोनाइज मार्स और मून, और maybe in very far future we want to harvest the total energy of sun, so we can make this kind of a Dyson sphere. इसको Dyson sphere बोलते हैं कि एक पूरा sun को ऐसा एक structure से cover कर लिया, and then we will harvest all its energy. So if we want to make this kind of structures or make any kind of progress, we want to make this out of material, और वो material काफी advance होना चाहिए. So one of the prospect of the material is quantum materials, कि जो नेक्स्ट जनरेशन जो मटेरियल होगा उसका हम क्वांटम जो प्रॉपर्टी है उसको हम रियल लाइफ में लाएंगे. सो what are quantum materials? So quantum materials are those materials which shows quantum properties. So quantum property, as you know, it in atomic scale में जो physics govern करता है, that is quantum mechanics. पर उसको हम real life में जब लाना है, the material scale has to be very big. पर large object में हमें मालूम है कि mostly it governs by classical mechanics. But quantum materials are those materials which shows the quantum properties even in classical scale. So these are very exceptional material और उसका काफी सारा applications है. So for example, if you see in modern days also the James Webb Space Telescope और उसके अंदर जो detector है, the camera, this is the infrared camera, and if you look into the structure, so these are artificially made quantum wells. तो इसको layer by layer deposition करके ऐसा quantum well बना है. Similarly, if you see the green LED, like a very high efficient green LED, उसके अंदर भी ऐसा quantum well जैसा structure होगा. So these are all one of the example of quantum materials. Similarly, if you want to detect single photons, you can use some structure. These are called superconducting meanders or a single photon detector के तक काम करता है. Similarly, there are very sensitive magnetic sensors जैसा SQUID है, और these are most precise magnetic sensors available to us. Similarly, if you want to make very robust quantum computing, हमें काफी एडवांस सुपरकंडक्टर चाहिए. सम ऑफ देम कुड बी टोपोलॉजिकल सुपरकंडक्टर जो एक्सटर्नल नॉइस है उससे वो ज्यादा इफेक्ट ना हो. तो दिस इज द वर्ल्ड ऑफ क्वांटम मटेरियल्स. तो फर्स्ट हमें क्वांटम मटेरियल को समझना है, तो फिर फर्स्ट वी नीड टू अंडरस्टैंड द स्केल ऑफ क्वांटम. कितना छोटा स्केल में क्वांटम मैकेनिक्स काम करते हैं. तो फॉर एग्जाम्पल ये एक मीटर स्केल है. वी ऑल नो आवर मीटर स्केल, और इसका जो स्मॉलेस्ट यूनिट है दैट इज ए मिलीमीटर. तो मिलीमीटर को अगर हम 1000 से डिवाइड करते हैं, दैट बिकम्स ए माइक्रोन. और एक माइक्रोन का जो मतलब स्केल है, दैट यू कैन इमेजिन कि जो स्पाइडर वेब है उसका जो एक थ्रेड है दैट इज अराउंड 1 माइक्रोन. अगर उससे भी छोटा आपको थिकनेस देखना है, दैट कुड बी ए लाइट बबल, बिकॉज जो लाइट बबल में आपको एक कलर दिख रहा है, वो कलर क्यों दिखता है मालूम है? बिकॉज जो विजिबल लाइट है उसका वेवलेंथ का थिकनेस के सेम है, और उसके लिए लाइट का एक इंटरफेरेंस उसका वॉल का थिकनेस के साथ होता है. दैट्स व्हाई वी सी डिफरेंट काइंड ऑफ लाइट. सो दैट्स व्हाई द सोप बबल का जो वॉल का थिकनेस है वो अराउंड जो लाइट का वेवलेंथ है वो उसके सिमिलर है. बट इफ यू वांट टू लुक एट इवन स्मॉलर ऑब्जेक्ट्स, तो उसका जो उससे स्मॉलर ऑब्जेक्ट डे टू डे लाइफ में हम इमेजिन नहीं कर सकते, बट और नेकेड आई से देख भी नहीं सकते. उसको देखने के लिए वी नीड टू यूज सम एक एडवांस माइक्रोस्कोप कॉल्ड इलेक्ट्रॉन माइक्रोस्कोपी. जो ये जो इमेज है दैट इज एन इलेक्ट्रॉन माइक्रोस्कोपिक इमेज, और इसमें एक डिफरेंट एटम्स का आपको लेयर दिख रहा है. एंड दिस इज ए आर्टिफिशियली ग्रोन क्वांटम वेल लाइक स्ट्रक्चर, और इसका जो इंडिविजुअल लाइन है वो एक एटम है. तो ये एटॉमिकली लाइन डिपोजिशन से हमने बनाया है, एंड दिस थिकनेस इज अराउंड लेस देन 1 नैनोमीटर. तो ये जो सोप बबल है उससे 1000 टाइम्स स्मॉलर. तो दिस इज द स्केल वेयर क्वांटम मैकेनिक्स वर्क. क्वांटम मैकेनिक्स यूजुअली वर्क्स इनसाइड एटम. उससे अगर लार्ज में जाएंगे तो यूजुअली नहीं मिलता है. बट ओके, सो देयर आर नाउ हियर द क्वांटम मैकेनिक्स कम्स. जो क्वांटम मटेरियल्स है they are made of definitely atoms, but उसका जो एटॉमिक फिजिक्स है और एटॉमिक स्केल का जो फिजिक्स है वो लार्ज स्केल में भी दिखता है. सो देयर आर डिफरेंट, फॉर एग्जांपल सुपरकंडक्टर जिधर इलेक्ट्रॉन पेयर होता है थ्रू इट्स फोनॉन, तो जो लैटिस का वाइब्रेशन है उसके साथ एक कपलिंग होता है. ये लोकल स्केल में है, पर ये जो फेनोमेना है जो कपलिंग, ये ग्लोबल स्केल में आपको दिखता है. सो सुपरकंडक्टर कैन बी वेरी लार्ज, और पूरा जो बल्क है उसमें सुपरकंडक्टिविटी आपको दिख सकता है. तो सिमिलरली देयर आर डिफरेंट काइंड ऑफ क्वांटम मटेरियल्स नाउ व्हिच शोज दिस काइंड ऑफ क्वांटम इफेक्ट्स इन लार्ज स्केल. सो लेट्स कम टू द फर्स्ट क्वांटम मटेरियल. तो वी ऑल नो एटम्स. तो एटम का जो ऐसा क्वांटाइज्ड एनर्जी लेवल्स है, एंड बट दिस इज अ मटेरियल व्हिच इज more than a millimeter. So this scale bar is 1 millimeter. तो ये जो पूरा हॉल बार है, this particular device geometry is called हॉल बार. तो ये हॉल बार का जो लेंथ है अराउंड 1 सेंटीमीटर होगा. दैट इज अ लार्ज ऑब्जेक्ट, क्लासिकल ऑब्जेक्ट. पर अगर हम उसमें मैग्नेटिक फील्ड डालते हैं, वी फाउंड दैट उसमें एक क्वांटाइजेशन होता है, जो एनर्जी लेवल क्वांटाइज होता है, एंड दैट क्वांटाइजेशन इज क्वाइट सिमिलर टू द एटॉमिक स्केल क्वांटाइजेशन. तो दैट इज वन ऑफ द फर्स्ट एग्जांपल वेयर वी सॉ कि जो एटॉमिक स्केल का क्वांटाइजेशन है वो एक लार्ज ऑब्जेक्ट में भी ये वाला क्वांटाइजेशन का इफेक्ट दिख सकता है, और उसका इफेक्ट हम ये जो रेजिस्टेंस है, एक पर्टिकुलर रेजिस्टेंस, उसमें आप ऐसा स्टेप्स दिखते हैं। और इसके वजह से क्लिजिक को 1985 के नोबेल भी मिला है। And this kind of quantum Hall can be seen in this kind of artificial structure. So these are also a type of quantum Hall. और ये वाला स्ट्रक्चर अगर हम बना सकते हैं लार्ज स्केल में, तो लार्ज स्केल एंटिटी एक क्वांटम प्रॉपर्टी दिखाते हैं। तो दिस क्वांटम प्रॉपर्टी इज नोन एज क्वांटम हॉल इफेक्ट। So similarly, so we work on engineered quantum material. For example, if you want particular property out of a material, कि एक कोई material memory हो सकता है, कोई material में भी you want some rectification, electrical rectification चाहिए, कोई भी आप property imagine करो कि हमें ये वाला property चाहिए कोई material से, and we want to design them that material from the scratch. So for do that we use this kind of heterostructure. तो क्या है, we deposit atoms layer by layer, और हमें इंडिविजुअल लेयर का प्रॉपर्टी में भी मालूम है, पर वो एक साथ जब ऐसा लेयर बाय लेयर डिपोजिशन करेंगे वो कैसे इंटरेक्ट करते हैं, दैट विल गिव यू अ न्यू इमर्जेंट प्रॉपर्टी। और ये डिफरेंट टाइप ऑफ हेटेरोस्ट्रक्चर हम मतलब डिफाइन करके हम उसका प्रॉपर्टी ट्यून कर सकते हैं। सो मे बी विल बी क्यूरियस कि हाउ वी कैन मेक दिस काइंड ऑफ आर्टिफिशियल स्ट्रक्चर। तो यूजुअली अगर आप मतलब नेचर में लैंथेना, मैंगनीज और ऑक्साइड और स्ट्रोंशियम एक साथ डाल दो और उसको वार्म हीट कर दो, मेल्ट कर दो एंड कूल इट डाउन, यू गेट ए क्रिस्टल, बट ऐसा क्रिस्टल आपको कभी भी नहीं मिलेगा। सो दिस यू कैन नॉट फाउंड इन नेचर, इसको आपको आर्टिफिशियली बिल्ड करना पड़ेगा। और टू बिल्ड दैट वी डू ए प्रोसेस इज सिमिलर टू स्प्रे पेंटिंग। हमारे पास एक फॉर एग्जाम्पल एटॉमिक स्प्रे कैनिस्टर है और उसमें हम स्प्रे कर रहे हैं, इंडिविजुअल एटम को हम स्प्रे कर रहे हैं लेयर बाय लेयर। पर नॉर्मल जो स्प्रे कैन है वो इंडिविजुअल मॉलिक्यूल स्प्रे नहीं करते, वो उसका जो थिकनेस है माइक्रोन होता है, तो अराउंड 1 लाख और 10 लाख टाइम्स लार्जर देन एटम। तो एक स्प्रे में ही आपका काफी एटॉमिक थिक वॉल ग्रो हो जाएगा। सो इफ यू वांट दिस एटॉमिक कंट्रोल in this kind of layer by layer growth, you want to have this kind of a system. This is called molecular beam epitaxy. So this is a system that we have in TIFR in our lab. और इसमें क्या करते हैं, we deposit create this kind of molecular और atomic beam. तो इधर individual elemental cell है, इधर जो cell है तो यही इसका schematic diagram है। तो और उसका जो individual atomic beam है वो इधर substrate में hit करता है। तो जो सबस्ट्रेट कैन बी एनी मटेरियल, वो जस्ट उसको जो थिन फिल्म हम ग्रो कर रहे हैं उसको सपोर्ट करने के लिए है। तो हम इधर ये जो इधर हम इसको रख देते हैं और उसको इंडिविजुअल जो सेल्स है उसको स्प्रे करते हैं। और इधर हमारे पास शटर है, तो उसको जब हम क्लोज करते हैं तो ये मॉलिक्यूलर बीम ऑफ हो जाएगा। तो मॉलिक्यूलर बीम पाने के लिए देयर इज ए इंपॉर्टेंट प्रोसेस, सो दैट इज कॉल्ड एफ्यूजन। तो क्या करते हैं, हम जो इंडिविजुअल एलिमेंट है उसको हम हीट करते हैं। फॉर एग्जांपल वी ऑल नो कि वाटर को अगर हम हीट करते हैं तो वाटर मॉलिक्यूल ऐसे इवापोरेट होता है, तो दिस इज वाटर गैस। सिमिलरली वी हीट अप मेटल्स, और मेटल क्या होता है, मतलब इवापोरेट होता है, आइदर उसका सब्लिमेशन हो सकता है सॉलिड टू गैस, और वो मेल्ट हो सकता है फर्स्ट एंड उसके बाद वो इवापोरेट हो सकता है। बट ये मेटल इवापोरेशन इज वेरी रेयर, हम डे टू डे लाइफ में नहीं देखते। एंड दैट उसके लिए और एक क्रिटिकल चीज है, दैट इज दिस प्रेशर। सो दिस इज 10⁻11 टॉर और मिलीबार काइंड ऑफ ए प्रेशर। तो जो एटमॉस्फेरिक प्रेशर से काफी कम प्रेशर, सो दैट इज वेरी लो प्रेशर। और ये वाला लो प्रेशर इज वेरी क्रिटिकल टू गेट जो मॉलिक्यूलर बीम, ये जो मॉलिक्यूलर बीम है ये पूरा स्ट्रेट आपका सबस्ट्रेट में जाएगा, इसका बीच में कोई भी इंटरेक्शन को नहीं होगा। तो उसको अंडरस्टैंडिंग करने के लिए कि मॉलिक्यूलर बीम कैसे क्रिएट करते हैं, सपोज यू हैव ए एलिमेंट कॉल्ड गैलियम, कोई भी एलिमेंट हो सकता है, प्लैटिनम, कोई भी मेटल हो सकता है, गोल्ड और मे बी एल्यूमिनियम, कुछ भी, पर आपको इंडिविजुअली उसको इवापोरेट करना है। तो आई थिंक देयर वाज अ वीडियो। ओके, सो फॉर एग्जांपल आप ऐसा गैलियम इवापोरेट करना चाहते हो बट इन एटमॉस्फेयर। तो एटमॉस्फेयर में क्या है कि ये सारे गैसेस है, और ये गैसेस के वजह से इसका पाथ हिंडर हो जाएगा। सो यू विल नेवर गेट दिस काइंड ऑफ प्रिसाइज एटॉमिक बीम। आपको अगर एटॉमिक स्केल में कंट्रोल चाहिए यू कैन नॉट गेट। और इसका जो मीन फ्री पाथ है, मीन फ्री पाथ मीन्स जो गैलियम सेल से निकल के जब कॉलिशन होगा दैट इज अराउंड 70 नैनोमीटर। तो 70 नैनोमीटर इज ए वेरी स्मॉल नंबर, हमारा जो हेयर है उससे भी 1000 टाइम्स स्मॉलर, तो वो वाला थिकनेस में कॉलिशन हो जाएगा। तो विल नेवर गेट दिस काइंड ऑफ मॉलिक्यूलर बीम, इतना जो लार्ज मशीन है उतना लार्ज पाथ में, तो उसको पाने के लिए वी नीड टू वैक्यूम। तो वैक्यूम का जब हम वर्ड यूज करते हैं, द फर्स्ट थिंग कम्स टू माइंड इज वैक्यूम क्लीनर, पर वैक्यूम क्लीनर इज नॉट गुड एनफ एट ऑल। तो हमारा जो अर्थ का अभी प्रेशर है, अभी हमारा जो हमारे आसपास जो एटमॉस्फेरिक प्रेशर है दैट इज अराउंड 1000 मिलीबार, तो उससे अगर हम वैक्यूम क्लीनर उधर लगा दे वी गेट टू 600 मिलीबार, तो अराउंड हाफ हो गया प्रेशर। पर हम उससे भी कम प्रेशर चाहते हैं, तो यू कैन डू वन थिंग, यू कैन गो टू इंटरनेशनल स्पेस स्टेशन हाइट, तो उधर जो एटमॉस्फेरिक प्रेशर है वो काफी कम हो जाता है। सो दैट इज अराउंड 10⁻⁻7 मिलीबार, तो 100 करोड़ टाइम्स कम हो गया जो प्रेशर है। पर उससे भी अगर आपको बेटर प्रेशर चाहिए then you can go to moon surface, तो moon surface में we know there is almost no atmosphere, तो उसके लिए उसके वजह से उसका जो प्रेशर है ऑलमोस्ट नहीं, मतलब काफी कम है, सो दैट इज अराउंड 10⁻⁹ मिलीबार। और उससे भी कम अगर प्रेशर चाहिए, you don't need to go far, you can come to our lab, quantum material lab, and inside our chamber the pressure is 10⁻11 millibar। तो ये जो प्रेशर है दैट इज वेरी इंपॉर्टेंट, क्योंकि इधर जो फ्री मीन पाथ है, जो एक गैलियम इधर से निकल के जो नेक्स्ट कॉलिशन होगा दैट बिकम्स वेरी लार्ज, तो उसका जो डिस्टेंस है अराउंड 1 लाख किलोमीटर। तो 1 लाख किलोमीटर इतना जो वैक्यूम अगर कर पाएंगे तो 1 लाख किलोमीटर तक एक मॉलिक्यूल के साथ और एक मॉलिक्यूल का कॉलिशन नहीं होगा। सो और उसके वजह से और एक एडवांटेज है कि कोई एक्स्ट्रा इम्प्योरिटी भी नहीं आएगा, कि फॉर एग्जांपल आपको मालूम है कि अगर आयरन आप रख देते हो तो रस्ट हो जाता है, ऑक्सीडाइज हो जाता है। तो अगर हम इतना अच्छा वैक्यूम करेंगे, क्योंकि हम जो एटॉमिक स्केल में स्ट्रक्चर ग्रो कर रहे हैं काफी कम मटेरियल, तो स्मॉल इम्प्योरिटी भी होगा, स्मॉल अमाउंट ऑफ ऑक्सीजन दैट कैन डिग्रेड योर मटेरियल, पर इतना अल्ट्रा हाई वैक्यूम में आपका मटेरियल का डिग्रेडेशन नहीं होगा। सो let's see a video to understand how molecular beam epitaxy work। तो this is the cell, और इससे हम इंडिविजुअल एटम्स को ऐसे इवापोरेट करते हैं और इधर इस सबस्ट्रेट में डिपोजिशन हो। तो ड्यूरिंग द इवापोरेशन वी डू समथिंग एज इलेक्ट्रॉन डिफ्रैक्शन। तो आप सब लोगों को मालूम है कि इलेक्ट्रॉन माइक्रोस्कोप क्या है, पर दैट इज ए सिमिलर थिंग बट ए डिफरेंट टेक्निक। तो इधर हम इलेक्ट्रॉन डिफ्रैक्शन देखते हैं। तो ये जो इलेक्ट्रॉन है, ये जो एटॉमिक अरेंजमेंट है उससे डिफ्रैक्ट होता है। तो डिफ्रैक्ट क्या है कि इलेक्ट्रॉन का वेव लाइक नेचर है, उसके वजह से इलेक्ट्रॉन का डिफ्रैक्शन है। जो सिमिलर कि अगर आपको ऑप्टिक्स के बारे में मालूम है तो ऑप्टिक्स का भी एक डिफ्रैक्शन है। बट एनीवे हम जब ग्रो होता है ये रियल टाइम हम उसका इलेक्ट्रॉन डिफ्रैक्शन ऐसा पैटर्न देखते हैं, और ये पैटर्न हम देख के समझ सकते हैं कि कैसा स्ट्रक्चर ग्रो हो रहा है, वो एटॉमिकली स्मूथ है कि नहीं, उसका एटॉमिक अरेंजमेंट कैसा है, वो सब डिटरमाइन कर सकते हैं जस्ट बाय लुकिंग एट दिस काइंड ऑफ इलेक्ट्रॉन डिफ्रैक्शन। यू नीड टू गेट ट्रेन्ड इन इट टू अंडरस्टैंड व्हाट इट इज, बट अगर एक बार आपको आ गया यू विल अंडरस्टैंड व्हाट इज गोइंग ऑन हियर, what is getting deposited here. So this is a very powerful tool called reflected high energy electron diffraction, RHEED। तो उससे हम क्या कर सकते हैं? तो अभी हमने देख लिया कि we have this kind of tools to grow atomically thin films, और हम जो मटेरियल है उसको मैनिपुलेट करना चाहते हैं to get something out of it। So one of the thing can be is memory। तो हमें सबको मालूम है कि memory is a state, तो that could be in computer क्या है कि 0 and 1। 0 मीन्स लो वोल्टेज हो सकता है, 1 इज हाई वोल्टेज। सिमिलरली मैग्नेटिकली अगर फॉर एग्जांपल जो हार्ड डिस्क है उसका अगर आपको मेमोरी डिफाइन करना है दैट कैन बी लाइक डाउन स्पिन डोमेन, जो मैग्नेटिक मोमेंट है नीचे है और मैग्नेटिक मोमेंट ऊपर है। सिमिलरली वी आर ट्राइंग टू इंजीनियर ए मेमोरी आउट ऑफ ए एंटी फेरोमैग्नेट। तो एंटी फेरोमैग्नेट इज ए वेरी वीक मैग्नेट। तो वीक मैग्नेट हमने इसीलिए चूज किया कि फॉर एग्जाम्पल आपका जो हार्ड डिस्क है उसको आप स्ट्रॉन्ग मैग्नेटिक फील्ड में अगर रख दोगे दैट memory will get lost, और उसका stray field effect भी आता है। Similarly, if you want, so to overcome this, we choose a antiferromagnet. But usually antiferromagnet में वो magnetization और domain is very difficult to get. So what we do, we distort the lattice. तो ये that is a Mn3 structure, तो इसका structure ऐसे मिलेगा। तो इधर जो blue atom है these are Mn, तो ये ऐसा triangle form करता है। This is what you get in nature। हम इसको क्या करते हैं कि एक पर्टिकुलर मेटल दैट इज टैंटलम, उसका एक एटॉमिक स्ट्रक्चर है, उसको पहले ग्रो करते हैं, उसके ऊपर Mn3 ग्रो करते हैं, एंड दैट distort this lattice. So this is a artificial distortion. इसका जो triangle है ये artificially distort हो गया और उसके वजह से you get a magnetic moment. Now there are some physics involved. For example, this electron has particular phase called Berry curvature और वो Berry curvature को हम modulate करते हैं. But if I don't go into that deeply, हम at the end result में क्या पाते हैं? This kind of multi-stable memory state. और these are very fastly switchable memory state. For example, हमारे पास जो RAM है, okay, that works in megahertz frequency, but ये जो memory है, that can be switched in terahertz. So around maybe 2 order of magnitude faster. So similarly, this is a material that we have grown. This is a TEM image. This is a transmission electron microscopic image. तो इधर आप individual atom को देख रहे हो इधर, and we are able to see that. इसमें भी क्या कर रहे हैं? We are artificially distorting this layer. So because there is a substrate underneath, हम जब ये material grow करते हैं, इसका atom distort हो जाता है. That is not its natural structure. We are able to tune its atomic positions. और वो position tune होने के बाद we can create a particular property called rectification effect. So we all use okay, I'll finish. Rectification effect. और उसमें क्या होता है कि आपका जो AC signal है that gets converted into DC. So now what we are doing, we are trying to make a membrane out of it. So for example, you have heard of this flexible displays, जो flexible thin films है. For example, अभी Samsung का भी fold level phone आता है. So you need flexible electronics for that. So what we do, we put a graphene here. Because graphene is a van der Waals material, we can peel off the material which we grow on top of it. So इधर भी एक video है that where we have grown a flexible material, and this can be like bent. So this is and you can use it for flexible electronics. So so you can create some quantum material and make some flexible membrane out of it. So this is the today's talk. I hope maybe some of you will work on quantum materials in future and progress the field. Thank you.
Thank you, Rudra, for the interesting talk. So if there are any questions, are there any questions? Okay.
How do you achieve such low pressures in the
Yeah, so
laboratory?
achieving this low pressure is very difficult. So there are different type of pumps. So one of the pump is called turbomolecular pump. So it is basically like a jet engine. Their blades rotates very fast. So that compress all of the air. And in the backing, we have a normal type scroll pump. So they pump most of the atmosphere out. And there are other types of pumps inside, which is called cryo pump. So cryo pump में क्या होता है कि there is a cold head, उसका जो temperature है that is around -170 degree Celsius, -170 degree. So around 3 to 4 Kelvin. तो उसमें उतना कम temperature में क्या होता है? All of the gas that is remained still after pumping with the turbo that get absorbed in the cold head. तो ऐसे हम रीच करते हैं, but that is not a easy process. उसके लिए हमें काफी कुछ प्रोटोकॉल फॉलो करना पड़ता है. फॉर एग्जांपल जो चेंबर का वॉल है, दे आर लॉट्स ऑफ एटमोस्फियर. जब हम एटमोस्फियर से ओपन करते हैं उसको, उधर काफी सारा वाटर और पोलर जो मॉलिक्यूल है दैट गेट्स एब्जॉर्ब देयर. तो उसको निकालने के लिए वी हीट अप द होल चेंबर. तो ये जो पूरा चेंबर है इसको हम पूरा 150 में बेक करते हैं, पूरा चेंबर. एंड देयर आर डिफरेंट लोड लॉक्स. तो फॉर एग्जांपल दिस इज द मेन चेंबर. तो इस चेंबर को हम कभी भी एटमोस्फियर से एक्सपोज नहीं करते, ये ऑलवेज वैक्यूम में रहता है. इधर हमारा गेट वाल्व है एंड इस गेट वाल्व को क्लोज करके वी कैन डिस्कनेक्ट दिस चेंबर्स. तो फॉर एग्जांपल ये जो छोटा सा पोर्शन है, वी लोड ए मटेरियल इनसाइड दैट चेंबर. उसके बाद उसको हम पंप कर देते हैं. रेस्ट ऑफ द चेंबर इज स्टिल इन वैक्यूम. उसके बाद इधर एक गेट वाल्व है, वी कैन क्लोज इट. एंड इधर हमारा मैग्नेटिकली कपल आर्म है, तो उससे इनसाइड वैक्यूम वी कैन ट्रांसफर दिस सैंपल फ्रॉम हियर तो इनसाइड द चेंबर. तो ये सारा इतना सारा प्रोटोकॉल मेंटेन करने के बाद वी कैन achieve this kind of ultra high vacuum inside the chamber.
Yeah, so just an announcement. So जो जिन लोगों ने नहीं किया है registration, you can just do the registration for the lab tour and all. We'll start at 1:45, the lab tour. Okay. And so are there any other questions, or else we'll start a quiz. So there are some prizes that we have kept. So we'll start the quiz then.
Okay.
So whoever wants to answer, just raise your hand and then we'll give you mic and we have some prizes for that if you answer correctly.
So if they have nothing to do, you can send them here. No, here there are mixed of physics and so the online. So we are also conducting quiz, so student might also be interested in that. So you are on escort duty. Hi.
Okay, so the question is, a chemist is found dead. A note lists carbon, lanthanum, sulfur, oxygen, nickel. Who did it?
Okay, it's yours.
Is his brother Nicholas, his sister Larissa, or his wife Suzanne?
I think his brother Nicholas murdered him because the first letters of all the carbon, lanthanum, sulfur, oxygen, and nickel spell out Nicholas.
Great. That's the
I-
correct
sorry.
answer.
Announcement.
I just said no. So he's getting a Tiafa t-shirt. So yeah. So the next question is, which gas often used in scuba diving tanks can make your voice sound incredibly deep, opposite to helium? Let me go to some other people.
Is it nitrogen by any chance?
Yeah.
It's helium. Helium. Argon.
No, not nitrogen. Anyone else? No. We can.
Maybe you all name one gas per per person.
But it's a not very conventional. It's a bit complicated if you're not from chemistry background, maybe. So it's sulfur hexafluoride, SF6. Okay. Okay. Then yeah. Well, no. Then just last question. One more. Yeah.
So you are expecting easier question or hard question? Huh? But easy, for easy question you won't get good prizes.
So for easier question we have eclairs, and for harder ones we
Okay,
have.
raise your hand. First, raise your hand. Don't shout the answer.
Which space telescope is named after prominent Indian American scientists?
So we'll give chance to other people who have.
Is it Kaprekar?
Yeah.
Chandra Excel.
Yeah.
Chandra Excel.
So who was the scientist?
The scientist name.
The name of the scientist. Full name of the scientist.
We'll give.
You have.
Subramaniam Chandrasekhar.
So you knew that, right? Yeah. So we need few chocolates here.
मैं एक देख के जाती हूँ. Take it for the scientists. Okay, we'll start. Rudra, you have to now introduce. Yeah. Who?
Younger people, we are requesting you to take seat in front of the foyer and leave the chairs for the senior citizens and people who are in need.
Yeah, so now we'll start with the next talk.
So, hello everyone. Hope you are enjoying the session. So, the next talk is from Kiran. So, she works on photons, so she can talk to photons and manipulates how they will behave. And to Kiran.
We request the younger people to come in front of the fire to sit, and chairs available for senior citizens and people who are in need.
Right? Hello.
Please try to maintain silence, and my friend Kiran will start. Please try to maintain silence. Kiran, please.
Yeah. Hi, everyone. So today I'm going to talk about Judwa particles. How many of you have seen Judwa movie? So this is a very old movie in which there are दो जुड़वा भाई होते हैं, और अगर एक को थप्पड़ मारते हैं तो दूसरे को भी असर होता है. वेल हमें पता है कि रियल लाइफ में तो ऐसा नहीं होता है. कितने लोगों ने जुड़वा भाइयों को देखा है? किसी ने नहीं देखा है? ऐसा नहीं होता है ना, पर क्वांटम वर्ल्ड में अपेरेंटली ऐसा होता है. सो वी आर गोइंग टू टॉक अबाउट जुड़वा पार्टिकल्स. Last year we celebrated 100 years of quantum, and the year 2025 was an international year of quantum science and technology, because 1925 was birth year of quantum mechanics. क्वांटम मैकेनिक्स को डेवलप करने में बहुत सारे साइंटिस्ट का बहुत ज़्यादा योगदान था. उनमें से कुछ एक साइंटिस्ट की लिस्ट यहाँ पे है. इन लोगों ने काफ़ी कुछ दिया हमें, और उनमें वो जो क्वांटम थ्योरी है वो बहुत ही कॉम्प्लेक्स मैथ्स है, और उस कॉम्प्लेक्स मैथ्स को अगर हम समझने की कोशिश करते हैं तो उनमें से कुछ मेन पॉइंट्स निकल के आते हैं. उनमें से एक मेन पॉइंट है वेव पार्टिकल ड्युअलिटी. कितने लोगों को पता है वेव पार्टिकल ड्युअलिटी के बारे में? यस. आप लोगों को नहीं पता है? क्या आपको पता है पार्टिकल क्या होता है? पार्टिकल समझते हैं? वेव समझते हैं? तो उन्होंने क्या बोला था? श्योर. सो उन्होंने क्या बोला, जैसे कि एक पार्टिकल है, एक बॉल होती है, वो एक पार्टिकल होती है. हम क्वांटम पार्टिकल्स की बात करते हैं जो बहुत ही छोटे होते हैं. तो उन्होंने बोला कि जो क्वांटम पार्टिकल्स होते हैं वो वेव और पार्टिकल दोनों की तरह बिहेव करते हैं. डिपेंड करता है कि आप कैसे देखते हैं. तो हमें पता है कि एक वेव जो होती है उसका एक वेवलेंथ होता है. वेवलेंथ पता है आपको? यस. एंड जो पार्टिकल होती है उसकी पोजीशन होता है और मोमेंटम होता है. राइट? मोमेंटम पता है, पोजीशन भी पता है. सो उन्होंने बोला कि एक क्वांटम पार्टिकल वेव और पार्टिकल दोनों की तरह बिहेव करता है, और उसका जो वेव के कोरस्पॉन्डिंग जो वेवलेंथ होता है वो मोमेंटम के साथ उसका एक रिलेशन होता है, जो कि इससे दिया जाता है. अब मान लीजिए आप एक वेव क्रिएट कर रहे हैं, एक रस्सी है उससे आप वेव क्रिएट कर रहे हैं, तो आप इसमें देख सकते हैं कि इसमें वेवलेंथ वेल डिफाइंड है. वेवलेंथ क्या होती है? दो मैक्सिमाज के बीच की डिस्टेंस या दो मिनिमाज के बीच की डिस्टेंस. राइट? सो इसमें हम वेवलेंथ डिफाइन कर सकते हैं कि ये यहां से लेके यहां तक की दूरी वेवलेंथ है. लेकिन अगर हम बोले कि वेव जो है वो रस्सी में कहां पे है, तो हम लोग पिन पॉइंट नहीं कर सकते. राइट? वो तो हर जगह है, यहां से लेके यहां तक. तो लेकिन इसमें पोजीशन डिफाइंड नहीं है. वेवलेंथ डिफाइंड है पर पोजीशन डिफाइंड नहीं है. अब अगर हम दूसरी तरह से देखें, अगर हम एक छोटा सा पल्स देते हैं रस्सी को और फिर छोड़ देते हैं, इस केस में हम वेवलेंथ डिफाइन कर सकते हैं क्या? कर सकते हैं? नहीं, क्योंकि हमारे पास दो मैक्सिमाज है ही नहीं, दो मिनिमाज भी नहीं है, तो हमें नहीं पता कि इसकी वेवलेंथ क्या होगी. पर इस केस में हम पोजीशन डिफाइन कर सकते हैं कि पोजीशन ये है. तो हम जब पोजीशन डिफाइन कर सकते हैं तो वेवलेंथ डिफाइन नहीं कर सकते, और वेवलेंथ डिफाइन कर सकते हैं तो पोजीशन डिफाइन नहीं कर सकते. राइट? तो दोनों चीजें हम एक साथ डिफाइन कर ही नहीं सकते. और वेवलेंथ से हम मोमेंटम निकालते थे. तो इसी से हमारे पास आता है क्वांटम मैकेनिक्स का दूसरा प्रिंसिपल, जो कि है हम लोग पोजीशन और मोमेंटम, उसको बोलते हैं हम अनसर्टेनिटी प्रिंसिपल. सो स्कूल स्टूडेंट्स लाइक आप ज्यादा नोटेशंस पे ध्यान मत दे, वर्ड्स पे ध्यान मत दे, आप समझने की कोशिश करें। अगर आप थोड़ा सा भी समझ पा रहे हैं बहुत अच्छी बात है। तो हम क्या कर सकते हैं, अगर हम पोजीशन मेजर करने की कोशिश करेंगे तो हमें मोमेंटम नहीं पता होगा, मोमेंटम मेजर करने की कोशिश करेंगे तो हमें पोजीशन नहीं पता होगा। तो हम दोनों चीजें एक साथ मेजर नहीं कर सकते उसके लिए। सो इसको हम बोलते हैं हाइजेनबर्ग अनसर्टेनिटी प्रिंसिपल, राइट। सो इसको हम कैसे समझ सकते हैं, मान लीजिए एक स्लिट है, उससे बहुत सारे पार्टिकल्स, अब हम क्वांटम पार्टिकल्स की बात कर रहे हैं, पार्टिकल्स पास कर रहे हैं, तो वो सामने अगर हम दीवार लगा दे तो दीवार पे कहीं ना कहीं तो इंसिडेंट करेंगे, जैसे बॉल इंसिडेंट करती है। अब ये वाला जो स्लिट है उसको हम बोलेंगे पोजीशन। पोजीशन क्या है पार्टिकल्स की, वो कहाँ से एंटर हुए, लेकिन वो दीवार पे कहाँ पे लग रहे हैं वो डिफाइन होगा कि उसकी बॉल जो पार्टिकल्स है उनकी डायरेक्शन क्या थी। अगर उनकी डायरेक्शन ऊपर की तरफ थी तो दीवार पे ऊपर की तरफ लगेंगे, नीचे की तरफ थी तो नीचे की तरफ। तो इस केस में सारे पार्टिकल्स सामने लग रहे हैं। लेकिन तो इसमें हमारी पोजीशन में इतनी अनसर्टेनिटी है, इतनी पोजीशन में अनसर्टेनिटी है और इतनी मोमेंटम में अनसर्टेनिटी है, बिकॉज डायरेक्शन मतलब मोमेंटम किस साइड है वो डिफाइन करेगा कि पार्टिकल्स दीवार पे कहाँ पे लग रहे हैं। अभी अगर हम पोजीशन को डिफाइन करने की कोशिश करते हैं, पोजीशन को वेल डिफाइन करने की कोशिश करते हैं, तो उससे क्या करेंगे, हम पोजीशन को, ये स्लिट को नैरो करेंगे, तो उस केस में क्या होगा कि पार्टिकल्स फैल जाएंगे। तो पोजीशन अनसर्टेनिटी कम हो गई लेकिन मोमेंटम अनसर्टेनिटी बढ़ गई, जैसे कि हमने रस्सी के केस में भी देखा था। तो यही हमारा अनसर्टेनिटी प्रिंसिपल है कि हम दोनों चीजें एक साथ डिफाइन कर ही नहीं सकते। ऐसा आप टैप के केस में भी देख सकते हैं, जब टैप से पानी निकल रहा होता है तो आपने देखा होगा कि पानी सीधा सीधा गिरता है, लेकिन अगर आप अपने हाथ डालते हैं और उनको नैरो करने की कोशिश करते हैं तो पानी हर साइड में फैल जाएगा, देखा है ना। हाँ, तो वही है, ऐसा ही होता है क्वांटम मैकेनिक्स में भी, इसको हम बोलते हैं अनसर्टेनिटी प्रिंसिपल। सो इसका मतलब है हम दो प्रॉपर्टीज को एक साथ नहीं पता कर पा रहे हैं। क्वांटम मैकेनिक्स में ऐसी बहुत सारी प्रॉपर्टीज होती हैं जिनके दो को हम लोग दो पेयर, मतलब एक पेयर को हम एक साथ डिफाइन नहीं कर पाते। उनमें से पोजीशन और मोमेंटम एक है, तो हम उसी के बारे में बात करेंगे अभी। अब नेक्स्ट है रैंडमनेस। आप लोगों ने अपने चारों तरफ रैंडमनेस देखी है, कॉइन फ्लिप करते हैं उसमें रैंडमनेस होती है। अब मान लीजिए कि हमारे पास एक बॉक्स है, उसमें दो बॉल्स हैं, एक ब्लू बॉल है और एक ऑरेंज बॉल है। आपने रैंडमली एक बॉल चूज करी, आपने देखा नहीं क्या है और उसको आप बहुत ही दूर लेके गए। तो आप अगर उसको बहुत दूर लेके गए और उसके बाद आपने देखा कि कौन सी बॉल है वो, और टर्न्स आउट कि वो ऑरेंज कलर की बॉल है, तो आपको क्या लगता है कि आपने जब बॉल निकाली थी तब से ही ऑरेंज है या फिर आपने जब देखा तब ऑरेंज हुई? आपको लगता है जब देखा तब ऑरेंज हुई। कितने लोगों को लगता है कि जब निकाली तब ऑरेंज थी? ओके, और कितने लोगों को लगता है कि जब देखा तब ऑरेंज हुई? हाँ, तो क्योंकि हमारे पास बॉल एक क्लासिकल पार्टिकल है, उसके केस में जब से वो बॉल निकाली गई है तब से ही ऑरेंज है। तो कलर जो है उसका वेल डिफाइंड होता है स्टार्टिंग से ही। तो क्लासिकल पार्टिकल के केस में क्या होता है कि जब हमने निकाली थी तब से ही ऑरेंज थी, हम लोग बस देख नहीं रहे थे उसको। तो रियलिटी थी, मेजरमेंट क्या, तो उस केस में जो हम देख रहे हैं वो एक मेजरमेंट है, और मेजरमेंट बताता है कि फैक्ट क्या है। मतलब वो बॉल ऑरेंज थी, दैट्स अ फैक्ट, वो शुरू से ही था, शुरू से ही ऑरेंज थी। और क्लासिकल केस में हमारे पास मेजरमेंट सिर्फ एक फैक्ट को रिवील करता है, जबकि जब हम क्वांटम पार्टिकल्स की बात करते हैं उसमें क्या होता है, हम पार्टिकल निकाल रहे हैं, उसको बहुत ही दूर लेके जा रहे हैं, और जब हम मेजरमेंट कर रहे हैं तब वो ऑरेंज हो जाता है। तो क्वांटम मैकेनिक्स क्या कहता है कि जब पार्टिकल हमने निकाला तो ऑरेंज और ब्लू एक साथ दोनों कलर की थी, और जब तक हम उसको मेजर नहीं करेंगे तब तक उसका कलर डिफाइन नहीं होता है। तो जबकि पिछले केस में क्या हो रहा था कि मेजरमेंट से एक फैक्ट रिवील हो रहा था, इस केस में मेजरमेंट ही क्रिएट कर रहा है उस कलर को। तो मेजरमेंट से ही डिसाइड हो रहा है कि वो पार्टिकल ऑरेंज होगा या ब्लू होगा, उससे पहले उसका कलर डिफाइंड था ही नहीं। सो यही डिफरेंस है क्लासिकल और क्वांटम मैकेनिक्स में। पर आइंस्टाइन को ये बात बिल्कुल पसंद नहीं आई, उसने बोला कि जो रियलिटी है वो फिजिकल होनी चाहिए, मतलब पार्टिकल का कलर तो डिफाइन होना ही चाहिए, डजंट मैटर वो क्वांटम पार्टिकल है या जो कुछ भी है, ऑब्जर्वेशन वो होना चाहिए, चाहे हम ऑब्जर्व कर रहे हैं या फिर नहीं ऑब्जर्व कर रहे हैं, कलर तो उसका होना ही चाहिए। दोनों कलर एक साथ कैसे हो सकते हैं? तो उसने बोला, डू यू रियली बिलीव मून इज नॉट देयर व्हेन यू आर नॉट लुकिंग एट इट? और उसने ये भी बोला कि गॉड डज नॉट प्ले डाइस, जैसे कि रैंडमली वो पार्टिकल ऑरेंज या ब्लू हो जाएगा। उसने बोला कि ये बहुत रैंडम इवेंट है और ऐसे रैंडम इवेंट नहीं होने चाहिए। जैसे डाइस के केस में भी क्या होता है कि वो एक रैंडम इवेंट होता है, पर अगर आप अच्छे से ट्रैक करोगे कि डाइस के किस कॉन्फ़िगरेशन में था, हमने कितना फोर्स लगाया, तो आप पता लगा सकते हो कि ऊपर कौन सा नंबर आएगा। तो रैंडम नहीं होता, बस हमें सब कुछ पता नहीं होता, हमारी इग्नोरेंस की वजह से वो रैंडम इवेंट बन जाता है, राइट। तो आइंस्टाइन यही कहना चाह रहा था कि कुछ तो है जो हमें पता नहीं है, इसकी वजह से ये रैंडम है, ऐसा नहीं है कि भगवान डाइस खेलते हैं। तो उसके बाद आइंस्टाइन ने क्या किया, दो और साइंटिस्ट के साथ मिलके, आइंस्टाइन, पोडोल्स्की और रोजन, इन तीनों का नाम का फर्स्ट लेटर ईपीआर, एंड उनके साथ मिलके उन्होंने एक पैराडॉक्स दिया जिसको हम बोलते हैं आज ईपीआर पैराडॉक्स। तो ईपीआर पैराडॉक्स में उसने बोला कि ठीक है चलो, मैं मान लेता हूँ, एक बार के लिए मैंने मान लिया कि क्वांटम मैकेनिक्स जो भी बोलता है कि भाई तुम्हारा वेव पार्टिकल ड्युअलिटी है, अनसर्टेनिटी भी है, और मेजरमेंट ही रिवील करता है, मेजरमेंट ही रिजल्ट देता है, तो ये सब मैं मान लेता हूँ कि रैंडम भी है। तो मान लीजिए कि दो पार्टिकल्स हैं, दो ऐसे पार्टिकल हैं जिनकी पोजीशन सेम है और मोमेंटम ऑपोजिट है, इक्वल एंड ऑपोजिट। तो ये दोनों पार्टिकल हैं, ठीक है। क्वांटम मैकेनिकली ऐसे पार्टिकल एग्जिस्ट कर सकते हैं, तो किसी को कोई प्रॉब्लम नहीं थी। तो उसने बोला कि ठीक है, दो ऐसे क्वांटम पार्टिकल्स हैं, हम उनको दोनों को निकालते हैं बाहर और उनको बहुत ही दूर लेके जाते हैं, बहुत ज्यादा दूर। सो एक को हम सन पे लेके जाते हैं, दूसरे को हम अर्थ पे लेके जाते हैं। तो अभी एक का हम पोजीशन में मेजर करते हैं और दूसरे का मोमेंटम मेजर करते हैं। अब पहले का हमने पोजीशन मेजर किया, लेकिन उस क्वांटम मैकेनिक्स के अकॉर्डिंग जैसे ही हम पोजीशन मेजर करते हैं सब कुछ चेंज हो जाता है। लेकिन क्योंकि एक पार्टिकल सन पे है और दूसरा अर्थ पे है, सन और अर्थ की डिस्टेंस बहुत ज्यादा है, सो लाइट सन से अर्थ तक पहुंचने में कितना टाइम लेती है? स्कूल स्टूडेंट्स 8.3 मिनट्स, सो अप्रोक्सीमेटली 500 सेकेंड्स। और लाइट से फास्ट कुछ ट्रेवल करता है? नहीं। सो अगर हम दोनों मेजरमेंट्स को 500 सेकेंड के अंदर परफॉर्म करेंगे तो दूसरे पार्टिकल को पता ही नहीं लगेगा कि पहले पार्टिकल का पोजीशन मेजर हुआ है। तो जैसे ही हमने पहले पार्टिकल का पोजीशन मेजर किया, हमें पता लग गया कि दूसरे पार्टिकल का पोजीशन क्या है, और जैसे ही हमने दूसरे पार्टिकल का हम मोमेंटम भी मेजर कर लेंगे, तो अब हमें दूसरे पार्टिकल का दोनों चीजें पता है, पोजीशन भी पता है, मोमेंटम भी पता है। तो इसका मतलब तो हाइजेनबर्ग अनसर्टेनिटी प्रिंसिपल गलत है। तो उसने बोला था कि मैंने मान लिया कि क्वांटम मैकेनिक्स सही है, पर अभी तो तुम बोल रहे हो कि क्वांटम मैकेनिक्स गलत है। तो दैट वाज द पैराडॉक्स। तो उसने बोला या तो हाइजेनबर्ग अनसर्टेनिटी प्रिंसिपल गलत प्रूव हो रहा है, या फिर रिजल्ट्स रैंडम नहीं है, मतलब ये जो रिजल्ट्स हमें दिख रहे हैं वो पहले से ही डिफाइंड थे, जैसे कि डाइस के केस में है। जैसे हम रोल करेंगे डाइस तभी पता लग जाता है कि भाई क्या आने वाला है, चाहे तुम कभी भी जाके देखो। तो उसने ये पैराडॉक्स दी थी 1935 में। तो उसने ये दोनों कॉन्फ्लिक्ट स्टेटमेंट को लेके बोला कि जो भी है क्वांटम मैकेनिक्स इनकम्प्लीट है। सो दैट वाज द कंक्लूजन। पर अभी इन स्टेट्स, ये जो पर्टिकुलर टाइप ऑफ स्टेट्स हैं, इनको बोला गया बाद में ईपीआर स्टेट्स, और इन्हीं स्टेट्स को बाद में एंटेंगल्ड स्टेट भी बोला गया, जो कि जिनमें हम जो वेरिएबल्स, कॉन्जुगेट वेरिएबल जो कि एक साथ डिटरमाइन नहीं कर सकते, वो कोरिलेटेड होते हैं। अभी उसी के बेसिस पे जो आइंस्टाइन ने बोला, उसके बेसिस पे लोगों ने कहा कि जैसे डाइस रोल करते हैं, उसमें जो भी फोर्स है या फिर जो भी इनिशियल पोजीशन है डाइस की, वो सब डिटरमाइन करती है कि रिजल्ट क्या होने वाले हैं। ऐसे ही क्वांटम पार्टिकल के केस में भी कुछ हिडन वेरिएबल है, ऐसे वेरिएबल जिनको हम मेजर नहीं कर सकते, पर वही डिफाइन करेंगे कि रिजल्ट क्या आने वाला है, कि जो हमारी बॉल है वो ऑरेंज होगी या फिर ब्लू होगी। सो जब हम बॉल को निकालते हैं तभी से कुछ वेरिएबल होते हैं ए बी, लेट्स से, जो कि हमसे हिडन होते हैं, हमें पता नहीं है, लेकिन वो पहले से ही प्री डिफाइंड होते हैं, और चाहे अब हम कितनी भी दूर उसको लेके जाएं, वो हिडन वेरिएबल उसके साथ ही चलते हैं और वही डिफाइन करेंगे कि हमारी बॉल ऑरेंज हो रही है या फिर ब्लू हो रही है। तो दिस वाज कॉल्ड हिडन वेरिएबल थ्योरी। पर अब हमारे पास ऐसा है कि हम दो बार तो मेजर नहीं कर सकते, कि एक बार हमने यहाँ पे मेजर कर लिया, एक बार हमने यहाँ पे मेजर कर लिया, क्योंकि एक क्वांटम मैकेनिक्स बोलता है अगर हमने एक बार मेजर किया तो सब कुछ चेंज हो गया, मेजरमेंट से सब कुछ चेंज हो जाता है। तो हम लोग कैसे वेरीफाई करें कि हिडन वेरिएबल थ्योरी सही है या फिर क्वांटम मैकेनिक्स सही है? सो दिस इज द क्वेश्चन। कितने लोगों को लगता है क्वांटम मैकेनिक्स सही है, और कितने लोगों को लगता है हिडन वेरिएबल थ्योरी सही है? ओके, तो आपको सबको लगता है कि हिडन वेरिएबल्स हैं जो कि डिटरमाइन करते हैं बाद में रिजल्ट्स क्या है। तो काफी टाइम तक साइंटिस्ट ने भी सोचा, जैसे कि हम बात कर रहे थे, ये 1937 में उन्होंने ईपीआर पैराडॉक्स दिया था और उसी टाइम पे हिडन वेरिएबल थ्योरी वगैरह आई। लोगों ने सोचा कि कैसे डिसाइड करें, क्या कर सकते हैं हम पता लगाने के लिए कि क्या सही है, क्योंकि जब उन्होंने बोला कि हिडन वेरिएबल्स है जिनको हम, जो हिडन है, जिनको हम मेजर कर ही नहीं सकते, तो हमें कैसा पता लगेगा कि क्या सही है। तो उसके बाद एक साइंटिस्ट जॉन बेल, उसने 1964 में एक एक्सपेरिमेंट सजेस्ट किया कि भाई आप ऐसे ऐसे परफॉर्म कर लेना। उसने एक्सपेरिमेंट किया नहीं, उसने सिर्फ सजेस्ट किया कि आप ये ईपीआर स्टेट लो और उससे एक एक्सपेरिमेंट करो, और अगर उसे मेजर करो दोनों पार्टिकल्स का रैंडमली पोजीशन या मोमेंटम, और उस एक्सपेरिमेंट को बार बार रिपीट जब करोगे आप, जब उसको बार बार रिपीट करोगे, तो अब ये रिजल्ट्स जो आएंगे उनसे हम पता लगा सकते हैं कि हिडन वेरिएबल सही है या फिर क्वांटम मैकेनिक्स सही है। तो उसने 1964 में एक्सपेरिमेंट परफॉर्म किया था। लेकिन ये इक्वालिटी जो है वो जैसे पोजीशन मोमेंटम के लिए उसने दी है, उसने अलग पार्टिकल स्पिन्स के लिए दी थी। तो लाइक अलग अलग वेरिएबल्स के लिए ऐसा हम बना सकते हैं और ऐसे मेजरमेंट कर सकते हैं अलग अलग क्वांटम प्रॉपर्टीज के लिए, और उससे हम पता लगा सकते हैं कि क्या सही है। तो उसने 1964 में ये दिया, पर क्योंकि एक्सपेरिमेंट्स बहुत टाइम लेते हैं, अभी उसने ईपीआर ने तो स्टेट दे दी दिमाग से निकाल के कि भाई ये तुम्हारी स्टेट है, लेकिन एक्सपेरिमेंटली उन स्टेट्स को अचीव करना बहुत डिफिकल्ट है, और फिर आपको डिटेक्टर्स चाहिए जो डिटेक्ट कर सके। टेक्नोलॉजी इतनी एडवांस नहीं थी, तो 8 साल लगे उस एक्सपेरिमेंट को एक्चुअल में परफॉर्म करने के लिए, और 8 साल बाद 1972 में ये एक्सपेरिमेंट किया गया और जिसमें उन्होंने प्रूव किया कि क्वांटम मैकेनिक्स सही है। तो उन्होंने ऐसा कुछ एक्सपेरिमेंट किया फ्रीडमैन एंड क्लॉस्टर ने जिसमें ये देखा गया कि क्वांटम मैकेनिक्स एक्चुअल में सही है। पर फिर लोगों ने बोला कि देखो, आपने तो ऐसा बोला था एक को सन पे लेके जाओ और एक को अर्थ पे लेके जाओ, एक को अर्थ पे रखो, दोनों पार्टिकल्स को इतना सेपरेट करना है, पर आपने तो दोनों के दोनों पार्टिकल्स को लैब में ही रखा है। तो ऐसे लोगों ने बहुत सारी कमियां निकाली एक्सपेरिमेंट के अंदर, जिन कमियों को बोला गया लूप होल्स। तो इवन तो एक्सपेरिमेंट हो गया था, पर उन एक्सपेरिमेंट्स में लूप होल थे बहुत सारे, और उन लूप होल्स को साइंटिस्ट ने एक एक करके ठीक करने की कोशिश करी, एंड फाइनली 2015 में जाके हमें पहला लूप होल फ्री बेल टेस्ट मिला, जिसमें उन्होंने जो डिस्टेंस था वो 1.3 किलोमीटर रखा था। 1.3 किलोमीटर सही, क्योंकि हम जब अर्थ और डिस्टेंस का देख रहे थे, तो अर्थ और सन का डिस्टेंस देख रहे थे, तो कितना था, टाइम कितना था हमारे पास, 500 सेकेंड्स, राइट। लेकिन 1.3 किलोमीटर के कोरस्पॉन्डिंग बहुत कम टाइम आएगा, लेकिन हमारे डिटेक्टर्स काफी फास्ट होते हैं, तो हम इतना टाइम से भी प्रूव कर सकते हैं, हमें बहुत ज्यादा सेपरेट करने की जरूरत नहीं है। तो ये एक्सपेरिमेंट किया गया, एंड फाइनली दैट अचीव्ड लूप होल फ्री बेल इनइक्वालिटी वायलेशन, और जिससे ये प्रूव हुआ कि एक्चुअल में क्वांटम मैकेनिक्स ही सही है। सो फास्ट फॉरवर्ड टू टुडे, आज हम सेकंड क्वांटम रिवॉल्यूशन में है, जहां पे हम ये समझने की कोशिश नहीं कर रहे कि क्वांटम पार्टिकल्स कैसे बिहेव करते हैं। आज हम एक्चुअल में वो क्वांटम पार्टिकल्स को लैब में प्रोड्यूस कर सकते हैं और उनको टेक्नोलॉजी में कन्वर्ट करने की कोशिश कर रहे हैं। और ये टेक्नोलॉजीज है क्वांटम कंप्यूटिंग, क्वांटम सेंसिंग एंड क्वांटम कम्युनिकेशन। ये अलग अलग चीजों में अप्लाई करने की कोशिश कर रहे हैं, और बहुत जल्दी आप सबकी लाइफ भी इन क्वांटम टेक्नोलॉजी से इम्पैक्ट हो रही होगी। सो हमारी लैब में हम मोस्टली क्वांटम कम्युनिकेशन पार्ट पे वर्क करते हैं। व्हाट वी डू इज हम लोग एंटेंगल्ड फोटोन्स जनरेट करते हैं लैब में, क्योंकि हम फोटोन्स की बात कर रहे हैं। फोटोन्स क्या होते हैं, लाइट का क्वांटा, लाइट एक सिंगल पार्टिकल ऑफ लाइट, राइट, पता है ना आप सबको। तो हम बहुत कम लाइट की बात कर रहे हैं, जो आजकल हम चारों तरफ देख रहे हैं, कितने फोटोन्स होंगे, एनी गेस? यस, जस्ट गेस।
लाइट के एक बल्ब में से निकलने वाले फोटॉन्स एक दूसरे से एंटेंगल्ड होते हैं?
नहीं, वो नहीं होते, हमें स्पेशल प्रॉपर्टी नहीं, वो अलग, वो नहीं होता है। हम इंडिविजुअल फोटॉन्स की बात कर रहे हैं, ऐसे एंटेंगल नहीं हो सकते हैं फोटॉन्स। यस, सो जो हम अपने चारों तरफ देख रहे हैं, एक सेकंड में लगभग 10⁻19 फोटॉन्स होते हैं, और अब हमें एक सिंगल फोटोन या बहुत कम फोटॉन्स के साथ काम करना है। तो इसलिए हमारे सारे एक्सपेरिमेंट ऐसे लाइट बंद करके होते हैं, ऐसे हम लैब में काम करते हैं। और ये आपको क्लियरली नहीं दिख रहा होगा, पर ये हम क्वांटम कम्युनिकेशन करने की कोशिश कर रहे हैं। हमने TIFR में सक्सेसफुली 100 मीटर क्वांटम कम्युनिकेशन अचीव किया है, वन ऑफ द 4 years। एंड अभी हम लोग 5 किलोमीटर पे भी ट्राई कर रहे हैं। एंड दिस इज आवर ग्रुप इन TIFR।
entangled photons मतलब कोई पैरामीटर्स हैं जो दोनों में सेम है, बराबर?
Yes.
कोरिलेटेड है।
Yeah.
तो कौन से पैरामीटर्स कोरिलेटेड होते हैं दो फोटॉन्स में?
या दैट्स अ गुड क्वेश्चन। सो अलग अलग डिग्री ऑफ फ्रीडम होते हैं, जैसे कि हमने पहले बात की पोजीशन और मोमेंटम। सो जैसे फोटोन इस डायरेक्शन में ट्रैवल कर रहे हैं तो हम ट्रांसवर्स पोजीशन और मोमेंटम की बात करते हैं, क्योंकि जेड डायरेक्शन में तो पोजीशन हमेशा चेंज होती रहेगी। तो ट्रांसवर्स पोजीशन और ट्रांसवर्स मोमेंटम हो सकते हैं। उसके अलावा पोलराइजेशन हो सकते हैं। आपको पता है ना लाइट का पोलराइजेशन क्या होता है, कि जो वेव है वो किस डायरेक्शन में ऑसिलेट कर रही है, कॉरस्पॉन्डिंग EM वेव। तो वो हो सकते हैं। उसके अलावा और भी होते हैं, जैसे कि एनर्जी और टाइम होता है फोटोन्स का, और ऑर्बिटल एंगुलर मोमेंटम भी होता है। तो अलग अलग डिग्री ऑफ फ्रीडम होते हैं जो यूज कर सकते हैं। हमारे पास स्पेशल टाइप ऑफ क्रिस्टल होते हैं जो कि बहुत छोटे होते हैं, नॉन लीनियर क्रिस्टल बोलते हैं हम उनको। उसमें क्या होता है कि वो दिखने में बिल्कुल ग्लास जैसे ही होते हैं। उसमें क्या होता है कि एक फोटोन जाता है और एक फोटोन से 2 फोटोन बनते हैं। अब क्योंकि 2 फोटोन एक ही फोटोन से बने हैं तो उनकी प्रॉपर्टीज कोरिलेटेड होंगी। Yeah, that's it. Thank you so much. We can take questions.
So any questions?
Yeah.
क्वांटम कम्युनिकेशन का गेम क्या होता है और व्हाट एक्चुअली वी डू इट? So my question is कि quantum communication का aim क्या होता है? What do we actually do when we say we are communicating?
So secure communication तब होता है जब हम कोई इंफॉर्मेशन एक एंड से दूसरे एंड तक भेज सके और बीच में कोई सुन रहा हो तो हमें पता लग जाए कि सुन रहा है, ताकि हम रोक सके उसको। तो क्वांटम कम्युनिकेशन जो अभी तक हम कम्युनिकेशन कर रहे हैं वो इस क्राइटेरिया पे बेस्ड होता है कि उसको इंफॉर्मेशन को डिकोड करना बहुत मुश्किल है। सो हमारे पास इतने रिसोर्सेज, इतने पावरफुल कंप्यूटर्स हैं नहीं जो डिकोड कर पाए। तो उस क्राइटेरिया पे बेस्ड होता है। क्वांटम कम्युनिकेशन में क्योंकि हमने देखा कि जब हम मेजरमेंट करते हैं तो रैंडमली रिजल्ट देता है। तो क्वांटम मैकेनिक्स के लॉज ही इंश्योर करते हैं कि अगर आप बीच में कोई मेजरमेंट करते हैं तो वेव फंक्शन चेंज हो जाता है और हमें डिटेक्ट हो जाता है कि हाँ कोई तो बीच में सुन रहा है एंड वी कैन जस्ट स्टॉप इट। सो क्वांटम मैकेनिक्स के लॉ ही इंश्योर करते हैं कि सिक्योर है। सो अगर फ्यूचर में कोई बहुत अच्छी टेक्नोलॉजी भी आ जाएगी तो उसको ब्रेक नहीं कर पाएगी। यस।
क्वांटम सेंसिंग क्या होता है?
सो क्वांटम सेंसिंग इज बेसिकली मेजरमेंट। कोई भी चीज है उसको प्रिसाइजली सेंस करना, मेजर करना। जैसे माइक्रोस्कोपी होती है जिसमें हम बहुत छोटे पार्टिकल्स को मेजर करते हैं। तो क्वांटम टेक्नोलॉजीज को यूज करना मेजरमेंट के लिए।
एटम देख पाएंगे?
एटम्स जैसे इलेक्ट्रॉन माइक्रोस्कोप से भी हम एटम्स देख सकते हैं। आपने रुद्र की स्लाइड देखी होंगी, उसमें देख पा रहे थे हम। बट हाँ, लाइक क्वांटम सेंसिंग का मतलब ये है कि हम बेटर रिजल्ट्स जो क्लासिकल इंस्ट्रूमेंट से अटेन कर पा रहे थे उससे बेटर रिजल्ट्स हम देख सकते हैं।
Then now we can start a quiz, a short quiz. So we have some prizes for that, and we'll just, so whoever knows the answer, you have to just raise your hand, and we have some prizes we can just distribute. This is not the question, by the way. This is the question. What is the scientific reason that food cooks significantly faster inside a pressure cooker?
I just forgot it.
It's because in a pressure cooker you increase the pressure inside, so boiling point depends on the pressure. So as you increase the pressure, the boiling point also increases. So you need more heat to heat the substance inside the pressure cooker. That's why it cooks faster.
Any other guesses?
Superheating of the steam, which leads to cooking of the food faster. It goes above 100 degrees.
Any other guesses? Okay, so the answer is, as he said, that as you increase the pressure, the boiling point basically increases. So that's why. So he's getting something now. I'll also give him. Your answer was partially correct, so yeah. So the next question is, these animals are very smart and use a busy street in Shibuya, Japan, to crack open nuts and other food sources. What is the animal?
A squirrel, probably a squirrel.
Okay, any other guesses?
Is it a crow?
So it's the crow. So he is getting a prize. Yeah, one more question. Kiran, can you just? So at least you tried, so you can keep. It's done. It's done. So this is the question. I'm a metal, but I'm so light that I can float on water. I'm also used extensively in phone and laptop. What am I?
Is it lithium?
Is it silver?
Other guesses?
Gold?
You get the gold? Who? Say,
Silicon?
what is the answer?
So the answer is lithium.
So we can start our next talk now. Hi, sir. Have any question? Sorry. So क्या आप सब क्या?
So are there any other ways in which entanglement has been done?
Yeah, it can be like a spin of the electrons, or any quantum particle can be entangled, provided we have enough technology. So we are able to entangle electron and other particles as well. But we are particularly studying photons. Yeah, that's fine. There can be different particles that can be entangled, but we actually are running out of time, so we have to continue. Oh, yeah, this one. Yeah, yeah. Because we are running out of time, we have to start our next talk, but you can always mail the questions to outreach@tifr.res.in, and we'll make sure you get your answers. So do you know, Aishwarya Ka, and we all are PhD students here. And well, I am in my 5th year. So when I came around 6 years back to TIFR for interview, what is the first thing I liked about TIFR? Campus. So have you seen the seashore? It's so beautiful. So being from North India, I found it like amazing that some institute can have such an amazing campus with sea facing. That was my inspiration. That was the day I decided that I need to be here for PhD. And different people have different stories. Today we have Professor Sri Ganesh Prabhu to tell the story, equations, exploration, and ocean views. Why do a PhD at TIFR? So over to him.
Thank you. Can you all hear me?
No, I don't think it's working.
Can you hear me? Yeah, can you hear me? Yeah. Okay. So, good afternoon, everyone. And I know it's lunchtime, so I don't want to hold on to you, but I think it's a great thing to tell you about equations, explorations, ocean views. As just now Kiran told you that she was so impressed with the ocean view, and you have it right next to door. So after the talk, maybe you can before your lunch or something, you can always have a big round around that and you will see the Mumbai skyline. So the main question is, why do a PhD at TIFR? So I was also a VSRP student here, and before that also I had come here for one Nobel laureate lecture by Professor Chandrasekhar, and I was so impressed because I didn't know that such an institute exists in Mumbai. And you are all local, so you are really lucky that you have this outreach program by which you can visit here and we can showcase to you what are the kind of things that we do. So I hope it will motivate you. And then I came here as a visiting student research program, which is just after MSc or just around the last year of MSc. And then, of course, I did my PhD here and then I joined as a faculty. So now let me tell you why you want to do PhD at TIFR. But first of all, why to do PhD at all? So we will first begin with our today, that is 28th February. So what is this? Why it is called National Science Day? You all know? Because today is the day when C.V. Raman Sahab actually saw this Raman effect. And that was actually found today, and therefore it was considered as a National Science Day since 1986. Now, today is also a special day where so many scientists are born. One is Linus Pauling. So, you know, he has won 2 individual Nobel Prizes, unshared with anyone. So, one in chemistry and the other for peace. The second person who was born today was Leon Cooper. So those of you who are familiar with superconductivity or have heard about superconductivity, there is something known as Cooper pairs. So these Cooper pairs were actually told how these 2 electrons can form a pair by Leo Cooper. So he was born today. Then you have Stephen Chu, again a Nobel Prize winner. So he's the one who actually showed using lasers how you can cool the atoms, trap single atom or ensemble of atoms or group of atoms together and then go to a very low temperature. So that is Stephen Chu, who was born there. Then Daniel Tsui, he is also a Nobel Prize winner and he found what is known as a fractional quantum Hall effect in an experimentalist. So he was also born today. And then there is Paul Krugman. He's an economist. He writes very regularly in New York Times. He was born today. And Philip Hench, who is known for adrenal cortex work and physiology or medicine. So these are all the scientists born today on 28th February. So it's a very special day. So remember this. This is a take-home thing for you. Now, let's go. Your journey into the unknown. Why PhD and why in TIFR? Okay. So let's see, why spend 5+ years working on just one problem? So that is a question, because these 5 years are so important part of your life that you are going to spend on this. So what is it that PhD will give you or PhD will teach you which your other education will not give you? Okay. So let's see. So this is not about being smart. So you may be thinking, oh, PhD means smart guys or something, but that is not correct. And what is a myth? You normally feel, oh, Einstein, so I should be thinking about equations, these, that, and air, and then and something like that. So these are all very big pictures that you see of great scientists and all that. But that is not actually the reality. What is the reality? You have to be stubborn, meaning you must be very focused and work on that problem. And this is something that PhD is basically 90% of hard work. You are actually going to have a lot of resilience. No matter how many failures you get, you have to still keep working on that. And this is something which all these PhD students have undergone or are undergoing. And this is what PhD actually teaches you. And it is 10% inspiration. And Einstein had also said, what is a genius? Einstein also said that it is 1% inspiration, 99% perspiration. That means you have to work really hard. I mean, you can get idea, but to make that idea, really put it in a proper thing, that takes a lot of time. So this is the perspiration. Now, your textbooks will give you answers to all the solved problems. Okay. So you may be able to solve a problem now, which may come into the textbook after maybe 10, 20, 30, 40 years down the line. Because somebody will say, okay, this problem was solved by such and such a person, and then your name or whatever will be. And this is what we have been learning in our textbooks. So PhD teaches you to ask questions which have not been answered yet. Okay, so you are not going to get PhD by solving some problems at the end of some book chapter or something, because that is what will give you marks or maybe in the exam. But PhD is something which you will be working on the problems which have nobody has found solution to, and you have to put in all these pieces together and then find the solution. So now how do we go? What are the things that you learn here? So first is the problem solving ability. Now this ability is basically you see something which is impossible, that how you can solve such a thing. So for that, now so many of you have done trekking. Have you done trekking? Okay. How many of you? Okay, very few. All right. So for trekking, you must have you gone to Himalaya? No, right? But if your dream is to go to Himalaya, you right now just cannot go and then directly land there. You will first go to Sahyadri, or even before going to Sahyadri, you will first go to some small places here near Andheri, Vinderi, all that, or maybe near Karjat. You will do some, background check. Okay, I can do this, I can climb these small things. And then once you know, okay, now I can really take up a challenge, then you will go for very big trek. But first you will do one day trek. Morning you go, evening you come back. Then you will go for 2-3 days kind of thing just to test yourself. And then you will go for 10, 15 days, 30 days, that kind of thing. So what did you do? You have step by step went on to tackling difficult problems. The PhD will teach you something similar. You want to solve one problem, you don't directly jump and try to solve that. You put it into several pieces and then keep working on several of those. And this is the technique, or this is the ability that PhD will teach you. And this is a very, very important technique that you learn. So that is what will give you a power to tackle even the most difficult problems. So because in later life, you may remain as a scientist, you may remain into academic, or you may go into industry. You may form your ideas may form a big industry. But there also, when you are making a product, you directly don't jump onto that. You first make small pieces of that, assemble them together, and then you make a full product. So this is something which PhD will teach you. And as a result, no matter how difficult problem that is given to you, you know how to solve or how to tackle that. So that is something that you will learn. Then the other thing is intellectual grit. So this is something that you will keep making certain mistakes, but PhD teaches you patience. Okay, PhD teaches you that no matter how many failures you have, you can still continue and you can still get an answer. And this is something, so a lot of beating is, in PhD you will get a lot of beating, because you will not be able to solve that particular problem in the first go. Some people may be lucky, but it is not that everybody will be lucky. Okay, so you will have to work very, very hard to get to that particular issue. And this is something which PhD will teach you, that no matter how many failures, you have to keep trying, you have to keep improving, and then you finally make the breakthrough, and then you have optimized the processes, something, and then your things start working. You start getting the results that you are expecting, or maybe some unexpected results. You are able to make a breakthrough into this key. Yes, now I understand why this particular result has come. Now the third is global network. So in the global network, what it means is you will, I mean, you are already right now owned by, oh, great scientists, get Nobel laureates, these, that, etc. But as you work more and more into this, these people become your colleagues, okay? Because at one point, you will be considered as one of these people who are contributing with them, because they were also students like you, they were also grew out of the system, and they just happened to solve certain things which led them to Nobel Prize. That's perfectly fine. And you can also do the same thing. There is no such rule that it prevents you from doing that. You can also do it. And this is why definitely you may end up meeting them in, what is global network? It is basically you will get to attend certain conferences where the Nobel laureate is there, and you may just sit with them having a coffee and having a certain discussion. So this is definitely possible, and they will also consider you as your future colleagues or budding colleagues, etc. Because they know that if the subject has to proceed ahead, they will need young minds, and that is where you will be. See, we as humans, we have all made all this progress is by networking. Always remember. That is why we are different from monkeys or any other animals, because those animals cannot do this networking. By networking, we can talk, we can disseminate ideas. What am I doing here? I'm actually giving you certain ideas. I'm disseminating some knowledge to you people, and then you are listening to me. But some monkeys can't do this. They will just have their own things, and that's it. But this is something that we can actually connect to each other and then do wonderful things. So why certain people from other parts of the world would like to look at my work, or I would like to look at their work. So this is something because we have been able to disseminate knowledge through certain channels, and that is what is the networking. So this is something very, very important that you will see, and you will get to meet very, very gifted people, So this is a great advantage of doing this. The next is fundamental versus applied research. So this is many times this question is asked, why fundamental, what is so fundamental, and what are the advantages and what are the disadvantages. So there is something that I will now tell you. Einstein discovered this equation. What is Einstein's equation? Very famous. E equal to mc square, correct. Now, can you improve on that? Is there anything new thing that you can do? This is something which always remains forever to be like that. Okay, it will be always there all the time. But applied research, Edison. What did Edison do? He found the bulb. Are you using this bulb? Have you even seen this bulb? Maybe none of you are, your generation, the students probably have not seen the bulb. So what happened? Does it mean that Edison invented something which was useless? No. Just that it was an applied research, it had certain lifetime. Now you have LEDs and many other very advanced level units. But he started with the light bulb. So it was an invention, and it gave him a lot of money, by which he could actually build laboratories like Bell Labs, where they made further inventions. So applied research has certain lifetime, but fundamental research is a lifetime thing. Till the human civilization exists, this will remain. For example, Marie Curie, she discovered polonium. Now you cannot discover polonium again. Okay, that's it. I mean, that element is now known, well known, and it's done. But you can have applied research where Alexander Fleming, he found penicillin. Now penicillin is an antibiotic. Now right now you are getting ciprofloxacin and all the fifth or sixth generation antibiotic. So that keeps changing. But when he first made penicillin, that was a big thing. It was a big lifesaver. And then people learned more and more about that. So applied research is appreciated immediately. There are immediate rewards, and it touches lives of many. and then there are immediate gains, patterns, etc. So you get a lot of things. But fundamental thing, it is hard, but it is long lasting. So always remember that E is equal to mc square is not going to change, or any other new principles, but this is something that you will always for. So this is the advantage of fundamental research. Now, what are the questions that you will ask before you take up any problem? So first is, what is the main question that you wish to answer? The other is, why that this particular research is important. Why should somebody spend so much time, effort, money, everything into that? So all these things you have to ask yourself. Maybe when you are working, you will have to hypothesize your work. And most importantly, you should have an eye for an unusual result. Okay, so this is something that will probably catch you. For example, you know how Newton, we have a very famous story of Newton, how he discovered that. What did he do? He saw a falling apple. But remember, he was already thinking on certain problem, and then he just made a connection. Okay, because you know, apples or fruits have been falling all over the world, but nobody saw that and figured out anything. Okay, so you have to have that unusual thing for the for this result, which everybody has missed. And each material has one particular function, and that definitely you can figure this out, that different materials. So this is a wonderful material science that one can do. Now, this is a typical matrix which people show. So quest for your fundamental understanding. So one is, if you go along this axis, okay, this is very high in terms of understanding. That is, you know who this is? This is Niels Bohr. So he found atomic theory, etc. Now, from the fundamental point of view, it was very important that you should understand that. So it improved our knowledge. It allowed us to expand the knowledge further, but no practical application. While Edison already had everything ready with him, all the technology, everything was there. So he just had to, you know, make certain tricks, applied those things, and then he started making dynamos, bulbs, everything. So all electrical thing, everything he could do. So it had enormous amount of application potential. But when Louis Pasteur, he did this, so he first proposed, okay, the diseases are caused by germs or bacteria, whatever it is. It is not because of some curse of God or something like that. So he basically changed our perspective. He changed our, he gained huge amount in terms of fundamental knowledge. But at the same time, his solution was also very useful because it saved lives of millions of people. So there are certain researches which can be of fundamental nature and also can save or can be very important for the changing of lives of people. So research is basically like that. Now, where is this and where can you find such kind of a thing? So again, we go back to this Newton's thing. Newton saw an apple falling. Now you may question, I mean, here in India on the coastal line, people must have seen nariyal falling from the coconut, falling from the coconut tree. But why nobody here could think of this? Why only Newton saw some apple falling and was able to think? It is because he was already working on many of these things beforehand. He already was working on the problem of the planetary motions and all those things. So he saw moon, he saw apple, and then he thought both must be falling, but just moon is falling, but it is just moving like that. So this way he could get an idea. But why did he get that idea in the first place? Suppose he was in India, do you think he would have got it? But because he was working in Cambridge. Cambridge University was already having a tradition there. So he already had access to those previous people's work, everything. Everything was in front of him. And then he was thinking on those lines, and that is how he got it. So that destination was very important. Okay. So same way, you have to have an environment where you have people who are giving you a lot of different ideas, and then only you will say, yes, this is what I want to do. Okay, you exchange ideas and this. So where is this destination? This destination is TIFR. So why to do a PhD in TIFR in India is because we have such kind of an environment, which I will talk about. So, Professor Bhabha pursued this because he wanted such a center of excellence in India, because when he came, that time there was a war going on in Europe and he could not go back. So he was in IISc for some time, Indian Institute of Science in Bangalore, and he said we should have something which will build very state-of-the-art knowledge base, and we will have trained people, trained scientists who will later on go on and build other set of institutions. So this was a seed thing that he wanted it, TIFR to be. And Mr. J.R.D. Tata, who is a very well-known, very highly respected industrialist, he supported this idea, and they found this TIFR. So TIFR is actually at the southernmost tip of Mumbai, right next to the sea, and this is where you can just have a look when you go out. So these are the institutions of higher learning, and these are very distinct indicators of intellectual traditions. So because of our civilization was attacked over for thousands of years, all our university, all the structure, everything was destroyed by the looters. So we were basically looted. India was looted very heavily, so we didn't have money, we didn't have resources. So we had to build these traditions, and that is where Bhabha started this. We should build these traditions of these scientists, and this is how it works out. I mean, Newton, he didn't just fall from the sky. He was there. I mean, there are also people like Newton who were here, but they didn't get those chance to or access. They will never flourish. They will just go down the in the time. They will just vanish. So you had to catch these people, nourish them, and then their genius things comes out. So that is why he founded this, and you can do science by the sea. The campus is designed to inspire curiosity, as we say it, and this is, what this part that you are looking at. So this is Governor's Bangla, and then this is Malabar Hill, and then you can see some part of Chowpatty on the horizon. You can just have a look there. Today your visibility is very good. Now why TIFR? Now in TIFR, the advantage is TIFR is not like a pyramidal structure. That is, you have director, then deans, then other senior professors, and then students, postdocs, like that. So many times you have undergone this kind of pyramidal structure in other institutions. But TIFR is a flat thing. What do you mean by flat? That our director or deans may stand in the queue, the same queue for which you are having tea, irrespective of whether he is a student or any other person. Here the position is just notional, okay? I mean, they have rights and power, but nobody throws that, and there will be no separate queue for them or anything. They will all be standing right next to you, and you will have no idea. And this is very important. Why is so important? This is called flat structure, and there are no walls. So you will meet a physicist, you will meet a mathematician, you will meet, and they may have been very accomplished people, but you will have no idea that they have done that just by looking at them. And you can, as a student, can also argue with them. If you think, okay, some idea is not right, you can argue with them. Oh, I disagree with this. There is no arrogance in that, but you are challenging certain ideas. And that's a normal thing. And that is what is different. That is how TIFR is different from others. I mean, a student is able to tell the professor who has PhD, or he has many other PhD scholars who have completed their doctorates, that, oh, I disagree with this, and that person will not take it as an offense. So that is the thing that Bhabha had built here. And the other thing is, your research, you start right from the beginning. So right in your coursework itself, you will start going to the laboratories and start doing the work. Now, if you see impact by numbers, ours is a #1 research institute in the country by Nature Index, Scopus citations, whatever. And we have had first in many things. BARC was found from TIFR. Okay. ISRO was found from TIFR. How many of you know this? Kalam Saab used to sit on this mezzanine floor. Then NCST, have you heard of NCST? National Center for Software Technology. The first software technology, first softwares engineers were trained here. These used to be on the ground floor, where some of you might go there in the computer center to see this. So these institutions were found. NCBS, which is in Bangalore, anything under the sun in biology you can do there. Just like anything under the sun in physics you can do in TIFR Mumbai, you can do that for biology in Bangalore. Then you have ICTS. Anything under the sun in theory subject you can do in there. So this is something like similar to ICTP in Trieste, Italy. We have a lot of interactive classrooms. So I mean, the number of students is small, so they all can sit together, and there's a very live discussion that can go in. Then we have what is known as a West Canteen culture. This is something which is very unusual. So the ideas many times happen in the West Canteen or in East Canteen, because that's where professor, you may be sitting and arguing with a professor on something on quantum mechanics or something like that. And you can have a very heated argument over the tea, coffee, whatever that you have. So the PhD student can debate like that. So it is not that professors or senior people I have are sitting on separate tables and others are sitting on separate, nothing like that. They all sit together and you will have no idea whom you are sitting with, and you can still argue with them. So this is something what I call a flat structure. Now, what are the practical perks? One is, of course, you will have financial independence. You will get stipends among the highest in the country, so that you can solely focus on science. You can get housing in South Mumbai. So your hostels are right next to the sea. So you can take a walk even in the midnight, 2 or 3 a.m. in the morning also you can take a walk. There is no problem. We used to take a walk like that in the night, and it used to be very quiet and very nice, and you can hear the sound of those waves. It's very nice. Then you can do global travel. You can go to American Physics Society meetings, Material Research Society meetings, or many international conference of mathematical things, etc. Many things you can go. Then there are also medical resources available. You have full medical coverage and access to 24/7 library. And this library is one of the best in the country. And this is how your PhD roadmap is. So in the first year, you will do coursework with lab rotations. Then in the second year, you will have qualifiers. You can select your topic. And the third year, basically, you deep dive into that research. And then you have publications, etc. And in the fifth year, you do your thesis writing, defense, etc. So this is how overall your thing will be. Now we have Wednesday colloquium in physics every week, and many distinguished people, many scientists with different backgrounds, biology, chemistry, physics, all of them have given these colloquiums. Then we have maths colloquiums on Thursday. Again, very renowned mathematicians, world-renowned mathematicians have given the highest prize in mathematics is Fields Medal. So Fields Medalists have given talks there. Then we also have science and technology engineering talks, which are on every Friday around 4 p.m. And then we have public lectures which are held in this Homi Bhabha auditorium. So today we have very distinguished Professor Atish Dabolkar, who is giving a talk. So I urge all of you to attend that. So several Nobel laureates have given these, and very other big luminaries have given these talks here. Then we have Amateur Music Association, and which actually have called people right from Arti Anklikar, Tikekar, Sajan Bandhu, Mishra brothers. When they were beginning, they have come here and they have sung here. So this entire thing is not new to them. And we also have Images. This is a film club of TIFR. So where we used to get very exotic and award-winning films. And yeah, so that will ask you, when are you coming to TIFR? So yeah, so if you have any questions, any comments, feel free to ask me. So I have stuck to time, I think 30 minutes. Yeah, so you can ask me, you still have quite a lot of time, right? Pardon?
The branch is not available.
Yeah, chemical branch is there now. It's called Department of Chemical Sciences.
We have a talk after that. I think it's from DCS, right? The next talk is from DCS.
Entry age. So you can enter after your bachelor's, which are called integrated PhDs, and you can also enter after your master's. These are called normal PhDs. So both are. So integrated PhDs will get 6 years. The normal PhDs will get 5 years. Masters wala people will get 5 years. And we don't care whether you are an engineer or whether you are a science graduate, doesn't matter. So far as you clear our written exam and interview, you are valid. I mean, whether you are chemistry person doing physics or whether you are physics person doing chemistry, it doesn't matter. Okay. Pardon? A TIFR entrance exam is there. It is held in every second Sunday of December. Second Sunday of December, and then we have interviews in March, February, March. It is called graduate students exam. Yeah.
I have a question.
Yes.
So my question is, what do you do after you do a PhD?
Okay, so what do you do after you do PhD? So there are many avenues which are available. You can get into academics. That is one thing. You can do postdocs, etc. The other thing is you can also join an industry, because what happens is PhD teaches you, as I told you, patience, perseverance, and it also teaches you how to solve very complex problems. And industry people actually need these type of people, because who are trained to work under pressure, I mean, who are really motivated and who can solve even the most complex problems. Okay, so industry demands that. Industry wants such kind of people. So if you have a PhD from TIFR, nothing like, even string theory PhDs have gone into finance. You will say, oh, why are they not doing string theory? No, they are interested in finance and they can do wonderful things, because it just teaches you how to solve a given problem. Now they have a complete mathematical background which they can apply to the actual problems, the real life problems, and they can do it. So they can shift to anything. You can shift to any other topic once you have a PhD, because you are already equipped with this I call superpower of solving a most impossible problem into small things and then cracking each one of them. So this is a very important thing that you learn. Yeah. Then there is one more.
Thank you, Dr. Prabhu sir, for enlightened student and faculties present over here today. My one question related to not exactly the PhD, but we have the UG and PG students, those who really want to come to TIFR for short-term projects, but there are not that much positions available sometimes. So if we follow, is there any short duration projects available in the summer? Or
yeah, that's a good question. See, as you have seen that we are highly restricted in space and resources. So we really cannot accommodate too many people. It's very unfortunate. But TIFR Hyderabad, there, TIFR has a very big campus, and that is where we are expanding. So there you will see large number of these summer trainee positions, and those things will become available, because this is a very important part for the UG and PG people, because the universities, what they teach them is really, I would say that it's like more clerical type of thing, not a practical thing. So for practical thing, they have to go on job. It's called industrial training. So this is a research industry. You can look at it like that. And that training, on-job training, is really needed. That's why many of the institutions now, ICERs and all that, they are allowing their students the entire last year, that is 2 semesters projects, that you go out and do projects, whether in industry, research institution, wherever you get, you do a project. Because what happens is you get to apply your knowledge there, whatever you have, because you have been just learning theoretical thing, not a practical thing. And see, it is also not their mistake, because we are really crunch for resources. I mean, there is not, we are only spending 0.7% of our GDP on research and education. So that is why we are really lacking a lot of resources in the colleges and universities. And that is why they are not able to actually train them on those. Because I get students, many of them, first year, I teach them experimental physics, and many of them have not even seen, they have heard of pumps and all that, but they cannot distinguish between vacuum pump, water pump, and also BNC cables and all that, which are now very common. But there is a fair amount of lack of resources, so there is a lack of knowledge, but not lack of intelligence. They are very intelligent, very knowledgeable, but are not really exposed to those things. So this is a very important point. We also have Vigyan Vidushi that we have started, and this is exclusively for girls. You can also tell them more about that. Kiran will be able to tell you. But this program is meant for all the girls students who are interested in pursuing career, because if you see STEM, that is science, technology, engineering and mathematics, we are seeing very less number of women participation at higher level. So this is like 50% of our population is really not coming into the production thing, because country's strength is and intelligence, it is equally divided. It's not a one particular gender's what I call monopoly or something. So we are trying to encourage girls to take up careers in science, engineering, and therefore this Vigyan Vidushi program is given, and these applications I think come in January or February, because in May and June, 2 months, 3 months, they have a very extensive training of different courses, and they have visits and all that. So I would encourage all the girl students to apply for that. Those who are just in first year MSc, or they are just finishing their BSc, then you can definitely try. Huh? Last week was the Vidushi. Okay. So you just look at our website and check.
So, sir, I have been doing my last year project, in my bachelor's BTech. So I wanted to know, is there any interim opportunity at TFR, all the campuses in general? I'm just asking a general question, not specific to TFR Mumbai, but are there any interim opportunities so that we do research, get to know the TFR's culture, and then know whether we are the right suit for TFR PhDs?
Yeah, there are many centers TIFR has, several centers. So depending on your interest, so you are BTech in what topic? Biotechnology, right? So NCBS, places like NCBS, so there you can definitely write to them and ask them. But you have to write to those specific professors who are working on those, and those topics have to match your interest. And then you can ask them, and they will tell you if you are ready, if you are motivated, then they will definitely will like to have you, because it's a very competitive field, and you really have to be motivated to work there. Otherwise, you will get frustrated. If you are not motivated, then it will generate a lot of stress for you, and then it can be very frustrating. So therefore, you have to be very, very motivated yourself. So that is a very key thing that I always tell the students. You must be motivated in doing whatever. Then what happens is, whatever work you are doing, you don't feel you are doing that work. It is basically, it's like a hobby, you get joy out of it. Otherwise, it creates a stress. So this you must be very clear in your mind. And nobody else can tell, only you yourself can tell whether you really like doing that particular work.
Sir, you mentioned that in Wednesdays and Thursdays, we have different seminars and events where there are
Colloquium.
lectures from mathematicians and all the things. So are the students from outside of Mumbai allowed to attend those?
You are allowed to attend, but they are also on YouTube and live. So you can watch them on YouTube also. So you don't have to really travel all the way, spend 2 hours, come here, go back. You can still watch it there. And they are also available afterwards also, you know, because YouTube you can always watch. Suppose the live thing you are not able to watch because of some exams or your practicals or something, you can later on also watch.
So how do we get the schedule for that, sir?
You go to TIFR website. See, all my slides have TIFR www.tifr.res.in. So you can always click on that and get the information of the latest. Yeah, department specific things also. You will see all the different departments have their web pages. You can go to each individual professor's web pages to see the activity. Everything is available. All information is available on the web page. And TIFR, this is the main TIFR web page where you will see Mumbai campus and many other campuses also. So campus wise also you can go. So you can hear their Hyderabad wala lectures or Bangalore wala lectures also. So now it has become very easy. Yes.
Yes, hello, sir. Sir, I have done masters in physics, and I don't know, I was willing to do PhD here, but I have so many friends who are doing PhD currently, and they have spoken about there is no work-life balance, and there is so much stress, struggle, and everything. So after seeing that, like we are little bit demotivated about it. What would you like to say? Is there a work-life balance?
Okay, work-life balance. Yeah, see, I was telling him it's a very demanding field because research is quite demanding. So you have to really like it. That is one part. And once you like it, then working hard will come natural to you.
I mean,
But
it's not coming natural to
Kiran,
them.
Well, being in my final year, I can tell that sometimes it varies like time to time. For example, if your instrument is working, you would, and things can happen. So, for example, all the instruments are working very well, and in the monsoon season, the humidity goes up to 99%, and it will stop working. So, and that's the problem with being an experimentalist. Like there are 10 instruments and they will be, if they are all working and your data is coming good, I have no issues staying overnight and taking data because next day it might not work. But that also comes with this flexibility that I have worked all night, so I might not come next morning and I can just take a leave, and that's not a problem. So yeah, I mean, it's your call. And it gives you flexibility to work whenever you want, and that's the freedom I enjoy.
I mean, are you
Yeah,
sure
fine.
about this just because, I don't know, maybe your professor is sitting beside you, that's why you're saying
No,
this?
no. She can give a completely opposite thing. There is no problem.
He's not going to sign my thing. I don't mind that.
I would
Yeah.
really like if you're honest. I mean, if you are, then that's great, but I have heard opposite from my friends, maybe.
Yeah, but
Working here
it can be really stressful at times. I admit that, but then looking back at the time, I really enjoy that I struggled a lot, and now that I'm here. Yeah, but definitely test your patience. So if you're going half-minded into the PhD, don't go for it.
Don't
If
go.
you are like prepared for everything, like I love science and I'm ready to do it, then only go for it. That's my advice.
So you have to see what your passion is. This is very important because PhD is just not for the degree. And especially in TIFR, it is not that because TIFR is a different place, I told you. See, you may be a topper in your college or whichever university, whatever it is. But when you come to TIFR, you will see a lot of such people around you. So you may be like a Sher or Sherni in your that thing. But here everybody is a Sher and Sherni, you know. So you have to really fight with because then you don't have a special place. So many times people find this psychologically unacceptable because everywhere their place they are all like Arey, great, and here nobody is giving you that kind of because you are just like anyone. So this is a big difference. Psychologically, it can make a big difference. two people. So that is another thing that can also stress them. So just be aware of that. So that is why I was telling him ki follow your heart. If you really like, you are really passionate about doing it, then only get into this. Otherwise, you will not be successful and you will be stressed out as everything that you said that can happen to you.
Yeah. To add is like when we are doing our bachelor's or master's, we have regular exams, we are tested regularly, and like we will get good marks, and that's really stand out, and that gives us motivation to work harder. But in research, it's not like that. For starting 1, 2, or 3 years, you'll be building your basics, and you'll be understanding how different components or different things work. And then after 3 years or 4th year, you get a research paper. And up to that time, you're just you might just be frustrated, like I'm not doing anything. You might think that, but actually you are learning, and the learning phase is so slow that gives you frustration. Otherwise, if you think that you're learning, it takes times, then yeah, it can be less stressful.
Okay, thank you.
Yeah. Any more questions? Yes.
It's not exactly a question, but like I'm a chemistry major student, but I have a lot of interest in interdisciplinary, like chemistry, physics, and maths. And I did a summer internship under a physics prof. But the thing is that when applying to different physics profs, I do not have any coursework related to physics. So I think it's a big con for me that they see that I do not have any physics coursework. How do I?
No, but many times these are interdisciplinary things where you make breakthroughs, because when you are as a chemist, you are taught to think in a certain way. As a physicist, you are taught to think in a certain way. As a mathematician, you are taught in a certain way. Now, the thing is, when you enter into another territory which is unknown to you, you are not biased by anything. So, and whatever thinking that you have, you can actually start applying, and it can actually give you a different perspective altogether. So, many breakthroughs have happened like that. That is why interdisciplinary thing is very important. And because what will happen is, suppose you start taking all the physics courses, eventually you will start thinking like that. And then you will say, okay, chemistry is not like that, I will think in that way. So don't do like that. Learn it the way things come to you. And suppose certain things are to be learned to understand things, just learn only that much. You don't have to learn each and everything. You don't have to undergo the entire course of physics, or entire course of chemistry, or entire course of biology. Then you will not be able to contribute anything. That I can guarantee you.
What to stand out to like if I'm mailing a prof, physics prof or a maths prof that I want to do some work under them, what can I do to stand out as a chemistry student?
So you have to see what you bring on the platter to them, because they will see what are the expertises that you are bringing in. You may be very good in synthesis, you may be very good in growing certain materials, etc., which may be useful to them. Then they will say, okay, look, you are able to grow this. While our students, physics people, are not really into that. They don't know how to mix those chemicals in what proportion, whatever. But that is where you can start making your own contributions, and they will teach you, okay, if you have made this, these are the properties this particular material has, and let us now study those. I'm just giving you one such example. So such things can happen. Now, if there are some MXenes and there are many other new materials which have come up. Now, those are synthesized by chemists, but they are very useful for the physicists, because they see, oh, there is a lot of many things that we can do out of this. But the chemists had no idea. I mean, this is a complete different expertise, So there are a lot of such things which happen.
Good afternoon, sir.
Good afternoon.
I wanted to ask that as a professor, you come across many students through your entire career. What is that one quality that instantly makes you think that this student might do something extraordinary?
So that is his or her motivation, dedication, and passion for the subject. That quickly tells you everything. So, and it is very clear. So it doesn't matter your performance in the, mostly your university exams, they test your memory. See, it's a memory test. So you get 90%, 80% is basically out of 100 things, you remember 80 of them or maybe 90 of them. That's all. But that doesn't mean you have understood that or whether you liked that subject. That comes when actual problem is given to you and how you tackle that, with what passion and intensity you tackle that. That tells you that is what actually distinguishes you from the other ones. So, for example, if you know Gukesh and all that, are you following sports? Huh? Now, those people, oh, you play chess. Nah, so, if you challenge Gukesh at 2 AM in the morning, he will still play with you and beat you. But if you catch some other random guy and say, "Arey, chalo chess khelo to so jao yaar," he will beat you up. Because that is a big difference between Gukesh, because he is like that because he has a passion for that. It's not just that he's doing it for just earning money or something. He has a passion for that. And those passionate people have no time limit that way. He may be tired, bodily he may be tired. See, for example, Sachin Tendulkar, he used to be so passionate. His whole thing he will be tired, but even he is feeling sleepy, he's still enthusiastic to play. So his aunt, Chachi used to feed him, ki, nahi, you now stop playing, you eat something and then go to sleep. Otherwise, you will not do. So that is the kind of passion or madness. That is why they could achieve so much. So that if you have, you can do anything in life. You will achieve great things in life. So that passion is most important. And that nobody, no exam or no nothing can test that. That comes only when you start working. And you yourself also realize that. Then you don't get stress. You get joy.
Any more question?
Pardon? Okay, he's asking whether like CET, NET, NEET, I think. So that is for after 12th. So what you are probably referring to is NET, NET and JEST and all that. So we do take students. Yeah, that is called NET, NET, CSIR NET exam, or you also have GATE, GATE, Graduate Aptitude Test of Engineering by IITs. Then you have NET, National Eligibility Test from CSIR, and JAM is again for IIT, for MSc. And you also have this JEST, Joint Entrance Test. So all these, we also see the merit list of these, and those students are called for interview. The first merit 10, 50, whatever, they are also called for interviews. So we hold those interviews. So that is no problem with.
We request you to raise your hand to ask questions, and we'll hand over the mic, then ask question, because we are also live streaming this. So hearing the question will also help. Yeah, so please go ahead.
So, sir, I am right now in junior college, and the system I am in right now is preparing for NEET and JEE. So, beside that, they are saying there is no future in science. But I want to opt core sciences. Like I'm preparing for entrance exam for research institute, basically. So
right. So you want to do research in science, then there is ICER's.
Yeah, I'm preparing for ICER aptitude test.
Correct.
So basically, people are saying that there is no future. Like you will end up being a professor, or you will do PhD and nothing after that. But what will I aim right now to become? Like after MSc, what should I aim for?
So see, your interest will keep changing as you go on doing more and more, as you learn more and more in specific courses, depending on who teaches you what subject, what kind of projects that you happen to do in which labs, etc. Your interest will keep changing. So your perspective also keeps changing. So right now at 11th and 12th standard, it is your perspective won't be that big. So you can if you are very passionate to do science, then definitely IISER will be a very good choice. And once you land up in IISER, then you see all the different activities which are happening there. There are very good professors, very good labs there, very good teaching activities. So just like IIT is for engineering, IISERs are for science. So you see that, and then only you will be able to make the call, because right now it will be premature to say anything, because after your MSc you may want to start up a company. It's possible, because you will say, oh, there is more scope to do that, there is more growth in that. Your interest may change. That's all right. There is nothing hard bound that you have to do this or you have to do that. There is nothing like that. It's very open, very flexible, and you should keep it like that only. Don't just narrow it down to one particular thing. So once you leave it open, you will see a lot of opportunities around, because things are changing very fast. So 5 years down the line, maybe there will be many more other avenues which will be available, which right now we cannot even think of, which you may think that, oh, you have now got that particular liking for that or particular passion that you have got it to do that. Yeah, nothing wrong with that. So leave that, as an open option. That is what my advice will be. Yes.
Sir, Ivy League is considered to be the series of, the most prestigious colleges abroad. So if we are talking about 3 parameters, environment, financial situations, and opportunities. So what will be the comparison between the institutes of India like TIFR, IITs, and the institutes over there, which are the most prestigious over there?
Okay, so why they are so prestigious and why they have achieved that? Now, China has come up with that, and pretty soon you will see Chinese institutions also coming up like that. Now, first thing is, we are spending 0.7% of our GDP. You know how much US spends? 7%. Okay, so it is already 10 times. And how big is US economy compared to us? How much factor? It is almost 20 times. So if you multiply this, the factor comes to 200. So now you see, they are sitting on something which is 200 times bigger than what we have. Okay, so there is no practical no comparison. Why they are going to do well? Because they have huge amount of resources. They can hire large number of people. They can get them trained. They can buy out people. So that is what China is doing. What China is doing is, they are buying out these Nobel laureates or very people who have achieved quite a lot. They just bring them there. They tell them, okay, take this institution, build whatever, and help or guide our professors or assistant professor, whoever. Take as many students as you like, and they are paying millions of dollars to them. So this is how you can build the tradition. So that is what I was telling you. The destination is very important. We have built TIFR to be like that we would like to build these traditions, because for thousands of years our traditions have been completely destroyed. So we have to rebuild all those things. So it is not that we lack in intelligence. It is just that we are lacking in resources, and we have to build this. So we are actually, I would say, we are manufacturing scientists. When you are doing your PhD, you are going out, you are actually manufacturing them. Okay, so you have to manufacture those. Now China is also doing that, but China is, because they have huge money, they are actually buying them and putting them and say, now you help our students, our teachers, whatever, and that is how they will manufacture those. So their quality, their everything will increase, because China is spending 3% of their GDP, which is 4 times more than us, and Chinese economy is 5 or 6 times than us. So they are 25 times bigger than us. So there, anybody at my level will have 25 times bigger resources than here. Understand? So that is why Ivy League is called Ivy League.
Intelligent people who are in India should stay in India and develop India by staying here. And the second perspective is, they should go abroad, learn all those things, and get the resources from there. So which is more correct? Which is
no, both are having their own advantages and disadvantages. See, once you have enough resources within the country, then they will say, look, we have got so many resources, why don't you come back? So it becomes attractive to come back for them and then start setting up things here.
Right.
So it is just a game of economics, money. It's a game of money, nothing else. So you see China example, no? So Chinese are offering their PhDs who are working there large amount of money, large amount of space, everything, resources. So they are naturally coming back and they say, okay, we would like to develop it here. So like that is what we have to do. That's all. It's a game of money.
So that depends on the student, sir.
Yeah.
Hi. So unfortunately, we have to close this session because we are getting late for the next talk. You obviously can write to Professor Prabhu if you have any more queries, and you can reach out to any other research scholar in TIFR. In TIFR website, there are like email addresses on all those information are available, and we welcome your queries through emails as well. I would request the audience to come in front of the fire and leave the chairs for the senior citizens and people who are in need. The younger people, please come closer to the fire, and yeah, we will start the next talk. Please.
All right, has everyone settled down?
Right.
Yeah, you can just sit here. There's nothing.
Just remember that if you cross this area,
Then this
the
one.
voice howls. So
I have to be there.
here. And also, if you go beyond this, the light will come on.
Yeah, that's fine. So is there any point?
That is the point. Thank you.
Yes. Yeah. Okay.
Yes. All right. So, yeah, that was a really amazing talk. It gave us insights about what happens inside TIFR, general. Now, we had technical talks before that, and now we are again going to jump back to the technical talks. So our next talk is going to be by Professor Debashis Das. He is a faculty in the Department of Biological Sciences. He works on molecular mechanism of intercellular communication. And I think this is not related to it, but I mean, molecular mechanism, intercellular communication, and life speaking through molecules sounded similar to me. So, okay, all right. So the talk is when life speaks in molecules. So over to you, Debashis.
Yeah. Okay. I hope everyone can listen me. Okay. So for next 30 minutes or so, I will be telling you some of the research work that we have been doing in our lab for last couple of years. Now, I am sure all of you have at least thought of during your academic journey that how life form has emerged, right? At some point. So if I have to kind of summarize this, essentially, life forms, the Earth probably formed around say 4.5 billion years ago, and from there, say, after some stabilization of the hydrosphere, a very important step happened, what we call that as prebiotic chemistry. What it means is essentially formation of some critical molecules that give rise to some really important biomolecules that ultimately led to the formation of the first cell, right? And then obviously the cell divides, and then the cells essentially diversification of life happened, and then so on. So now if I go one step ahead and ask this question, the molecular evolution, right, from the real actually cellular evolution. So I basically highlight this step from where the important biomolecules actually assemble together and they give rise to this first, say for example, cell. Now, if I have to now go into the biomolecules, you can think about RNA, DNA. All of you have heard about known. These are very known biomolecules for you: RNA, DNA, protein. Obviously, carbohydrates are there, phospholipids are there, and so on. I have not listed all of them here, but among these three biomolecules, if I have to, okay, so I'll be actually talking about these biomolecules today, so hence I listed them here. Now, before going there, I ask a simple question: is if I have a say hat or umbrella or say car, how do you think that these are actually not living and these are living objects? Is there a can you yeah, please. Yes, very nice, great. So that is one of the, that's exactly where I am actually coming. So one of the real kind of sign of life is essentially an entity that can actually produce its own copy, right? It can actually self-replicate and give rise to its own. So that means this is one of the fundamental feature of life. Now that means cells need to do some function in order to essentially give rise to either replication or this kind of critical phenomena that we see for the to keep it live, right? Now the question really is in the molecular term, not in the molecular term. If I now have to ask the same question, that what makes cell to perform these functions essentially, among this RNA, DNA, protein. DNA is certainly not a functional molecule. This is a storage molecule which actually stores information. Which is functional is essentially RNA and protein. These are the two molecules that are the workhorses of cell. If I go into the chemical composition of this structure, these biomolecules, these are nothing but polymers essentially. And all of you have heard about polymers, right? So RNA is essentially polymer of nucleic acids, right? 4 nucleic acids assemble or joins in a different sequence and give rise to this RNA polymer, right? The same way, protein is essentially amino acid polymers. So at approximately 20 amino acids, they assemble together in different sequence. I mean, it's a really different sequence, and that gives rise to a kind of a polymer. We call that as protein polymers. Now the question really is, what makes them functional then? I can synthesize them in test tube, right? I can synthesize these very well in a test tube, but what really makes them functional? What makes them functional is essentially one of the main features is these biomolecules can actually assemble these different regions of this biomolecule come close together and can form different structures in three-dimensional space. And that actually gives rise to the functionality of these biomolecules. So yeah, that is what is shown here. Now, what really happens is, say for example, in case of protein, some chemical and physical forces, they actually bring these different regions of this polypeptide together, like say for example, ionic bonds, say for example, hydrophobic interaction, hydrogen bonds. They actually, these kind of interactions, they bring these different regions together, and that is the basis, chemical basis by which this three-dimensional structure actually forms, which is functional. Okay, now these are typical examples of some proteins. One is this is I just gave kind of a random examples. These are restriction enzymes which interacts with DNA, and this is proteasome complex. Is a multi-protein subunit complex which actually degrade proteins. This is a protein that is present in the plasma membrane and involved in the transport of some ion molecules across the plasma membrane of cell. And this is a kind of a molecule that is involved in antibody immune regulation, which is another important aspect. So now in this way, a typical human cell contains approximately 10 to 12,000 different unique protein structures. It's an approximate number, but that is what what is the kind of an estimate you can think of. Now you can imagine if that is the case, then how much complicated it is that in 10,000 or 12,000 different ways these sequences are organized and folds that give rise to these unique functions they are actually doing within the cell, and that keeps them actually live, right? So now the question is how that happens. That's the big question. How and how to trace that? How these structures are forming, and I can trace the formation of these functional structures. One of the simple way that people have been doing is you take this for the protein. You take this. That's what I'm going to tell today for the protein structure formation. You take the protein, you denature it. That means what you are doing by denaturation. I showed you some of the physical and chemical forces, right? Ionic bonds and hydrophobic interactions and so on. You're adding some chemicals. You're actually disrupting all these interactions. That then and making it a linear kind of an unfolded structure. You can imagine, right? And once that happens, then what you do is you slowly take that denaturant out from the reaction media. And while you are doing that, you trace the reformation of this folded and three-dimensional structure. That is using various different physical and chemical techniques to do that, and that is what people have done. And in fact, the one guy who got Nobel Prize on protein folding, Anfinsen, actually did this measurement long back. So now this is how you can understand how this structure formation happens in vitro. In vitro means in test tube essentially. But when I go inside the cell, then it's a little different story. It's not exactly what happens, what I showed now. Inside the cell, you have to consider ribosome. Why ribosome? How many of you have heard about ribosome? I guess all of you have heard about ribosomes. Ribosomes are essentially protein biosynthetic machinery, right? Where the amino acid polymerization occurs within the cell. So and once it's a huge megadalton complex of RNA and protein. There are so many proteins, like say simply bacterial ribosome contains 31 ribosomal proteins in the large subunit and 21, almost 50 or 52 proteins and 3 big RNA molecules. That makes it really a 2.5 to 2.6 megadalton molecular weight. So these big complex is actually involved in polymerizing amino acids. And what happens is then it comes out of the ribosome and it folds, either folds or misfolds. Now when I use the term folding, it's a very generic term. What I explained to you and what I am actually focusing on, when I say it's a generic, what it means is, say I said like a totally unfolded structure, right? If the two regions of that unfolded structure coming together and I have a way to trace that, that is also a folding. But for cell, that doesn't matter that much. What matters is the final structure. What is actually functional? So that means for us here, what we are actually focusing on is how the functional structure forms, so the final functional structure forms. So now this is the, we are fortunate now that the ribosome structure has been solved in great details. What it means is we now know in atomistic detail how these different proteins and RNA assemble together to form the ribosome. And thanks to 3 Nobel laureates, Ada Yonath, Venki Ramakrishnan, and Tom Stays, who actually solved these RNA ribosome structures. And this is essentially a cryo-electron microscopic structure of ribosome, a small part of ribosome, which is actually the active center of it. That means this is where this amino acid polymerization is actually occurring. And once the amino acid polymerization occurs, this nascent polypeptide comes through this peptide through a narrow pathway, we call that as peptide exit tunnel. And so the length of this tunnel is essentially 100 angstrom long, and the width is around 6 to 10 angstrom. That means what is the bottom line is a nascent protein, means newly synthesized protein, after the peptide bond formation is taking place here, when it is coming out, approximately 30 to 40 amino acid remains in an unfolded conformation when it is traversing out of the ribosome. So it's a situation like this happens when the synthesis and release of the polypeptide happens through the ribosome. So this is where so basically this is the direction of synthesis. When this amino acid polymerization occurs, N terminus of the protein has started forming a three-dimensional structure, while its C terminus is still inside the peptide exit tunnel and unfolded. And then at the last, essentially, this is we call that as a termination complex, where the full-length nascent polypeptide stuck at the last p site tRNA on the ribosome, and from there it is coming out and coming out into the medium, and say for example into the inside the cell, and becomes functional. So the question that we ask is how comparable these two structures, or rather at what point during the biosynthesis a protein attains its functional structure is our kind of a current one of the project that we are working on. So what we do? So first thing, we have to actually choose a test protein on which we can actually study this. So the test protein is GFP. GFP is a green fluorescent protein. I hope that many of you have heard about GFP. This protein has been isolated from jellyfish by a Japanese scientist a long back. And the reason for taking this protein as our test protein is our kind of a ease of doing experiment, because within this protein, these three amino acids, tyrosine, glycine, and serine, they form a very nice structure. We call that as chromophoric structure. The speciality of this particular structure is it can absorb light at certain wavelength and emits at another wavelength. What it means is you can actually get a green color. So you can actually see. So that means the formation of that color, when I measure in that wavelength, is my score for the folding of the protein, or the overall functionality of the protein. Because of that, we are using GFP as a test protein. Okay, so now this is a typical spectra of a purified GFP. This is excitation, and this is an emission spectra. This is a wavelength, and this is the intensity, fluorescence intensity plotted. So what you can do, what I said is you take before already, that you take the GFP, you chemically unfold it, and using some chemical denaturant, you make it linear almost, and then you start to take that denaturant out of the medium, and what you see is this is the fluorescence with respect to time. When you plot, you see gradually that GFP fluorescence is coming and saturating. Which is a typical experiment that people have been doing with the purified protein. But that's not what our interest is. As I said before, our interest is here in the ribosome, in the nascent protein, right? So how within the ribosome, when the protein is synthesizing, and at the last stage, whether it is functional or at what stage it becomes functional, that is our interest. So we have an assay in the lab where we can specifically isolate these complex where the GFP is bound at the last p site tRNA on the ribosome, and it is not released. We can actually isolate that from all other reaction mixtures. So but the first thing you have to really show that it is GFP is there. So the proof is this is an immunoblot, Western blot, where antibody specific for GFP will recognize the GFP in the termination complex, and you don't add DNA. Essentially, no GFP is synthesized, so there is no DNA. So you actually confirm that your GFP is there. Now, when we confirm that, you take that complex and now put it in a fluorimeter. Fluorimeter is the machine that actually measures the fluorescence intensity, right? So when you add it in the fluorimeter, and then you add some factors that will allow the protein to come out of the ribosome. So which is I call it as a puromycin. You don't need to necessarily know the mechanism or anything. Just call it as a puromycin, and and this. So now when you add that, this is the black trace. You see the similar kind of thing that you're getting in a chemical unfolded refolding thing. In the same way, you are actually getting this GFP fluorescence appearing. But and what happens is when you mutate, when we are doing this experiment, a very interesting thing we observed is at the 0 time point, when we did not add any such factor at all, we observed a huge amount of fluorescence. Why would that happen? So this black line is where I have added factors to release the protein outside the ribosome. But even if I don't add that factor, I see a huge amount of fluorescence. This should not be the case, right? I should actually allow the protein to release and then it will be functional. So why it will be the case, why we observe that? That's a very simple question we asked. Is it like we have done some mistake? So that's exactly what our starting point was. And interestingly, why it is not changing? Okay, yeah. So interestingly, when we mutated, I told you that in GFP these residues are important for this green fluorescent color, right? So when you mutated mutated means you change the amino acid responsible for giving this color. When we mutated that, we did not see that 0 time point fluorescence. That means the initial fluorescence that we observed is now gone. So why this is happening? That was the question. The 3 possibilities can happen. One is either the protein that we are thinking that hasn't really released and on the ribosome somehow got released, and we don't know it. So that is one possibility. Second possibility is that the protein somehow got released but yet bound to ribosome and giving activity, because that region is now out and nothing really prevents it to form the interstructure, but it is stuck on the ribosome, can give activity. That's also possible. And the third possibility is it hasn't released at all. It is still bound in the C terminus and giving somehow activity. Now the question is how we test 3 things, right? So one simple thing we have done is we took this complex to check what is going on and run it in a gradient, sucrose gradient. What is gradient? Gradient is essentially you run different percentage of sucrose in a tube, test tube, right? And what happens is based on the molecular weight, which is the heaviest will go in the bottom and the lightest will remain in the top. When you run it in the ultracentrifuge, it's some speed, right? So when you have done that, what we observed is and this is and then what we do, you measure absorbance. Because the ribosome is an RNA protein complex, you measure the absorbance at where the RNA absorbs at 254 nanometers, the wavelength for the RNA. So it's an indication that some ribosomal particle or the RNA protein particle is there. Essentially, you think in that way. That is plotted in y-axis, and in x another y-axis in parallel we plotted the fluorescence. So we have a machine where we can actually parallelly measure both the things. And in x-axis, essentially it's a distance from the bottom, right? You are taking different fractions after running into the test tube. And what we observed is in the 70th fraction, which is actually the heaviest one, where we got this green fluorescence coming from, and the 50th, but very less is coming from the 30th. When we add that release, the factors that are responsible for releasing it, or the allowing the protein to go out, then you see there is no such fluorescence associated with the 70th now. So that suggests that most likely neither this or not this. It is actually this. Why? Because the factor that I'm talking is actually can only act through this conformation, because that factor acts here in the peptidyl transferase region, not in any other place. Hence, this is most likely the conformation where actually it is it is, it is there, right? Now, okay, so in what is happening nowadays is not like one technique is not sufficient. You have to show in multiple different ways the same thing. So another technique we have used is called fluorescence correlation spectroscopy. Don't get scared about the term or anything. Just remember that this technique differentiate between essentially a heavy particle versus a lighter particle. That means through diffusion. My ribosome is a megadalton complex, it's a heavy particle, and GFP is a small, tiny particle. If it binds to ribosome, that means if I can measure the diffusion of that from a very small, tiny detection volume, GFP will definitely diffuse much faster compared to that of ribosome, because ribosome is a heavy particle. That's all it measures. Is it clear? It's essentially diffusion. It's a heavy particle from a small volume. It will diffuse much slower compared to that of a small particle. So when you did that, and this is a kind of a graph you get, you don't need to go into the x and y axis, but just show that this is essentially we measure a kind of self correlation with time. So the black is the ribosome bound protein, and the green is free protein, which are different. That is good enough information for you. And when we have done a lot of mathematics and then quantified the diameter. From the diffusion coefficient, you can actually calculate the physical diameter. Now, in that from here we found that the TCGFP, that means this ribosome bound GFP, we get essentially the ribosome diameter. But we are measuring a fluorescence. Measuring a fluorescence, getting the ribosome diameter. But in free particle, free SFGP, obviously you get the free GFP diameter. We added those release factors that release it. Now we get more and more population of the free GFP compared to that of ribosome. That again confirmed this is essentially the structure that we are actually talking about, where the C terminus is bound to the ribosome. Okay, so now the question is how it is possible. We got really very puzzled, because if you see the GFP structure, essentially this is the you are actually talking about this red entire one last beta strand, one region of the protein is out within the tunnel, within the ribosome, and they cannot really go and associate with the remaining structure here. So still we are getting a GFP fluorescence. How it is possible? Does that mean that region is not required at all for the protein to give some that color? So when we tested that, we deleted that region. You can do it and delete that region and try to express it and see the fluorescence. When we deleted that, we didn't even delete the 30. We just deleted 15 to 16 amino acid from the C terminus, and it is non-fluorescent. Now I want you to give little attention to this 2-4 construct, where we deleted around 16 amino acid from the C terminus and try to express within the cell, or even in vitro is of the ribosome fluorescence. And now let's see what happens on the ribosome when you are trapping it on the ribosome. When you are trapping it on the ribosome, we see that this 2-4 construct is now giving fluorescence. That means essentially on the ribosome, it is helping the protein to attain some kind of a this higher order structure formation, and probably ribosome is helping to kind of give a kind of assistance to fold the remaining structure. Now how it is possible? Obviously I will not go into too much detail. A very simple experiment we have done, I tell you, is we now mutated some of the residues, like changed the amino acids which are present within the exit tunnel, which is unfolded, I told you, and that allowed the protein to this 2-4 construct, while even if it is on the ribosome, it is non-fluorescent. So looks like what is going on is there is people used to believe that this pathway is a kind of a passive pathway. That means it doesn't have any role, because this region is anyway unfolded. It can only associate with the remaining part once it comes out of this narrow pathway. But that's probably not true. while it is on the ribosome, probably there is a functional connection going on, what we call that is allostery, to be more specific, dynamic allostery, that actually allows this structure formation. So I will stop here. Essentially, what we are trying to, what we learn is essentially ribosome, what is known for the peptidyl transferase action or the amino acid polymerization, probably have evolved with another function where, in addition to peptidyl transferase or the amino acid polymerization, where it can act as a folding, protein folding kind of a chaperone as well, that assist in folding of the nascent protein. It not just polymerizes, allows the formation of the, or the synthesis of the polypeptide, it also allows to fold it in a particular conformation. And there are a lot of, if this is true, and if we can proceed further, it has a huge therapeutic benefit. The reason is we can now make a protein which the function of which is the function of the protein is of our interest by just mutating it and then knowing their interaction with the ribosome. Okay, so that has a huge implication in biotechnology and a lot of other kind of field. Okay, this is my lab. I'm thankful to all my students. This particular these students are essentially protein folding gang who are actually doing all these nice works. I'm thankful to all of them. I'm thankful to all TIFR colleagues and funding sources. Thanks. Please, questions.
We request you to raise your hand if you have questions to ask Professor Das.
No.
Do you have any questions?
Nobody understood. Okay.
That means it was a wonderful talk. Everyone understood everything.
Yeah, go ahead.
Can you talk in onto
Yeah,
that?
this might not be directly related to
Yeah,
the
yeah,
talk,
go
but
ahead.
it's to do with protein folding nonetheless. I think 2 or 3 years ago, some people in AI they used AI to figure out something about folding proteins. Can you tell us something about that?
So look,
What was that exactly?
Yeah, so that is essentially an algorithm that can be used to predict a protein structure. Suppose what I said at the beginning is, look, it's a polymer. It forms and folds in a particular structure that is giving you the functional form, right? That's a functional form. Now, if I give you a kind of a random structure, random sequence, because it's a 20 amino acid, right? Say, for example, I have a 200 amino acid long protein. The 20 amino acid can be arranged in so many ways. Can all of them give rise to this folded structure which is functional? No. That is exactly what they have done. But that is not sufficient to explain what happens within the cell. By knowing that, it is good advancement for the protein engineering, but that's not going to help that much within the cell unless we know what happens within the cell, how this thing, what they observed in, say, for example, in silico, is actually cell is doing that. When you know this, how cell is doing that, then you can tweak and do all this engineering within the cell and really kind of do. Otherwise, it will be a very random thing. Is that clear? Okay. No more question?
Any more questions? So, if not, let's, yeah.
Hello, sir. So I'm doing BSc Biotechnology currently. So I wanted to ask if a particular research project is being done. If I want to be an intern or I want to be working here, what could I do here? Like, how do I contact?
There are many BSc like undergrads, they do intern in all our labs. So you just have to directly write to the PI, but only request is write little in advance, because what really happens is we have very limited space, frankly speaking. So that's the only limitation. Otherwise, you are most welcome to come and you can contribute to the lab. And another thing is, try to get little more time. Because in biology, unless you have at least 4, 5 months or 6 months, you don't get anything done. You will see it, but not really will, assimilate something that, so that, that will actually, you go with something. Keep that in mind and you can write to the PIs. Yeah.
More questions? Are there more questions? If not, let's thank Professor Debashish Das for his wonderful talk. So now I would like to interest you with quizzes. So let's check how scientifically aware you guys are. And if you can answer those questions, we have certain goodies, even TFR logo t-shirt for you guys. So are you interested? Yes. So do you want harder questions or easier? Okay, let's see. So yeah,
Not this one.
not this one.
So here's our first question. What do we call a liquid that flows upward against gravity when cooled to near absolute zero?
Your name and answer.
Ayush, I think it's superfluid. Like I know helium has this property. I think the term is superfluid.
Yeah, yeah.
Thank you, Ayush. The question answer was right, and we give a chocolate to Ayush
No, we should give a t-shirt.
and a
I think.
t-shirt.
Yeah.
So yeah, so Ayush wins a t-shirt. So let's see what's the next question is. So all of you are comfortable in English, or should I also speak? कोई क्लास 8, 7, 5 का बच्चा है जिसको हिंदी में भी बोलना पड़ेगा?
Wow.
Yeah. So which famous 19th century chemist invented dynamite?
Ask it without mic.
So-
Let's see, because there are a lot of hands.
So we will request you to whisper the answer. Yes, yes. I mean, so we are. Alfred Nobel. Alfred Nobel, and many of you have got right. So we'll distribute some chocolates for it. So are you up for the next challenge? Rudro, यहाँ पे. So yeah, hydrogen smart skin is inspired by which animal's ability? Okay, so I see couple of hands raised. Let's give a chance because
Amphibians, like amphibians, frogs.
answer is no. Okay, so the next attempt.
A dolphin.
Dolphin. No. Snakes. No. Anyone else? Earthworm? No. Hint. So this answer, the answer disqualifies. You have to follow the etiquette of the quiz. You have to raise your hand. Don't shout the answer. Otherwise, you lose the prize. So raise your hand. Yeah. Yeah. Okay. She actually gets a chocolate because she followed the etiquette. No. The answer was shouted. Next time. We have a couple of more questions, so don't worry. You will get many chances. So yeah, let's move on to the next question. Are you enjoying this?
Okay, no.
Are you excited for the next question? Okay, let's see.
Interesting.
Okay, so cauliflower, cabbage, broccoli, Brussels sprout, kale, all these vegetables that are derived from the same plant, right? In fact, we cultivate the original plant as a crop as well. What is the plant? So Ayush has raised his hand. Let's see if Ayush can get it.
I knew these are all the same species, but I forgot but I'm guessing the original name is lettuce, I believe. Right? Yeah.
So no Ayush. Anyone else want to have a guess? So okay. Since there is no, so we'll keep the chocolate for ourselves. So let's move on to the next question. The answer is,
Will anyone guess?
you can take a guess at least. Random guess.
I think it's a very beautiful crop.
So it looks good.
Yeah. And DDLJ.
Come on. Come on. Dilwale Dulhaniya le jayenge. What you right. But then again, you shouted the answer. You didn't follow the etiquette. So, all right. So, you can only get like one chocolate for this. So, yeah, next time. So we'll move to the next question. Kiran?
Yeah. So the next question is, the first organ that forms in a developing embryo is the heart. What is the second organ that develops? Okay, we have a lot of.
Remember, we are asking about the second organ, not the first one. So we'll give the younger audience chance. Okay. So okay.
Can I give this one?
Okay, we can give this one.
Okay.
No more t-shirts for you, bud. Okay. So, are you liking the quiz so far? How do you think the questions are? Good. Okay. So, shall we make the quiz even harder? Okay. Let's find out a hard question. So, do you know heavy water? What is a heavy water? Do it. Okay. So, you have H2O, you have deuterium, like the hydrogen replaced with deuterium, right? So, will it, if you make an ice cube from that water, will it float or sink? So, I can see, I will give him a chance because he has not got a chance.
They will float. Because so it depends. The density of the water is also high, and the upthrust will be higher. It will not. It's not just that the ice cube is denser because it's made up of deuterium, but
So we'll take one more response for this. Yeah, Ayush, I will give him a chance.
Density of ice has an anomalous property, so the density is less than the liquid water, and that's why
will it float or
yes, it would float.
It will float. We'll take one more response.
So the clarification, both the water and the ice cube are both made of heavy water. So in that case, it should float only because the ice will still have the same structure. It's just that you're replacing some of the atoms. ice and water still will have the same structure, and the ice, they will both proportionally increase in density, but the ratio of the density should remain approximately equal. So they'll still float like they regularly do.
What if the water is H2O and the ice is the didotarium?
If the ice is made of heavy water, then it may sink. It may sink. I'm not sure about the exact ratios of the densities, but the ice is more likely to sink if only the ice is made of deuterium.
So Ayush wins a T-shirt. He has a T-shirt. Okay, we will give him a pen. Okay, pen and a chocolate maybe. So since you already have a T-shirt. So the answer is the ice cube made out of heavy water will sink because the density depends on mass, and deuterium has an extra neutron in it, so the mass will be heavier and it will sink. So yeah, but you didn't make that case. Ayush made that case. Okay.
Serve a chocolate.
Give me a T-shirt.
No, we'll give the T-shirt for a good answer. You were right, but I think Ayush has made his case very. So next one. Don't get disheartened. We will try to give everything what we have. We are not trying to save anything. So yeah, let's move on to the next question. Kiran. So yeah, Acanthamoeba is recently emerging as a public health concern in Kerala. It is what kind of organism? Whisper the answer. Don't shout. Are you okay? I think I'll give others some chance. Somebody raised their hands from here, I guess. Did anyone? You want to take a guess?
From the name, is it amoeba?
He said amoeba. Is it a acceptable answer? Yeah, it's a free living amoeba. Yes, but it's amoeba. So yeah, you okay?
Yeah, explain the whole process of it.
Okay. Yeah. Price. So so next question we are. Okay. Parenthegenesis is a way of reproducing without any genetic exchange with another parent, seen in bees or Komodo dragon. Human have used this process for their own, like we have used this process for our own benefits in agriculture. So the question is, where would you see the product of this process commonly around you? So I see 3 hands, okay, and we'll freeze these 3 hands only, and I'll give a chance to the person and behind because other 2 have already got chances.
I think it's banana.
Banana is the right answer. Yeah. So we use this to produce seedless fruits. Banana is one of them, so the answer was right. So yeah, she gets a prize. Uh, sh- so you find this questions easy? Okay. You want the hard ones? Okay, we'll don't just look for the prize. Enjoy the excitement behind the quiz. Okay. Next question is Subramaniam Chandrasekhar was awarded the Nobel Prize in Physics in 1983 for his work on stellar evolution. The question is, which other scientist won the Nobel Prize in Physics for what discovery and which year? Scientist, work, and year. All three. Ah, eh. So, partially answer. So the right answer is Sir C.V. Raman for discovering the Raman effect, and he won the Nobel Prize in the year 1930. Yes, so he gets something. So yeah, you can clap for the whoever answered. So for all the answers, so we can still. Do you want to easy question? Okay, okay. Ashwarika, load the question. So easy question. तो मतलब intermediate 28 में क्या
Was used in the 19th century to make vibrant green wallpaper, accidentally killing many people.
many है but we'll give a chance to the people who have attended that. He had not attended. Okay, I will take one more response. I'll take one more response. Yeah. Wait. Your turn. So yeah, these two.
These two were. These. Okay.
ये और ये. Look, you should not cheat in science, okay? And if you cheat in science, you don't go that far. So, huh? अच्छा वो हो गया ना यहाँ पे oh. Last question you last. हाँ. इसके बाद Okay. So we have a really cute question here. Okay. And this is the last question of the session. So the question is, calico cat and tortoise shell cats have a particular color and patches because of random X chromosome which gets inactivated in early cells, and their pigment genes are on these X chromosomes. What is so special about these cats? Uh, you can explain. So you better explain. Wait. Good. Yeah, you can explain.
Okay, so it's a very much biological term. Basically, it's a doses compensation. Like one of the part of X chromosomes, which is linked to the color coding, that gets inactivated. So some part of the cells have inactivation of the color white. Some has the part of inactivation of brown color. So that is called doses in compensation. Which gives the different color to the cat. So this experiment was done on the cats only to understand why they have different fur colors. Human also, females most of probably have the X chromosome like doses compensation also.
But okay, there's one more thing we are looking for in your answers. Okay, I think it's fine. Okay, so we can give out the prizes to Ayush and him, and now we close the quiz session. Did you like the quiz session? Okay, so come here next year for the next quiz session, and we will now have a science talk by Professor Malay Patra. He is he's an hello. He's a professor at Department of Chemical Sciences. His expertise are medicinal chemistry, and he works on drug delivery. He will be talking about catalytic drugs used in chemotherapy, and yeah, how and what are the cutting edge science being developed in in TIFR. So yeah, I will request Professor Malay Patra to enlighten us with the information about this catalytic.
No, that's okay. It's
Hi. So these speakers are, if you cross these speakers, the mic will howl. So be aware.
Yeah,
while
I'll just
talking
stand
to
right
you,
here.
use This area. And also, if you go further in the middle, the projector light will be. So
That's
since
fine.
we are live streaming, I'm
Yeah.
just
Yeah,
giving
yeah.
a heads up.
Sure.
It should be delayed because people might be coming.
Maybe just
go out and announce कि talk शुरू हो रहा है, talk शुरू हो रहा है. हाँ, district chemistry talk शुरू हो रहा है.
Yes, for 3 minutes, so we'll just start.
Post out and do some publicity.
ये
ये भी जा रहा है.
कल ही बाहर खड़े हैं.
So we'll wait for a few minutes. Are you interested in another question?
I don't think it works.
Quiz question.
No. Things to organize.
So all my colleagues are not here, so not able to load questions. But this won't have any prize. Are you still interested?
Definitely. কত সাথে তোমাদের 7-8 দিন হবে।
হ্যাঁ আমরা শুরু করিনি এবছর একটু ফরম্যাটটা আলাদা there will be some videos to watch
হ্যাঁ মানে তুমি তো নিশ্চয়ই কোনো ইনস্ট্রাকশন ইমেল পাঠাবে তার আগে।
So
I need the names. Give
the
me a
question
minute,
is,
I'll tell you.
which nearby star is predicted to be go supernova soon in our galaxy? which, so did you understand the question? Which nearby star is predicted to go supernova in nearby galaxy, like in our galaxy? So yeah, I see two hands, so I'll give her the first chance. So,
Betelgeuse?
right, Betelgeuse. I'm sure you also know the answer. Yeah, good. So we are waiting for a few minutes. Since we are waiting, let's continue with one more question regarding Betelgeuse itself. What kind of star Betelgeuse is? Yeah, you can shout out that. Right. Do you know which constellation it belongs to? What is the constellation which looks like a man like having a sword? Orion, right? So the shoulder star is the Betelgeuse. So sorry, we are hello. Yeah, everyone is able to see the slide clearly. If not, you can come closer in these areas to sit. Okay. Yeah, let's start the talk by Professor Patra. He will be talking about catalytic drug. So, Dr. Patra, please.
Okay, I think, am I audible to the end? Yes. So first I will ask you, how many of you are chemist or from related areas? Can you raise your hand? No. Biologist or related areas? Okay, very good. Some people. You don't have to be a chemist or biologist to understand this, huh? By the way, that was a joke. So it will be very simple. I kept it simple. There are some words, for example, the catalytic. Does it work? ऐसा I think इसको बैटरी चेंज करना है.
थोड़ा सा आप अगर ऊपर रखो आवाज नहीं
Was नहीं है. Maybe here. It's better now. Yeah. चलिए. अभी नहीं समझ आ रहा है? हाँ, very good. Okay, so what we will do is now I will tell you a little bit what we call drug. Okay, drug means medicine, not the bad ones. Okay, like cocaine or something. And then the term which is called catalytic, which is a little bit too technical for people who are not from chemistry background. This catalytic comes from catalyst. Okay, catalyst industry used for making chemicals. I think all of you know a lot of catalysts are being used for generating valuable chemicals nowadays. And we also do use catalyst for doing a variety of chemical transformations, whether it's organic, inorganics, and so on. Okay. Now you can see these two terms does not fit at all. Okay. You open a book, standard textbook, okay, of medicinal chemistry, chemistry, or anything, you will find either the term catalyst or the term medicine, okay, which is another word is drug. You will never find these two terms going along together, okay, anywhere. So I'm going to tell you a very new way of thinking about medicines, okay? And in the near future, probably we'll be able to get something which really works in this way, okay? So why we care about this? Because how many of you have never had paracetamol in your life? I think everybody had paracetamol at some point, right? Either as a suspension when you were a kid or as a tablet, okay? The white tablet that comes with different names, okay? So those paracetamol, have you ever asked, like you took a pill and then suddenly half an hour later your fever is gone and you also started feeling better because the body pain is gone? It's a mild painkiller, okay? Have you ever asked this question to yourself that I took a pill and what the magic happened in half an hour, okay? Basically, every disease has a specific target, okay? This is again a technical thing, but just think about a whole body. You have fever, okay, or you have any other disease. You break it down to different organs. So we are built of a lot of water and some important organs, lung, heart, so on, okay, kidney and all kind of things. Now you break it down, your organ, to a cell level, okay? Those are the small cells Debashish was talking about. If some of you have attended, you have seen that he was talking about the functional molecule of cells, which are protein and RNA, and DNA is the storage molecule, okay? So these are the typical 3 macromolecules that builds the cell. So that means we now goes to a level of single molecule, which are macromolecule, but still molecules, okay? Which you can read if you know a little bit of chemistry. If you know how carbon, hydrogen, oxygen, nitrogen comes together and then modify their own valency to give you a 2D or 3D structure, which is called a molecule, okay? Atoms builds molecule. So now if you think back, you can build molecules from atom. Those molecules can fold to give you certain functions. When a bunch of those comes together, that gives you a living cell, okay? And that inside that particular cell, you have a lot of chemical reactions which are ongoing in every fraction of seconds. That is making it living. You put together a lot of cells of different types. Let's say lung cell will build lung, kidney cells will build kidney, and so on. Now you put all together these organelles with some fluids, you get the whole body constructed, okay? With the bone, of course, a different type of cells. So now you can see if you look at, okay, it's too complicated, the whole body, you fragment it down and you ultimately end up with very simple chemicals where you can look things in a much more simplified manner, okay? So that is what I will try to tell you in the next 20-30 minutes or so, okay? That how one can really understand things using chemistry knowledge and then translate it to biological systems with the aim of ultimately treating a disease, okay? And the catalyst comes into the picture because the existing drugs, you take paracetamol, you take azithromycin, antibiotic, all kind of drugs that you treat disease,
they have a specific target. This is where they bind, okay? Because every disease is caused by malfunction of certain biomolecule, which are the functional molecule basically, either your protein or your RNA or your DNA. So what you are doing, you use a medicine to block the function of that particular protein. Okay, that's a very crude way of understanding a medicine. Whatever medicine you pick, you enter a pharmacy shop, you pick a tablet, you pick a liquid or whatever it is, it simply is a bunch of chemicals, okay, that specifically blocks either the function or expression of a functional molecule inside your cell somewhere in the disease area. This is how you get relief, okay, or you treat the disease. So that is what is enough to understand what a drug means. Now that means you also see that your molecule, every time it binds to a target, it gets consumed, right? So that means you need at least, if you have 50 copies of your disease causing molecule, you need 50 copies of drugs to come to contact and bind to it, right? So that means you are getting it consumed, your drug is getting consumed. Now just imagine a situation, you have one molecule of drug and that can cause damage to 50 copies of the disease causing molecules. So how cool is that? Because then you don't need a lot of dose, it will be cost effective. Second thing is every medicine has side effects, nothing is perfect, okay? It's really the balancing between the efficacy and toxicity. So you can reduce the toxicity significantly, okay? And who does that? A catalyst can do this, okay? So that is what I'm going to teach you, that it's really possible to fit these two terms together for thinking a better medicine for tomorrow, okay? All right, so now what I told you already is a lot of things, that a drug is nothing but a chemical, okay, which has a defined structure, and typically they're made of, most of them are made of organic carbon, nitrogen, hydrogen, and so on, sulfur. Some of them are exceptions, which are made out of metals, okay, which we are not going to talk because that will complicate the things, okay. But you will see, I will eventually come back to the metal, and I will tell you why is that. So drugs basically cause two things. They're not foods, okay. They cause changes in the physiological as well as sometimes psychological level, okay, and can be of broadly two types. One type are the bad guys, okay, which are really addictive stimulants. We're not going to talk about this. We don't have to develop this, okay. They're not for good. So drug is rather here pharmaceutical drug, which are the medicines, okay, that are again chemicals and you use to treat, cure, or prevent diseases, okay, or sometimes also diagnose some complicated disease. So these packets, I think you are familiar of. You see these packets when you enter the pharmacy, okay. Now these pills, okay, are not magics, okay. They contains really small molecules like this, formulated with some sort of items which are edible, okay, and which can allow you to make this kind of safe, fancy shapes, so that people buy it, okay. If I give this one to you as a powder, you will not buy it, okay. So that is how the drugs are made or tablets are made, and you buy them, okay. This is ibuprofen. I think a lot of us has had it. If you have inflammation issue, and paracetamol is very common thing, okay. Now coming, this also I told you, okay, how drug works. Every drug works on a particular target, and that target is coming from the disease selections, okay. So you have a disease, you have a particular target, which is here in this case, it's a protein, let's say, and the malfunction of this protein gives you the disease. So you have to block that, okay, that protein's function. You don't want that. You come up with a chemical, this smiley guy, and this, you have to design this chemical in such a way that it's a perfect fit to this protein, because you have thousands of protein in your cells. You don't want to harm all the proteins. You have to be extremely specific. So that means this is where your design comes into the picture. Your design has to be very, very handy, okay. So you don't touch any other protein, but you touch only the disease causing protein, and you form a protein drug complex like this. And since now your drug is fitting here, this protein cannot function in its usual manner. So the disease is stopped here, okay. You can go one step forward. You can make a covalent bond, okay. I don't know if you understand covalent or non-covalent, but this is kind of give you a more stable adapt, okay. So either you have a non-covalent binding or covalent binding, whatever it is. Ultimately, the goal is what you are doing. Here is a functional protein. You are making it a non-functional protein. Or if your disease is caused by a non-functional protein, you are activating the function of the protein, both way, okay? So you are changing the function of the protein, and changing the function of the protein is giving you ultimately the therapeutic response that you are looking for, okay? So this much, I think, is quite clear to you, right? That's not really very complicated. How you remember this is, you can remember this just like a lock and key, okay? So this is your lock, this is the key. Once you put it in, it's locked, okay? So this cannot function anymore. It's not free, all right? Now, everything is fine. We have a lot of drugs. You can treat, many diseases. The problem comes when you have certain disease when the medication available is not enough, okay? And cancer is one of them, all right? Because you have cancer, one type of cancer, 10 people gets it, 10 people will respond to a particular medicine in a different way, okay? Because the tolerability comes into the picture. It's not one-time medication. Unfortunately, you need to take it for months, for years. But let me remind you that the scenario is not same like what was 20 years back. Now, many cancers are treatable. A lot of them are also curable, okay? But you need to get yourself updated with the inventory of the drug, okay? Same happens with infections, which is also because of the superbugs which are getting resistant, does not respond to the medicines which are available in the pharmacy. Then you need to produce new medicines, okay? How you do this? The simple way that industry does is they follow the same thing. So you have a disease, you identify a disease, you develop a drug, and you follow this pathway, all right? Now, what is the problem? Everything is fine. Now, the problem is that when you have this kind of complicated disease, I told you, which is, let's say, cancer in this case, okay? This is a real example, a lymphoma. So this TBK1 protein is one of the essential protein for this cancer to grow, okay? So you want to block this, okay? This, you see this guy, this is the key here, okay? Ibrutinib is the inhibitor of this protein, was developed by AstraZeneca. And this guy binds here to the functional part of the protein, which is here, the C481, and block the function of the protein, and then you get the disease remission, okay? This is fine. Now the thing is, just think about a scenario, okay? That, as I told you, you need to treat the patient for a month. So you give one treatment, and in one cell, just assume that 100 copies of this protein is there, okay? You give 100 copies of drug. Now, when you are coming to with the next cycle, the cells already know, they're very clever. They also want to survive, right? So they make 200 copies of this protein for themselves. Then your 100 copies of the drug that you are giving is not acting at all. And that is what you call resistance, okay? So that means since your drug has to get consumed to block the function, that is where the problem is. But if your drug is not consumed, even if you have 500 copies of this, you can still deal with that, okay? So this is where the issue is, okay? Eventually, now one can actually correlate this catalytic drug, what I'm talking about, from where this concept came to our mind, is these are simple chemical transformations that you will learn also in class 12, for example. So this one is called ketone. You have a carbonyl here, okay? And sodium borohydride, this gives you H minus, which is a hydride, okay? That's a nucleophile. This is an electrophile, comes together, 1:1, you get the alcohol, okay? So you can assume that each molecule of this requires one molecule of this to get to the alcohol, okay? So that's a stoichiometric reaction. That's what we call, okay? So what you need, basically, you need at least get one equivalent or more reagent. You get a lot of byproduct generated and so on, okay? The same transformation can be done using a catalyst and using a sacrificial reductant, which is hydrogen here is a gas, okay? And you can use palladium and carbon-coated palladium. And here you see you need only 0.1 to 10 mole%, okay? You don't need this 1:1 equivalent ratio at all, okay? You can still do this transformation in a much better way without having a lot of byproduct and in a much faster and efficient way, okay? So that is what a catalyst can do. It can do the same job, but without getting consumed again during the process, because the palladium carbon you can recycle and can also reuse, okay? So you want to extend this concept for developing medicines, okay? Because all the medicines you can think of like this. You have one target, you are transforming it to a different target by using an inhibitor, okay? And that is getting consumed. So we want to follow this path, okay? Now, how do you do this? So coming back to the example, this example you have seen already, okay, in the lymphoma, one of the hot target in lymphoma. And this one is the inhibitor. So this is getting consumed. Ultimately, what you are getting is a functional protein becoming non-functional, okay? So that is what the task. What we're going to do is we're going to exactly do the same thing, but not using a drug, but using a catalyst. So that means one copy of catalyst can make this transformation for 1,000 of proteins, okay? That's the idea. So there will be a lot of benefits to this, okay? I've already told, I'm not going to read this. Specifically, we want to look at the resistance and the side effects here, the drug that we are using currently, okay? Now coming back to the cancer, I will give you one example that we are currently working on in our own lab here in TIFR, okay? So that you are convinced at the end that this is possible. I'm not something bluffing, okay? I will talk to you in the context of cancer, okay? And why we got motivated to work on this disease and to find a better treatment options is because this is one of the disease that kills millions of people, okay, and cause a tremendous amount of suffering in the society. Only the family who got this nasty guy, they knows, okay, how pathetic this is. And now, if I have to tell you, if you're not from the science background, that how does it works is you get a normal cells, which is your building block, and because of some sort of cause, you get some unfortunate mutations, okay, in your DNA. And then this guy became wild, okay, and it does not stop to proliferate. So you get 1 to 2, 2 to 4, 4 to 8, then the exponential growth, okay? And then you get a undesired mass somewhere in your organ. So here, let's say in the kidney, okay? It was a normal kidney cell, and then suddenly it started growing that your body doesn't want, and it gives you a 3D undesired mass, okay? And it started now behaving as your own organ, but it's an undesired organ, okay? And want to survive within you like a parasite, okay? And again, at the same time, it's your own cell. So you can see the difference, okay? It's not a bacteria or virus coming from outside, which are relatively easy to get rid of, but this is your own cell, okay? Now, this is not everything. Then what happens is it's very complex pathology, which makes this disease even more, dangerous. It's not only just growing the cells, it can metastasize from one organ to another organ. It can completely destroy your immunity in the local where it's growing, okay? It can create resistance to the therapy, whatever you are using. So you can see that how difficult this disease is to treat, okay? And the drugs that are available here for chemotherapy, a lot of you know that when people get cancer, most of the cases, chemotherapy is the one which is used. There is a reason. Nowadays, there are advanced therapy. You might have heard of cell therapy, CAR T cells, okay? Immunotherapy, Nobel Prize was given 2 years back, okay? There are a lot of advanced therapy, but those therapies does not work as a standalone therapy, most of the cases. Second thing is, also those are not affordable, because when you are talking about CAR T cell therapy, it's a personalized therapy, okay? It's your bone marrow cells are taken, engineered, and put it back. So that means for every individuals, you have to design the therapy, and you can imagine the cost of that, which is not possible for common people, okay? So chemotherapy is still one of the main way of treating drugs. So chemotherapy is what? It's basically using toxic molecule. Let me tell you a simple thing. Toxic molecules, I will not even use a molecule, okay? Because you want to kill something. So that means you need to use toxic molecules. But now then the issue is, you see, how do you make sure that your drug is really toxic to the tumor, but not toxic to the rest of the kidney? In the case of kidney tumor, for example. That's very, very difficult, okay? So chemotherapy is all about using toxic chemical and balancing the efficacy and toxicity, okay? That's what chemotherapy definition is. So these are small molecules which are currently used in the clinic. All of them, most of them actually binds to DNA. So you see, DNA is the one where your replication starts, okay? Then translation, and then you get to have from 1 cell to 2 cells. So these guys block the DNA to have 2 copies or translate into RNA, and then you get the cells to stop growing, okay? But the problem here is, you can see again here, this is getting consumed, okay? When it binds to the target, it's done, huh? So you need at least more than stoichiometric drug. So the problem here is it's monotargeted. You want to have monotargeted drug because you want to have extreme selectivity, but that backfires. When you talk about cancer, for example, you need to have little bit nasty drugs, okay, which can cause a lot of damage. But in a particular area of your body where you have the cancer. So the issue is resistance, okay, because of they're getting consumed, and you need a lot of dose because one molecule at least needs one molecule to cause the damage, okay. So here the catalytic drug can come into the rescue. So what we thought here is that if you look at the pathology of the cancer, it's not only proliferation, but a lot of them, okay. So all of them are nicely connected with a very complex genetic network. You can see these things, okay, which is very, very complex. And now if you look at this as a chemist, okay, one common thing is there is that every chemical reactions here, which is doing the signaling to the pathology, is controlled by a very controlled redox homeostasis, which is inside the cell, okay. What redox homeostasis means? Every reaction you can think of as an oxidation or reduction, which requires a controlled environment of redox to function, okay. Now, if you destroy this, then a lot of them will be cut down, okay. And if you can cut down this, lot of pathology is not only one, you can cut down a lot of pathology of the cancer, okay. And if your drug is now catalytic, you don't have to worry much about the side effects, okay. Then where do you start? Because there was no guidelines available. This is a completely new concept we started working on. No guidelines are available, and you don't know how to design a molecule like this because you don't have a target. You see, we are targeting the physiology of the cell rather than a particular protein, what you have seen, the way the traditional drugs are developed, okay. So what we thought is we went back to the literature and then looked at a particular reactions. Which reactions we are looking at? These two molecules, okay. The thiols in the cells are the controller of the redox homeostasis. So we want to do catalytic reactions on thiols and inside a cancer cell in a controlled manner, okay. So what catalyst do we choose is when we look at in the literature, people have done a lot of organic chemistry catalysis, and we saw that there are rhenium is a metal, okay. Rhenium molecules, rhenium containing molecules can transform thiol to its oxidized form by utilizing H2O2 or even oxygen, okay. And those reactions were done in reaction vessels, single substrate, single catalyst, no air, no moisture, organic solvent, but this works, okay. So we thought that let's start here, okay. So what we need is, if you want to go from a reaction flask to do catalysis inside the cell, you can, I think, appreciate the complexity here, okay. The first barrier is your catalyst has to enter the cell, okay, which here you are simply adding through the open neck, okay. Second thing is here you have only one reactant. Here you have thousands of reactants, and your catalyst has to reach to those reactants which are again compartmentalized inside the cell and then to do its job, okay. So it's a very, very challenging task, and we have to start somewhere. So we started with this class of molecule. What we did is we used our synthetic chemistry library, synthetic chemistry facility to generate a library of this class of molecule, okay. And you can see here, this is a rhenium complex containing rhenium in 5 oxidation state. We generated a library, and what you do is afterwards, then we started screening, okay. What are the criteria that we put? Your catalyst has to be water stable, stable in human plasma. The reactivity with biological nucleophile should not be there, okay. That is what will assure the stability. The catalytic efficiency has to be good or moderate because first generation compound, that is fine. And then this can also enter the cell, okay. When we apply all these criteria, we found one molecule only, okay, out of many, and we went ahead with this, okay. So this is now a simple chemical that we have synthesized, and we looked at in a cuvette, in a reaction vessel, okay. So this is a thiol, okay. You can see this is called glutathione, okay. Why I called it a thiol is because of this SH group here, okay. And this is present in the cells in tens of millimolar concentration and is the main redox buffer, which controls a lot of signaling process, okay. So then what we did was we throw the catalyst that we have made to the reaction vessel in water, 10 mole%, and what we saw was this catalyst, what we made, this 8, can actually catalytically oxidize glutathione to form this disulfide bond, okay. And here is the thing. So this is an NMR spectra, okay, because you have to monitor these two things. So you see the signal from GSH is absent here with time, and then the signal for this guy is actually arising. So you integrate this, and you can calculate something called TON. TON means turnover number. Okay, what does that mean? Is this is very important. So you can see one molecule of this 8 can oxidize at least 900 molecule of this. That is what it means. Okay, before it's degrading. So if you have a drug, okay, imagine this 8 as a normal drug, and this is your biological target. So one molecule of drug can only damage one molecule of your biological target. That is what you have seen, right? But this guy now can damage more than 900 targets, okay, just by one molecule. Okay, so it's really catalytic. But then we looked at the mechanism, because we are chemists, we love drawing this kind of things. Okay, so we looked at a lot of spectroscopy, and then we found out that how this cycling is happening. So we start here, this chloride goes out, you have this active catalyst generated, it picks up oxygen, which is present in the tissue, and then it forms this kind of dimer, it undergoes homolytic cleavage, you goes to rhenium 7. So this is this is the important part. If 5, here you have 7, that means 2 electron is gone. Okay, then it has to gain 2 electron from GSH. So 2 molecule of GSH comes, gives you 2 electron, and then 1 oxygen is out as water, and then you form this one, and this guy is now back to the rhenium 5 and picks up again electron. Okay, so this is what one molecule can give you 900 cycles. Okay, now the thing is, we are coming back a little bit to the biology. Okay, until now it's fine. Okay, people have done this, we have made a new catalyst. What's big thing? Okay, so now we first check that this molecule, to do catalysis, you have to have the plasma membrane permeability and enter the cells. Okay, so what we used here a technique called inductively coupled plasma mass spectrometry, which can quantify metals in tissue with a high accuracy. Okay, so we have a metal here, that is what we used as a tag. And if you look at here, the picomole metals that enter the cells per million cells, this is way higher than a clinical drug. So this is a clinically available drug. This is the ballpark that we set. We wanted to have this molecule at least comparable or higher uptake inside the cell, and that is what we saw. Now the second question comes is, can this reach the compartment of the cells and picks up glutathione and can oxidize catalytically? Okay, so that is what we have done. We have picked a lung cancer cell. This A549 is a lung cancer cell. So what it does is that this molecule goes in, picks up oxygen which is available inside the cell, and then transform this SH containing molecules, glutathione as well as proteins, okay, to its oxidized dimer, which makes it completely non-functional. And once you destroy this redox balance in the cells, what you have your oxidative stress generated. Okay, so that is what you can see here. We have used a tracer. You have a lot of reactive oxygen species now generated. You can see the cells light up. These are cells. Here you see not much. You treat with the catalyst, it lights up. And then now your cells are under stress, and it's a catalytic stress with a very low dose. And then we expect the cells to undergo death. Okay, and that is what you have seen. I'm not showing this one here. Okay, so these are lung cancer lab model tumors. Okay, you can see the 3D shape like a tumor. So what this dye does, this calcine AM, is it's staining the live cells. Okay, so these green things are live cells in a tumor. All right, and this dye, the red one, this one stains the dead cells in a tumor. Okay, so what we did was we build this tumor and we allow them to grow. Okay, one petri dish has this tumor. We did not treat them with any drug. Another petri dish, we treat them with a clinically available drug, which is cisplatin. Okay, another petri dish we treated with the catalyst that we developed. Okay, so you see with time, what happens here is this is your untreated one. It grows bigger. Okay, you treat with the cisplatin, which is a drug, it's smaller, and then this catalyst also can reduce the size. All right. Now, if you look at the number of, this is the size, but if you look at the number of dead cells, this catalyst can cause much more damage because the light of red is much more here compared to this. Okay, so then what it basically tells you is that this compound can actually kill cancer cells. And now I want you to look at the dose. Okay, so look at this. We had to use 15 micromolar, and here is 0.7 micromolar. Okay, so it's nearly 24 lower dose, but doing a much better job. Okay, and that is what a catalyst can do. Now, if you can use a 20-fold less dose and can get the same efficacy, you can cut down a lot of side effect. I think you agree with that, okay? Because paracetamol, you take typically 500 or 600 mg, right, as an adult. You can take maybe 2 or 3 max to max, depending on the situation. But if you take like 10 of them, what will happen? You will become more sick, right? You will have a lot of side effects. So that is what I'm talking about the dose, okay? All right, so I think that should be enough. So what I told you is that currently the drugs are designed to fit to a pocket within a protein. So that's a stoichiometric binding. But there is a possibility to use catalyst to get the same effect, okay, where the drug is not consumed and the benefit is your side effect, as well as you can have less resistance, okay? And that is possible. You start with a reaction flask where you generate the catalyst, you reconfirm, then you do a whole lot of biological testings, and ultimately we are looking for in the near future to have a drug which can perform in a catalytic manner, okay? And now I would like to thank the people who work in the lab basically with these great ideas. We have many PhD students. The names are here, I'm not going to read, but specifically the catalytic work was done by a PhD student, Suvangi, and she is now a research associate working with us. And I would also like to thank a lot of collaborators that we have to collaborate, because not a single guy knows everything. You see the research is very interdisciplinary. We need to also deal with mice sometimes, okay, and rats, and then the generous funding, okay. Without money, you cannot do research, okay. End of story. So thank you very much. And if you have any question, you can feel free to ask. So yeah, all right.
Hi. I just want to know, is this still at conceptual level or is it already commercially available? And if
No, that's very conceptual level. That's the first example I have shown you in the world.
okay, so how old is this tech in the sense of this concept?
We started working on 3 years back. So it's only 3 years old, the whole concept.
Okay, thank you.
So it will take a lot of time to go to the clinic. Okay, that's the really fast generation. Yeah, there will be multiple generations, multiple let's say tuning of the structure to improve certain properties, and this is just really the concept.
Thanks.
Hello, sir. So I wanted to know that you talked about its binding. So does it work in the same way as an enzyme substrate complex does?
Exactly.
Exactly.
Yeah. So all the
The-
binding of drugs are really, the concept came from enzyme substrate. Huh? So what you do is, if you pick enzyme is also a protein, right? So your enzymatic dysfunction can also lead to a disease. So that time what can happen is you try to mimic the substrate. So the substrate can bind and come out, but you want to have a better binder which can be a substrate but at the same time can stick there. So that is exactly the concept was translated to the clinic, and then you get all the drugs coming up.
So one more question. Here you said that the molecule that we came at was lead to be used.
Lead?
Lead, the metal lead was
Okay, not
decided
lead,
to
it's rhenium. Yeah.
Austranium.
Hmm.
Okay. So, sir, heavy metal poisoning is also a thing. So, does that have a side effect here?
Yeah. So now the thing is, this is the problem. This heavy metal poisoning, this buzzwords, no, let me just tell you this. These are not really very correct thing. Okay. When you say poisoning, okay, poisoning, the first thing, if you don't say the dose, at which dose it poisons, okay, it has just simply no meaning, because your water can be a poison if you drink too much, right? Now the thing is, we call heavy metal poisoning, arsenic poisoning. These things are simply a wrong word. All right, arsenic is everywhere. You pick a fish, I can tell you, pick a fish from Sassoon Dock. We have measured it here, okay, and you measure the arsenic content. There is arsenic, okay, because you throw them in the darya, no, right? So the fish will eat it, okay, and we're getting it again. Now the thing is that at what concentration arsenic is toxic, unless you spell that clearly, okay, this poison thing is not valid, first thing. Now, second thing is the heavy metal poisoning. I'm coming there. As I told you, you need toxicity to kill something. All right. Now you have to deal with this, keep the toxicity minimum. That is why we are going to catalytic. So here the applied dose will be so low that you not reach the toxic limit. Okay, I hope this clarifies. Yeah, because when you have one molecule causing damage to 900 molecules, right? Then the heavy metal toxicity is not coming into the picture, because as I told you, the dose will be way lower than your toxic dose. But then the organic molecules, even if you take, okay, then the issue is that you get resistance and it does not work. So it's better to have something little bit toxic which works rather than having nothing. All right. And that is the thing, it depends on the disease. Obviously, I will not tell you to take a toxic medicine for curing fever. But when you have no choice, when it's cancer, okay, you really want to get rid of that bad thing, okay, with the cost of little bit of side effect, which is tolerable. Okay?
There has to be that.
All right.
Sir, so what exactly is the oxidation reaction in the cancer that you're trying to block? And how do you know that this reaction will only occur in cancer cells?
Exactly. That's the thing. So now look, for drugs, there are two things important. So for your first question was which oxidation reaction is happening. That's the thing, right? So it's not an oxidation reaction. The molecule is oxidizing thiols using oxidation as a oxygen as a sacrificial oxidant. All right. So now mechanistically what happens is that you have 5 oxidation state 5 in your catalyst. Oxygen comes, transform this 5 to 7. That means you are losing 2 electrons. All right. You know oxidation reaction? Oxidation can be 2 ways. Okay, you can either lose electron, that's an oxidation, or you can install oxygen, that is also oxidation. All right. So in this case, both are happening, and you end up having uranium-7, which is of 2 electrons short than the original species. Then it would like to take 2 more electrons from something. That means that guy has to be oxidized to get back to 5. Okay. So that is the cycle which goes on inside the cell. Now you say, how do you know it's happening in the cell, right? That's a fantastic question. This is where the mechanism comes into the picture. I did not present it anywhere. So now you see in the catalytic cycle, what you need first oxygen, right? So to prove that scientifically, you culture cells in an hypoxic environment where you don't have oxygen, and you see your reaction will not work. Okay, that's a direct proof, first of all. Second thing is that the rhenium-5 to rhenium-7, okay, what you do, you treat your cells with the catalyst, you harvest the cells, you lyse them, and you quantify those species inside the cell, if they exist. Okay. Now the third thing is in the second part of the cycle, you have seen the glutathione comes and then get oxidized, right? So that we have already measured in the cells, that it is happening inside the cell. Okay. So these are the evidence, if you put together, is enough to say that it's real and it's happening. All right. Yep.
Thank you, sir, for trying to answer and giving feedback, but I don't think you properly answered. This rhenium-7 to rhenium-5 is what the catalyst your medicine is doing, right? My question was the bad cancer reaction that you are trying to stop. That bad reaction, how do you know that that's only happening in cancer cells and you can target that and destroy the cancer cells only?
Okay, the selectivity problem. Yeah, that's another next level of question. So you have to have the catalyst working in the cancer cell. That's the ideal scenario, right? You have a normal cell, let's say you have an organ, and you have full of normal cells and somewhere a tiny bit of cancer. All right. So you have given the things. Now, how your catalyst preferentially destroy the cancer cell? That's what you're asking, right? Now, there are multiple ways of doing these things. Okay. So here you see, when we pick the substrate inside the cell, which is glutathione, okay, glutathione is one of the main driver of cancers. Why is that? If you measure glutathione in normal cells and cancer cells, it will be at least 10-fold higher in cancer cells. Okay, so that's exactly how you pick a target. Target means even the pharmaceutical drugs which are in the clinic, those proteins which are targets are available in the disease cells in many more copies compared to normal cells. The same applies here in the case of glutathione. So you get some sort of selectivity based on the availability of the target, because you have more glutathione in the cancer cells. So more the catalytic cycle will run, more disbalance will happen there. Okay, but that is a qualitative measure. Okay, so let's say if I tell you that 10-fold upregulation of your substrate in the cancer cell, you can max to max expect 10-fold difference, right? Not more than that. Then you can bring more selectivity to this by making your drug targeted. How do you make it targeted? That time, typically cancer cells have a lot of receptor or transporters on the surface, which are again elevated, not present in the normal cells or present in a minimum amount. You can use a transporter recognition unit attached to your drug so that the vector will carry your catalyst or drug to the cancer cells and allow its accumulation more and more in the tissue. So then you get two factors. One factor is selectively delivering your catalyst to the cancer cell, and the second factor is selectively exploiting the overexpressed target in the cancer cell itself. So your selectivity will further go up. The third layer to add this is you can put it inside a polymer that will prevent degradation and other things when it's circulating in the body, in the plasma basically. That will add up a third layer of selectivity through something called enhanced permeability and retention effect, okay, which is little complicated. But these three layers of targeting that one can do, right?
I have a follow-up. Since the approach is very new, is it fair to say that we haven't yet fully understood how cells will respond to such things, in the sense of, going back to traditional drug deployment, cells develop some form of resistance. There are a lot of kind of responses like that which combat it. So is it fair to say we don't know yet how
We
this
don't
will
know,
be combated?
no, we don't know yet that. But what we have seen is that first thing is we have evidence that it is working better even at 1/20th dose than the normal drugs. That's a significant dose reduction, first of all. So even if there is resistance, you have the window of at least to go 20-fold higher to match the dose of the clinically available drug first. Now, second thing is, what will be the mechanism that will drive resistance, let's say, against this guy? That is, we are yet to figure out, because we have to first find a perfect candidate and then find where that lacks the efficacy, for example.
Thank you.
Yeah.
Any more questions? If not, let's thank Professor Malay Patra for his wonderful talk and informative. So we are closing this session here. At 4 o'clock, there is a public talk at the auditorium. So you may join if you want to. Thank you.
Okay,